Hi everyone, welcome to this video tutorial on machine learning projects by Simplilearn. In this video, we will cover some of the crucial topics related to machine learning and explore the different algorithms that are widely used to solve machine learning tasks, and then we'll look at several machine learning projects which are very interesting. So here is the agenda for today's session. We will begin by learning the basics of machine learning, and then we will explore about linear regression analysis, followed by logistic regression with hands-on demo sessions in Python. Next, we'll understand about decision tree and random forest. After that, we are going to learn about support vector machines, k-nearest neighbors, and k-means clustering with hands-on demo in Python programming. Moving ahead, we'll learn how to predict coronavirus cases using several algorithms in machine learning. Next, we'll explore about the stock market analysis, and then we'll look at an exploratory data analysis about the World Happiness Report, followed by understanding how you can use election data to make United States election prediction. We will wind up this session by learning about time series in R, and then we'll look at German credit and college admission project.
What is machine learning? Hello, my name is Richard Kirschner. I'm with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. Today we're covering what is machine learning. What's in it for you? We're going to cover the basics of machine learning. What is machine learning? Artificial intelligence versus machine learning versus deep learning. How does machine learning work? Types of machine learning prerequisites, applications of machine learning. Here we have our, it looks a little bit like Frankenstein, our Frankenstein-looking robot. Today, let me tell you what is machine learning. Machine learning works on the development of computer programs that can access data and use it to automatically learn and improve from experience. Watch a robot builder construct a house in 2 days. This was back in July 29th, 2016, so that's pretty impressive. This amount of time to continue to grow in its development. And it's smart enough to leave spaces in the brickwork for wiring and plumbing, and can even cut and shape bricks to size. Amazon Echo relies on machine learning, and with more data it becomes more accurate. Play your favorite music, order pizza from Domino's, voice control your home, request rides from Uber. Have you ever wondered the difference between AI, machine learning, and deep learning? Artificial intelligence, a technique which enables machines to mimic human behavior. This is really important because this is how we are able to gauge how well our computations or what we're working on works, is the fact that we're mimicking human behavior. We're using this to replace human work and make it more efficient and make it more streamlined and more accurate. And so the center of artificial intelligence is the big picture of all of this put together. IBM Deep Blue Chess, electronic game characters. Those are just a couple examples of artificial intelligence. Machine learning, a technique which uses statistical methods, enabling machines to learn from their past data. So this means if you have your input from last time and you have your answer, you use that to help prove the next guess it makes for the correct answer. IBM Watson, Google search algorithm, email spam filters, these are all part of machine learning. And then deep learning, which is a subset of machine learning, composing algorithms that allow a model to train itself and perform tasks. AlphaGo, natural speech recognition. These are a couple examples. Deep learning is associated with tools like neural networks where it's kind of a black box. As it learns, it changes all these things that are, as a human, we would have a very hard time tracking. And it's able to come up with an answer from that. Now let's see how machine learning works. First, we start with training the data. Once we've trained the data, we go into the machine learning algorithm, which then puts the data into a processing, which then goes down to another machine learning algorithm. And then we take new data, because you have to test whatever you did and make sure it works correctly, and we put that into the same algorithm. Once we do that, we check our prediction, we check our results, and from the prediction, if we've set aside some training data and we find out it didn't do a good job predicting it, and it gets a thumbs down as you see, then we go back to the beginning and we retrain the algorithm. And a lot of times it's not just about getting the wrong answer, it's about continually trying to get a better answer. So you'll see the first time you might be like, oh, this is not the answer I want, depending on what domain you're working in, whether it's medical, economical, business, stocks, whatever. You try out your model, and if it's not giving you a good answer, you retrain it. If you think you can get a better answer, you retrain it. and you keep doing that until you get the best answer you can. Let's see the types of machine learning. Supervised learning, unsupervised learning. There's a number of ways to divide up machine learning and how it works. These are two main categories you can divide it into. Supervised learning, we have a known amount of data. So in this case, we have a bunch of apples. We have a machine learning algorithm. It goes through the process. It goes through and trains a model based on that known data. And then once you've trained your model on the known stuff, you can then put an unknown data in there, and you get a new response. And of course, in this particular one, it's an apple. So it's trying to figure out whether it's an apple or another fruit. There are many different algorithms you can use for computing this information, for doing this supervised training. Just to list some of the top ones that are currently being used, and by no means there's more than just this. So by no means this isn't the complete list. There's polynomial regression, there's a random forest, there's linear regression, there's logistic regression, there's decision trees, there's k-nearest neighbors, and there's naive Bayes. Like I said, this is just a short list of some of the many tools that are out there nowadays. And if you have supervised learning, then we should also look at unsupervised learning. Unsupervised learning. So we have unknown data. In this case, you can see we have a bunch of fruit, and we might not have labeled it. We don't know. We've never had anybody look at it and say, this is what this is. And we take that data, and we put it through the machine learning algorithm. And then that goes through the processing and then the trained model. And what the trained model says, hey, can I see a pattern here? And from that pattern, it divides it up into a response. In this case, apples and pears. You can see some of these things look just like the other, and it tries to put them all together so that you get similar things in similar groups. And again, we have a nice list of algorithms here, and this is not the only algorithms used for this. So don't limit yourself to just these. These are just some of the primary ones used today. And of course, we have the k-means clustering, singular value decomposition, fuzzy means, partial least squares, a priori, hierarchical clustering, principal component analysis. Machine learning prerequisites. Computer science, fundamentals and programming. So any of the machine learning out today, you have to know some basic scripting or programming. Intermediate statistical knowledge. You have to understand a little bit about probabilities. If A is current, how likely is B going to happen? If there's clouds overhead, how likely is it going to rain? Linear algebra and intermediate calculus. The linear algebra is very important because you have to understand basically drawing a line through the data points and what that means. That's the most fundamental linear regression models. You draw a line through all your data and you use that line to compute new values. Intermediate calculus means you need to have a little bit of understanding of what a differential equation is. You really don't need to be an expert because the computer does all the heavy lifting for you, but it's important to know the terms when they come up, unless you're doing some advanced programming on the actual models themselves. And data wrangling and cleaning. I would say this might be the biggest one in here, is you have to start getting a grip on how to clean up your data. There's a saying is, bad data in, bad data out. Good data in, you're more likely to have good data out. Some applications of machine learning. Instance segmentation. Object detection. Instance segmentation. You can see here where they use machine learning to go in there and find where the different cats are and the different objects are in the picture. And then in segmentation, it actually cuts them out. Kind of a fun one, especially if you have a Google Pixel phone and you can do little animation objects on top of your ongoing pictures you're taking or movies. Number plate detection. You can see here where we have a car and it comes in there and it finds a number plate on the car. Once it's done that, it can then do automatic translation. Automatic translation is we pick up some symbols, in this case on a machine, and it does machine translation so that you can know what it's saying even if you don't speak that language. Let's look at another example of machine learning. Based on the amount of rainfall, how much would be the crop yield? So here we have our crops, we have our rainfall, and we want to know how much we're going to get from our crops this year. So we're going to introduce two variables, independent and dependent. The independent variable is a variable whose value does not change by the effect of other variables and is used to manipulate the dependent variable. It is often denoted as x. In our example, rainfall is the independent variable. This is a wonderful example because you can easily see that we can't control the rain, but the rain does control the crop. So when we talk about the independent variable controlling the dependent variable, let's define dependent variable as a variable whose value change when there is any manipulation in the values of the independent variables. It is often denoted as y. And you can see here our crop yield is dependent variable, and it is dependent on the amount of rainfall received. Now that we've taken a look at a real-life example, Let's go a little bit into the theory and some definitions on machine learning and see how that fits together with linear regression. Numerical and categorical values. Let's take our data coming in, and this is kind of random data from any kind of project. We want to divide it up into numerical and categorical. So numerical is numbers, age, salary, height, where categorical would be a description, the color, a dog's breed, gender. Categorical is limited to very specific items, where numerical is a range of information. Now that you've seen the difference between numerical and categorical data, let's take a look at some different machine learning definitions. When we look at our different machine learning algorithms, we can divide them into three areas: supervised, unsupervised, reinforcement. We're only going to look at supervised today. Unsupervised means we don't have the answers and we're just grouping things. Reinforcement is where we give positive and negative feedback to our algorithm to program it, and it doesn't have the information until after the fact. But today we're just looking at supervised because that's where linear regression fits in. In supervised data, we have our data already there and our answers for a group, and then we use that to program our model and come up with an answer. The two most common uses for that is through the regression and classification. Now we're doing linear regression, so we're just going to focus on the regression side. And in the regression, we have simple linear regression, we have multiple linear regression, and we have polynomial linear regression. Now on these three, simple linear regression is the examples we've looked at so far, where we have a lot of data and we draw a straight line through it. Multiple linear regression means we have multiple variables. Remember where we had the rainfall and the crops? We might add additional variables in there, like how much food do we give our crops? When do we harvest them? Those would be additional information add into our model. And that's why it'd be multiple linear regression. And finally, we have polynomial linear regression. That is, instead of drawing a line, we can draw a curved line through it. Now that you see where a regression model fits into the machine learning algorithms, and we're specifically looking at linear regression, let's go ahead and take a look at applications for linear regression. Let's look at a few applications of linear regression. Economic growth, used to determine the economic growth of a country or a state in the coming quarter, can also be used to predict the GDP of a country. Product price can be used to predict what would be the price of a product in the future. We can guess whether it's going to go up or down, or should I buy today. Housing sales, to estimate the number of houses a builder would sell and what price in the coming months. Score predictions, cricket fever, to predict the number of runs a player would score in the coming matches based on the previous performance. I'm sure you can figure out other applications you could use linear regression for. So let's jump in and let's understand linear regression and dig into the theory. Understanding linear regression. Linear regression is a statistical model used to predict the relationship between independent and dependent variables by examining two factors. The first important one is which variables in particular are significant predictors of the outcome variable. And the second one that we need to look at closely is how significant is the regression line to make predictions with the highest possible accuracy. If it's inaccurate, we can't use it. So it's very important we find out the most accurate line we can get. Since linear regression is based on drawing a line through data, we're going to jump back and take a look at some Euclidean geometry. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. And if you look at our model here, we plotted 2 points on here, x1 and y1, x2 and y2. Y being the dependent variable, remember that from before, and x being the independent variable. So y depends on whatever x is. M, in this case, is the slope of the line, where m equals the difference in the y2 minus y1 and x2 minus x1. And finally we have c, which is the coefficient of the line, or where it happens to cross the zero axes. Let's go back and look at an example we used earlier of linear regression. We're going to go back to plotting the amount of crop yield based on the amount of rainfall. And here we have our rainfall. Remember, we cannot change rainfall. And we have our crop yield, which is dependent on the rainfall. So we have our independent and our dependent variables. We're going to take this and draw a line through it as best we can through the middle of the data. And then we look at that, we put the red point on the y-axis is the amount of crop yield you can expect for the amount of rainfall, represented by the green dot. So if we have an idea what the rainfall is for this year and what's going on, then we can guess how good our crops are going to be. And we've created a nice line right through the middle to give us a nice mathematical formula. Let's take a look and see what the math looks like behind this. Let's look at the intuition behind the regression line. Now, before we dive into the math and the formulas that go behind this and what's going on behind the scenes, I want you to note that when we get into the case study and we actually apply some Python script, that this math that you're going to see here is already done automatically for you. You don't have to have it memorized. It is, however, good to have an idea what's going on, so if people reference the different terms, you'll know what they're talking about. Let's consider a sample data set with 5 rows and find out how to draw the regression line. We're only going to do 5 rows because if we did like the rainfall with hundreds of points of data, that would be very hard to see what's going on with the mathematics. So we'll go ahead and create our own 2 sets of data, and we have our independent variable x and our dependent variable y. And when x was 1, we got y equals 2. When x was 2, y was 4, and so on and so on. If we go ahead and plot this data on a graph, we can see how it forms a nice line through the middle. You can see where it's kind of grouped going upwards to the right. The next thing we want to know is what the means is of each of the data coming in, the x and the y. The means doesn't mean anything other than the average. So we add up all the numbers and divide by the total. So 1 plus 2 plus 3 plus 4 plus 5 over 5 equals 3. And the same for y, we get 4. If we go ahead and plot the means on the graph, we'll see we get 3, 4, which draws a nice line down the middle. A good estimate. Here we're going to dig deeper into the math behind the regression line. Now remember before I said you don't have to have all these formulas memorized or fully understand them, even though we're going to go into a little more detail of how it works. And if you're not a math whiz and you don't know, if you've never seen the sigma character before, which looks a little bit like an E that's opened up, that just means summation. That's all that is. So when you see the sigma character, it just means we're adding everything in that row. And for computers, this is great because as a programmer, you can easily iterate through each of the XY points and create all the information you need. So in the top half, you can see where we've broken that down into pieces. And as it goes through the first 2 points, it computes the squared value of x, the squared value of y, and x times y. And then it takes all of x and adds them up, all of y adds them up, all of x squared adds them up, and so on and so on. And you can see we have the sum of equal to 15, the sum is equal to 20, all the way up to x times y, where the sum equals 66. This all comes from our formula for calculating a straight line, where y equals the slope times x plus the coefficient c. So we go down below, and we're going to compute more like the averages of these, and we're going to explain exactly what that is in just a minute, and where that information comes from. It's called the square means error. But we'll go into that in detail in a few minutes. All you need to do is look at the formula and see how we've gone about computing it line by line, instead of trying to have a huge set of numbers pushed into it. And down here you'll see where the slope m equals, and on the top part, if you read through the brackets, you have the number of data points times the sum of x times y, which we computed one line at a time there, and that's just the 66. And take all that and you subtract it from the sum of x times the sum of y. And those have both been computed. So you have 15 times 20. And on the bottom, we have the number of lines times the sum of x squared, easily computed as 86 for the sum, minus, I'll take all that and subtract the sum of x squared. And we end up, as we come across with our formula, you can plug in all those numbers, which is very easy to do on the computer. You don't have to do the math on a piece of paper or a calculator. And you'll get a slope of 0.6. And you'll get your c coefficient. If you continue to follow through that formula, you'll see it comes out as equal to 2.2. Continuing deeper into what's going behind the scenes, let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 0.6 and c equals 2.2. We're going to take these values and we're going to go ahead and plot them. We're going to predict them, so y equals 0.6 times where x equals 1 plus 2.2 equals 2.8, so on and so on. And here, the blue points represent the actual y values, and the brown points represent the predicted y values based on the model we created. The distance between the actual and predicted values is known as residuals or errors. the best fit line should have the least sum of squares of these errors, also known as E-square. If we put these into a nice chart where you can see X and you can see Y, what the actual values were, and you can see Y predicted, you can easily see where we take Y minus Y predicted and we get an answer. What is the difference between those two? And if we square that, Y minus Y prediction squared, we can then sum those squared values. That's where we get the 0.64 plus the 0.36 plus 1, all the way down until we have a summation equals 2.4. So, the sum of squared errors for this regression line is 2.4. We check this error for each line and conclude the best fit line having the least E-square value. In a nice graphical representation, we can see here where we keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. Now, we only looked at the most commonly used formula for minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. What you want to take away from this is whatever formula is being used, you can easily, using a computer programming and iterating through the data, calculate the different parts of it. That way, these complicated formulas you see with the different summations and absolute values are easily computed one piece at a time. Up until this point, we've only been looking at two values, X and Y. Well, in the real world, it's very rare that you only have two values when you're figuring out a solution. So let's move on to the next topic, multiple linear regression. Let's take a brief look at what happens when you have multiple inputs. So in multiple linear regression, we have, we'll start with the simple linear regression, where we had Y equals M plus X plus C, and we're trying to find the value of Y. Now with multiple linear regression, we have multiple variables coming in. So instead of having just X, we have X1, X2, X3. And instead of having just one slope, each variable has its own slope attached to it. As you can see here, we have M1, M2, M3, and we still just have the single coefficient. So when you're dealing with multiple linear regression, you basically take your single linear regression and you spread it out. So you have Y equals M1 times X1 plus M2 times X2, so on all the way to M to the nth, X to the nth, and then you add your coefficient on there. Implementation of linear regression. Now we get into my favorite part. Let's understand how multiple linear regression works by implementing it in Python. If you remember before, we were looking at a company and just based on its R&D, trying to figure out its profit. We're going to start looking at the expenditure of the company. We're going to go back to that. And we're going to predict its profit. But instead of predicting it just on the R&D, we're going to look at other factors like administration costs, marketing costs, and so on. And from there, we're going to see if we can figure out what the profit of that company is going to be. To start our coding, we're going to begin by importing some basic libraries. And we're going to be looking through the data before we do any kind of linear regression. We're going to take a look at the data to see what we're playing with. Then we'll go ahead and format the data to the format we need to be able to run it in the linear regression model. And then from there, we'll go ahead and solve it and just see how valid our solution is. So let's start with importing the basic libraries. Now, I'm going to be doing this in Anaconda Jupyter Notebook, a very popular IDE. I enjoy it because it's such a visual to look at and it's so easy to use. Just any IDE for Python will work just fine for this. So break out your favorite Python IDE. So here we are in our Jupyter Notebook. Let me go ahead and paste our first piece of code in there. And let's walk through what libraries we're importing. First, we're going to import Numpy as NP. And then I want you to skip one line and look at import pandas as PD. These are very common tools that you need with most of your linear regression. The Numpy, which stands for NumberPython, is usually denoted as NP, and you have to almost have that for your sklearn toolbox. So you always import that right off the beginning. Pandas, although you don't have to have it for your sklearn libraries, it does such a wonderful job of importing data, setting it up into a data frame so we can manipulate it rather easily, and it has a lot of tools also in addition to that. So we usually like to use the pandas when we can, and I'll show you what that looks like. The other three lines are for us to get a visual of this data and take a look at it. So we're going to import matplotlibary.pyplot as PLT and then Seaborn as SNS. Seaborn works with the matplot library. So you have to always import matplotlibary and then Seaborn sits on top of it. And we'll take a look at what that looks like. You could use any of your own plotting libraries you want. There's all kinds of ways to look at the data. These are just very common ones, and the Seaborn is so easy to use that it just looks beautiful. It's a nice representation that you can actually take and show somebody. And the final line is the ampersand matplot library inline. That is only because I'm doing an inline IDE. My interface in the Anaconda Jupyter notebook requires I put that in there, or you're not going to see the graph when it comes up. Let's go ahead and run this. It's not going to be that interesting because we're just setting up variables. In fact, it's not going to do anything that we can see, but it is importing these different libraries and setup. The next step is load the data set and extract independent and dependent variables. Now, here in the slide, you'll see companies equals pd.read CSV, and it has a long line there with the file at the end, 1000 companies.csv. You're going to have to change this to fit whatever setup you have. And the file itself, you can request. Just go down to the commentary below this video and put a note in there, and Simplilearn will try to get in contact with you and supply you with that file so you can try this coding yourself. So we're going to add this code in here, and we're going to see that I have companies equals pd.reader_csv, and I've changed this path to match my computer, c:/Simplilearn/1000_companies.csv. And then below there, we're going to set the x equals to companies under the I location, and because this is companies is a PD data set, I can use this nice notation that says take every row. That's what the first colon is, comma, except for the last column. That's what the second part is, where we have a :1, and we want the values set into there. So X is no longer a data set, a pandas data set, but we can easily extract the data from our pandas data set with this notation. And then Y, we're going to set equal to the last row. Well, the question is going to be, what are we actually looking at? So let's go ahead and take a look at that. And we're going to look at the companies.head, which lists the first 5 rows of data. And I'll open up the file in just a second so you can see where that's coming from. But let's look at the data in here as far as the way the pandas sees it. When I hit run, you'll see it breaks it out into a nice setup. This is what pandas, one of the things pandas is really good about, is it looks just like an Excel spreadsheet. You have your rows, and remember, when we're programming, we always start with 0. We don't start with 1. So it shows the first 5 rows. 0, 1, 2, 3, 4, and then it shows your different columns: R&D spend, administration, marketing spend, state, profit. It even notes that the top are column names. It was never told that, but Pandas is able to recognize a lot of things that they're not the same as the data rows. Why don't we go ahead and open this file up in a CSV so you can actually see the raw data. So here I've opened it up as a text editor, and you can see at the top we have R&D spend, comma, administration, comma, marketing spend, comma, state, comma, profit, carriage return. I don't know about you, but I'd go crazy trying to read files like this. That's why we use the pandas. You could also open this up in an Excel and it would separate it since it is a comma-separated variable file. But we don't want to look at this one. We want to look at something we can read rather easily. So let's flip back and take a look at that top part, the first 5 rows. Now, as nice as this format is, where I can see the data, to me it doesn't mean a whole lot. Maybe you're an expert in business and investments and you understand what $165,349.20 compared to the administration cost of $136,897.80, so on, helps to create the profit of $192,261.83. That makes no sense to me whatsoever. No pun intended. So let's flip back here and take a look at our next set of code where we're going to graph it so we can get a better understanding of our data and what it means. So at this point, we're going to use a single line of code to get a lot of information so we can see where we're going with this. Let's go ahead and paste that into our notebook and see what we got going. And so we have the visualization, and again we're using SNS, which is pandas. As you can see, we imported the matplot library, .pyplot as PLT, which then the Seaborn uses. And we imported the Seaborn as SNS. And then that final line of code helps us show this in our inline coding. Without this, it wouldn't display, and you could display it to a file and other means. And that's the matplot library inline with the ampersand at the beginning. So here we come down to the single line of code. Seaborn is great because it actually recognizes the Panda data frame. So I can just take the companies.core for coordinates, and I can put that right into the Seaborn. And when we run this, we get this beautiful plot. And let's just take a look at what this plot means. If you look at this plot, on mine the colors are probably a little bit more purplish and blue than the original one. We have the columns and the rows. We have R&D spending, we have administration, we have marketing spending, and profit. And if you cross-index any 2 of these, since we're interested in profit, if you cross-index profit with profit, it's going to show up, if you look at the scale on the right, way up in the dark. Why? Because those are the same data. They have an exact correspondence. So R&D spending is going to be the same as R&D spending, and the same thing with administration costs. So right down the middle, you get this dark row, or dark diagonal row, that shows that this is the highest corresponding data. That's exactly the same. And as it becomes lighter, there's less connections between the data. So we can see with profit, obviously profit is the same as profit. And next, it has a very high correlation with R&D spending, which we looked at earlier. And it has a slightly less connection to marketing spending, and even less to how much money we put into the administration. So now that we have a nice look at the data, let's go ahead and dig in and create some actual useful linear regression models so that we can predict values and have a better profit. Now that we've taken a look at the visualization of this data, we're going to move on to the next step. Instead of just having a pretty picture, we need to generate some hard data, some hard values. So let's see what that looks like. We're going to set up our linear regression model in 2 steps. The first one is we need to prepare some of our data so it fits correctly. And let's go ahead and paste this code into our Jupyter notebook. And what we're bringing in is we're going to bring in the sklearn pre-processing, where we're going to import the label encoder and the one hot encoder. To use the label encoder, we're going to create a variable called label encoder and set it equal to capital L label capital E encoder. This creates a class that we can reuse for transferring the labels back and forth. Now about now you should ask, what labels are we talking about? Let's go take a look at the data we processed before and see what I'm talking about here. If you remember when we did the companies.head and we printed the top 5 rows of data, we have our columns going across. We have column 0, which is R&D spending, column 1, which is administration, column 2, which is marketing spending, and column 3 is state. And you'll see under state we have New York, California, Florida. Now, to do a linear regression model, it doesn't know how to process New York. It knows how to process a number. So the first thing we're going to do is we're going to change that New York, California, and Florida, and we're going to change those to numbers. That's what this line of code does here. X equals, and then it has the colon comma 3 in brackets. The first part, the colon comma, means that we're going to look at all the different rows. So we're going to keep them all together. But the only row we're going to edit is the 3rd row. And in there we're going to take the label coder and we're going to fit and transform the X, also the 3rd row. So we're going to take that 3rd row, we're going to set it equal to a transformation. And that transformation basically tells it that instead of having a New York, it has a 0 or a 1 or a 2. And then finally we need to do a one hot encoder, which equals one hot encoder categorical features equals 3. And then we take the X and we go ahead and do that equal to one hot encoder fit transform X to array. This final transformation preps our data for us so it's completely set the way we need it as just a row of numbers. Even though it's not in here, let's go ahead and print X and just take a look at what this data is doing. You'll see you have an array of arrays, and then each array is a row of numbers. And if I go ahead and just do row 0, you'll see I have a nice organized row of numbers that the computer now understands. We'll go ahead and take this out there because it doesn't mean a whole lot to us. It's just a row of numbers. Next, on setting up our data, we have avoiding dummy variable trap. This is very important. Why? Because the computer has automatically transformed our header into the setup, and it's automatically transformed all these different variables. So when we did the encoder created 2 columns. And what we need to do is just have the 1, because it has both the variable and the name. That's what this piece of code does here. Let's go ahead and paste this in here, and we have X equals X colon comma 1 colon. All this is doing is removing that 1 extra column we put in there when we did our one hot encoder and our label encoding. Let's go ahead and run that. And now we get to create our linear regression model. And let's see what that looks like here. And we're going to do that in 2 steps. The first step is going to be in splitting the data. Now whenever we create a predictive model of data, we always want to split it up so we have a training set and we have a testing set. That's very important. Otherwise we'd be very unethical without testing it to see how good our fit is. And then we'll go ahead and create our multiple linear regression model and train it and set it up. Let's go ahead and paste this next piece of code in here, and I'll go ahead and shrink it down a size or 2 so it all fits on one line. So from the sklearn module selection, we're going to import train, test, split. And you'll see that we've created 4 completely different variables. We have capital X train, capital X test, smaller case y train, smaller case y test. That is the standard way that they usually reference these when we're doing different models. You usually see that a capital X, and you see the train and the test and the lowercase y. What this is X is our data going in. That's our R&D spend, our administration, our marketing. And then Y, which we're training, is the answer. That's the profit. Because we want to know the profit of an unknown entity. So that's what we're going to shoot for in this tutorial. The next part, train test split, we take X and we take Y. We've already created those. X has the columns with the data in it, and Y has a column with profit in it. And then we're going to set the test size equals 0.2. That basically means 20%. So 20% of the rows are going to be tested. We're going to just put them off to the side. So since we're using 1,000 lines of data, that means that 200 of those lines we're going to hold off to the side to test for later. And then the random state equals 0. We're going to randomize which ones it picks to hold off to the side. We'll go ahead and run this. It's not overly exciting because it's setting up our variables. But the next step we actually create our linear regression model. Now that we got to the linear regression model, we get that next piece of the puzzle. Let's go ahead and put that code in there and walk through it. So here we go. We're going to paste it in there. And let's go ahead and, since this is a shorter line of code, let's zoom up there so we can get a good look. And we have from the sklearn.linear_model, we're going to import linear regression. Now, I don't know if you recall from earlier when we were doing all the math. Let's go ahead and flip back there and take a look at that. Do you remember this, where we had this long formula on the bottom and we were doing all this summization? And then we also looked at setting it up with the different lines. And then we also looked all the way down to multiple linear regression, where we're adding all those formulas together. All of that is wrapped up in this one section. So what's going on here is I'm going to create a variable called regressor. And the regressor equals the linear regression. That's a linear regression model that has all that math built in. So we don't have to have it all memorized or have to compute it individually. And then we do the regressor.fit. In this case, we do X train and Y train because we're using the training data, X being the data in and Y being profit, what we're looking at. And this does all that math for us. So within one click and one line, we've created the whole linear regression model. And we fit the data to the linear regression model. And you can see that when I run the regressor, it gives an output, linear regression. It says copy X equals true, fit intercept equals true, in jobs equal 1, normalize equals false. It's just giving you some general information on what's going on with that regressor model. Now that we've created our linear regression model, let's go ahead and use it. And if you remember, we kept a bunch of data aside. So we're going to do a yPredict variable, and we're going to put in the X test. And let's see what that looks like. Scroll up a little bit, paste that in here, predicting the test set results. So here we have yPredict equals regressor.predict X test going in, and this gives us yPredict. Now because I'm in Jupyter inline, I can just put the variable up there, and when I hit the run button, it'll print that array out. I could have just as easily done print yPredict. So if you're in a different IDE that's not an inline setup like the Jupyter Notebook, you can do it this way, print yPredict. And you'll see that for the 200 different test variables we kept off to the side, it's going to produce 200 answers. This is what it says the profit are for those 200 predictions. But let's don't stop there. Let's keep going and take a couple look. We're going to take just a short detail here and calculating the coefficients and the intercepts. This gives us a quick flash at what's going on behind the line. We're going to take a short detour here, and we're going to be calculating the coefficient and intercepts. So you can see what those look like. What's really nice about our regressor we created is it already has the coefficients for us. And we can simply just print regressor.coefficient underscore. When I run this, you'll see our coefficients here. And if we can do the regressor coefficient, we can also do the regressor intercept. And let's run that and take a look at that. This all came from the multiple regression model, and we'll flip over so you can remember where this is going into and where it's coming from. You can see the formula down here where y equals m1 times x1 plus m2 times x2 and so on plus c, the coefficient. So these variables fit right into this formula. Y equals slope 1 times column 1 variable plus slope 2 times column 2 variable all the way to the m into the n and x to the n plus c, the coefficient. Or in this case, you have minus 8.89 to the power of 2, etc., times the first column and the second column and the third column. And then our intercept is the minus 103009 point. Boy, it gets kind of complicated when you look at it. This is why we don't do this by hand anymore. This is why we have the computer to make these calculations easy to understand and calculate. Now, I told you that was a short detour, and we're coming towards the end of our script. As you remember from the beginning, I said if we're going to divide this information, we have to make sure it's a valid model, that this model works, and understand how good it works. So, calculating the R-squared value. That's what we're going to use to predict how good our prediction is. And let's take a look at what that looks like in code. And so we're going to use this from sklearn.metrics. We're going to import R2 score. That's the R-squared value. And we're looking at the error. So, in the R2 score, we take our y-test versus our y-predict. Y-test is the actual values we're testing. That was the one that was given to us so we know are true. The y-predict of those 200 values is what we think it was true. And when we go ahead and run this, we see we get a 0.9352. That's the R2 score. Now, it's not exactly a straight percentage, so it's not saying it's 93% correct. But you do want that in the upper 90s, and higher, shows that this is a very valid prediction based on the R2 score. And if R-squared value of 0.91, or 92 as we got on our model, because remember it does have a random generation involved, this proves the model is a good model, which means success! Yay! We successfully trained our model with certain predictors and estimated the profit of the companies using linear regression.
Alright, what is logistic regression? As I mentioned earlier, logistic regression is an algorithm for performing binary classification. So let's take an example and see how this works. Let's say your car has not been serviced for quite a few years, and now you want to find out if it is going to break down in the near future. So this is like a classification problem. Find out whether your car will break down or not. So how are we going to perform this classification? So here's how it looks. If we plot the information along the x and y axis. X is the number of years since the last service was performed, and y is the probability of your car breaking down. And let's say this data was collected from several car users. It's not just your car, but several car users. So that is our labeled data. So the data has been collected, and for the number of years and when the car broke down and what was the probability, and that has been plotted along x and y axis. So this provides an idea, or from this graph we can find out whether your car will break down or not. We'll see how. So first of all, the probability can go from 0 to 1. As you all are aware, probability can be between 0 and 1. And as we can imagine, it is intuitive as well. As the number of years are on the lower side, maybe 1 year, 2 years, or 3 years till after the service, the chances of your car breaking down are very limited, right? So for example, chances of your car breaking down, or the probability of your car breaking down within 2 years of your last service are 0.1 probability. Similarly, 3 years is maybe 0.3 and so on. But as the number of years increases, let's say if it was 6 or 7 years, there is almost a certainty that your car is going to break down. That is what this graph shows. So this is an example of an application of the classification algorithm. And we will see in little details how exactly logistic regression is applied here. One more thing needs to be added here is that the dependent variables outcome is discrete. So if we are talking about whether the car is going to break down or not, so that is a discrete value, the y that we are talking about, the dependent variable that we are talking about. What we are looking at is whether the car is going to break down or not, yes or no. That is what we are talking about. So here the outcome is discrete and not a continuous value. So this is how the logistic regression curve looks. Let me explain a little bit what exactly and how exactly we are going to determine the outcome rather. So for a logistic regression curve, a threshold has to be set, saying that because this is a probability calculation, remember this is a probability calculation, and the probability itself will not be 0 or 1. But based on the probability, we need to decide what the outcome should be. So there has to be a threshold. Like for example, 0.5 can be the threshold, let's say in this case. So any value of the probability below 0.5 is considered to be 0, and any value above 0.5 is considered to be 1. So an output of, let's say, 0.8 will mean that the car will break down. So that is considered as an output of 1. And let's say an output of 0.29 is considered as 0, which means that the car will not break down. So that's the way logistic regression works. Now, let's do a quick comparison between logistic regression and linear regression, because they both have the term regression in them. So it can cause confusion. So let's try to remove that confusion. So what is linear regression? Linear regression is a process, is once again an algorithm for supervised learning. However, here you're going to find a continuous value. You're going to determine a continuous value. It could be the price of a real estate property. It could be your hike, how much hike you're going to get, or it could be a stock price. These are all continuous values. These are not discrete compared to a yes or a no kind of a response that we are looking for in logistic regression. So this is one example of a linear regression. Let's say the HR team of a company tries to find out what should be the salary hike of an employee. So they collect all the details of their existing employees, their ratings and their salary hikes, what has been given, and that is the labeled information that is available, and the system learns from this. It is trained and it learns from this labeled information, so that when a new employee's information is fed based on the rating, it will determine what should be the hike. So this is a linear regression problem and a linear regression example. Now, salary is a continuous value. You can get 5,000, 5,500, 5,600. It is not discrete like a cat or a dog or an apple or a banana. These are discrete, or a yes or a no. These are discrete values, right? So this, where you're trying to find continuous values, is where we use linear regression. So let's say, just to extend on this scenario, we now want to find out whether this employee is going to get a promotion or not. So we want to find out, that is a discrete problem, right? A yes or no kind of a problem. In this case, we actually cannot use linear regression, even though we may have labeled data. So this is the labeled data. So based on the employee rating, these are the ratings, and then some people got the promotion, and this is the ratings for which people did not get promotion. That is a no. And this is the rating for which people got promotion. We just plotted the data about whether a person has got, an employee has got promotion or not. Yes, no, right? So there is nothing in between. And what is the employee's rating? Okay. And ratings can be continuous. That is not an issue. But the output is discrete in this case. Whether employee got promotion, yes, no. Okay, so if we try to plot that and we try to find a straight line, this is how it would look. And as you can see, it doesn't look very right, because it looks like there will be a lot of errors. The root mean square error, if you remember, for linear regression would be very, very high. And also the values cannot go beyond 0 or beyond 1. So the graph should probably look somewhat like this, clipped at 0 and 1. But still, the straight line doesn't look right. Therefore, instead of using a linear equation, we need to come up with something different. And therefore, the logistic regression model looks somewhat like this. So we calculate the probability, and if we plot that probability, not in the form of a straight line, but we need to use some other equation. We will see very soon what that equation is. Then it is a gradual process, right? So you see here, people with some of these ratings are not getting any promotions, and then slowly at certain rating they get promotion. So that is a gradual process. And this is how the math behind logistic regression looks. So we are trying to find the odds for a particular event happening. And this is the formula for finding the odds. So the probability of an event happening divided by the probability of the event not happening. So P, if it is the probability of the event happening, probability of the person getting a promotion, and divided by the probability of the person not getting a promotion, that is 1 minus P. So this is how you measure the odds. Now, the values of the odds range from 0 to infinity. So when this probability is 0, then the value of the odds is equal to 0, and when the probability becomes 1, then the value of the odds is 1 by 0, that will be infinity. But the probability itself remains between 0 and 1. Now, this is how an equation of a straight line looks. So y is equal to beta 0 plus beta 1x, where beta 0 is the y-intercept and beta 1 is the slope of the line. If we take the odds equation and take a log of both sides, then this would look somewhat like this. And the term logistic is actually derived from the fact that we are doing this. We take a log of px by 1 minus px. This is an extension of the calculation of odds that we have seen, right? And that is equal to beta 0 plus beta 1x, which is the equation of the straight line. And now from here, if you want to find out the value of px, you will see we can take the exponential on both sides, and then if we solve that equation, we will get the equation of px like this. Px is equal to 1 by 1 plus e to the power of minus beta 0 plus beta 1x. And recall, this is nothing but the equation of the line, which is equal to y. Y is equal to beta 0 plus beta 1x. So this is the equation also known as the sigmoid function, and this is the equation of the logistic regression algorithm. Alright, and if this is plotted, this is how the sigmoid curve is obtained. So let's compare linear and logistic regression, how they are different from each other. Let's go back. So linear regression is solved or used to solve regression problems, and logistic regression is used to solve classification problems. So both are called regression, but linear regression is used for solving regression problems where we predict continuous values, whereas logistic regression is used for solving classification problems where we have to predict discrete values. The response variables in case of linear regression are continuous in nature, whereas here they are categorical or discrete in nature. And linear regression helps to estimate the dependent variable when there is a change in the independent variable, whereas here in case of logistic regression, it helps to calculate the probability or the possibility of a particular event happening. And linear regression, as the name suggests, is a straight line. That's why it's called linear regression, whereas logistic regression is a sigmoid function, and the shape of the curve is S. It's an S-shaped curve. This is another example of application of logistic regression in weather prediction, whether it's going to rain or not rain. Now keep in mind, both are used in weather prediction. If we want to find the discrete values, like whether it's going to rain or not rain, that is a classification problem. We use logistic regression. But if we want to determine what is going to be the temperature tomorrow, then we use linear regression. So just keep in mind that in weather prediction we actually use both. But these are some examples of logistic regression. So we want to find out whether it's going to be rain or not, whether it's going to be sunny or not, whether it's going to snow or not. These are all logistic regression examples. A few more examples. Classification of objects. This is again another example of logistic regression. Now here, of course, one distinction is that these are multi-class classification. So logistic regression is not used in its original form, but it is used in a slightly different form. So we say whether it is a dog or not a dog. I hope you understand. So instead of saying is it a dog or a cat or an elephant, we convert this into saying, so because we need to keep it to binary classification. So we say, is it a dog or not a dog? Is it a cat or not a cat? So that's the way logistic regression can be used for classifying objects. Otherwise, there are other techniques which can be used for performing multi-class classification. In healthcare, logistic regression is used to find the survival rate of a patient. So they take multiple parameters like trauma score and age and so on and so forth, and they try to predict the rate of survival. Alright, now finally let's take an example and see how we can apply logistic regression to predict the number that is shown in the image. So this is actually a live demo. I will take you into Jupyter Notebook and show the code. But before that, let me take you through a couple of slides to explain what we are trying to do. So let's say you have an 8x8 image and the image has a number 1, 2, 3, 4, and you need to train your model to predict what this number is. So how do we do this? So the first thing is, obviously, in any machine learning process, you train your model. So in this case, we are using logistic regression. So, and then we provide a training set to train the model, and then we test how accurate our model is with the test data, which means that, like any machine learning process, we split our initial data into two parts, training set and test set. With the training set, we train our model, and then with the test set, we test the model till we get good accuracy, and then we use it for inference, right? So that is typical methodology of training, testing, and then deploying of machine learning models. So let's take a look at the code and see what we are doing. So I'll not go line by line, but just take you through some of the blocks. So first thing we do is import all the libraries, and then we basically take a look at the images and see what is the total number of images. We can display using matplotlib some of the images or a sample of these images, and then we split the data into training and test, as I mentioned earlier, and we can do some exploratory analysis, and then we build our model. We train our model with the training set, and then we test it with our test set and find out how accurate our model is using the confusion matrix, the heat map, and use heat map for visualizing this. And I will show you in the code what exactly is the confusion matrix and how it can be used for finding the accuracy. In our example, we get an accuracy of about 0.94, which is pretty good, or 94%, which is pretty good. All right, so what is a confusion matrix? This is an example of a confusion matrix, and this is used for identifying the accuracy of a classification model, or like a logistic regression model. So the most important part in a confusion matrix is that, first of all, this, as you can see, this is a matrix, and the size of the matrix depends on how many outputs we are expecting. So the most important part here is that the model will be most accurate when we have the maximum numbers in its diagonal. Like in this case, that's why it has almost 94%, because the diagonals should have the maximum numbers, and the others other than diagonals, the cells other than the diagonals, should have very few numbers. So here that's what is happening. So there is a 2 here, there is a 1 here, but most of them are along the diagonal. What does this mean? This means that the number that has been fed is 0, and the number that has been detected is also 0. So the predicted value and the actual value are the same. So along the diagonals, that is true, which means that let's take this diagonal, right? If the maximum number is here, that means that like here in this case it is 34, which means that 34 of the images that have been fed, or rather actually there are 2 misclassifications in there. So 36 images have been fed which have number 4, and out of which 34 have been predicted correctly as number 4, and 1 has been predicted as number 8, and another one has been predicted as number 9. So these are 2 misclassifications. Okay, so that is the meaning of saying that the maximum number should be in the diagonal. So if you have all of them, so for an ideal model which has, let's say, 100% accuracy, everything will be only in the diagonal. There will be no numbers other than 0 in all other cells. So that is like a 100% accurate model. Okay, so that's gist of how to use this matrix, how to use this confusion matrix. I know the name is a little funny sounding, confusion matrix, but actually it is not very confusing. It's very straightforward. So you are just plotting what has been predicted and what is the labeled information, or what is the actual data. That's also known as the ground truth sometimes. Okay, these are some fancy terms that are used. So predicted label and the actual label, that's all it is. Okay, yeah, so we are showing a little bit more information here. So 38 have been predicted, and here you will see that all of them have been predicted correctly. There have been 38 zeros, and the predicted value and the actual value is exactly the same. Whereas in this case, right, it has, there are, I think, 37 plus 5, yeah, 42 have been fed the images. 42 images are of digit 3, and the accuracy is only 37 of them have been accurately predicted. 3 of them have been predicted as number 7 and 2 of them have been predicted as number 8, and so on and so forth. Okay. Alright, so with that, let's go into Jupyter Notebook and see how the code looks.
So this is the code in Jupyter Notebook for logistic regression. In this particular demo, what we are going to do is train our model to recognize digits, which are the images which have digits from let's say 0 to 5 or 0 to 9, and then we will see how well it is trained and whether it is able to predict these numbers correctly or not. So let's get started. So the first part is, as usual, we are importing some libraries that are required, and then the last line in this block is to load the digits. So let's go ahead and run this code. Then here we will visualize the shape of these digits. So we can see here, if we take a look, this is how the shape is, 1797 by 64. These are like 8 by 8 images. So that's what is reflected in this shape. Now from here onwards, we are basically once again importing some of the libraries that are required, like Numpy and Matplot, and we will take a look at some of the sample images that we have loaded. So this one, for example, creates a figure, and then we go ahead and take a few sample images to see how they look. So let me run this code, and so that it becomes easy to understand. So these are about 5 images, sample images that we are looking at. 0, 1, 2, 3, 4. So this is how the images, this is how the data is. Okay, and based on this, we will actually train our logistic regression model, and then we will test it and see how well it is able to recognize. So the way it works is the pixel information. So as you can see here, this is an 8 by 8 pixel kind of a image, and each pixel, whether it is activated or not activated, that is the information available for each pixel. Now based on the pattern of this activation and non-activation of the various pixels, this will be identified as a 0, for example, right? Similarly, as you can see, so overall each of these numbers actually has a different pattern of the pixel activation, and that's pretty much that our model needs to learn for which number, what is the pattern of the activation of the pixels, right? So that is what we are going to train our model. Okay, so the first thing we need to do is to split our data into training and test data set. Right? So whenever we perform any training, we split the data into training and test, so that the training data set is used to train the system. So we pass this probably multiple times, and then we test it with the test data set, and the split is usually in the form of and there are various ways in which you can split this data. It is up to the individual preferences. In our case here, we are splitting in the form of 23 and 77. So when we say test size as 0.23, that means 23% of that entire data is used for testing, and the remaining 77% is used for training. So there is a readily available function which is called train test split. So we don't have to write any special code for the splitting. It will automatically split the data based on the proportion that we give here, which is test size. So we just give the test size, automatically training size will be determined, and we pass the data that we want to split, and the results will be stored in x_train and y_train for the training data set. And what is x_train? These are the features, right, which is like the independent variable, and y_train is the label, right? So in this case, what happens is we have the input value, which is, or the features value, which is in x_train, and since this is labeled data, for each of them, each of the observations, we already have the label information saying whether this digit is a 0 or a 1 or a 2. So that this is what will be used for comparison to find out whether the system is able to recognize it correctly or there is an error. For each observation, it will compare with this. right? So this is the label. So the same way, x underscore train, y underscore train is for the training data set, x underscore test, y underscore test is for the test data set. Okay, so let me go ahead and execute this code as well, and then we can go and check quickly what is how many entries are there and in each of these. So x underscore train, the shape is 1383 by 64, and y underscore train has 1383 because there is nothing like the second part is not required here. And then x underscore test shape we see is 414. So actually there are 414 observations in test and 1383 observations in train. So that's basically what these 4 lines of code are saying. Okay, then we import the logistic regression library, and which is a part of scikit-learn. So we don't have to implement the logistic regression process itself. We just call these the function, and let me go ahead and execute that. So that we have the logistic regression library imported. Now we create an instance of logistic regression, right? So logistic regr is an instance of logistic regression, and then we use that for training our model. So let me first execute this code. So these 2 lines. So the first line basically creates an instance of logistic regression model, and then the second line is where we are passing our data, the training data set. Right, this is our the predictors, and this is our target. We are passing this data set to train our model. All right. So once we do this, in this case the data is not large, but by and large the training is what takes usually a lot of time. So we spend in machine learning activities, in machine learning projects, we spend a lot of time for the training part of it. Okay, so here the data set is relatively small, so it was pretty quick. So all right, so now our model has been trained using the training data set, and we want to see how accurate this is. So what we'll do is we will test it out in probably phases. So let me first try out how well this is working for one image. Okay, I will just try it out with one image, the first entry in my test data set, and see whether it is correctly predicting or not. So and in order to test it, so for training purpose we use the fit method. There is a method called fit which is for training the model. And once the training is done, if you want to test for a particular value, new input, you use the predict method. Okay, so let's run the predict method, and we pass this particular image, and we see that the shape is or the prediction is 4. So let's try a few more. Let me see for the next 10. Seems to be fine. So let me just go ahead and test the entire data set. Okay, that's basically what we will do. So now we want to find out how accurately this has performed. So we use the score method to find what is the percentage of accuracy, and we see here that it has performed up to 94% accurate. Okay, so that's on this part. Now what we can also do is we can also see this accuracy using what is known as a confusion matrix. So let us go ahead and try that as well, so that we can also visualize how well this model has done. So let me execute this piece of code, which will basically import some of the libraries that are required, and we basically create a confusion matrix, an instance of confusion matrix, by running confusion matrix and passing these values. So this confusion underscore matrix method takes 2 parameters. One is the y underscore test, and the other is the prediction. So what is the y underscore test? These are the labeled values which we already know for the test data set, and predictions are what the system has predicted for the test data set. Okay, so this is known to us, and this is what the system has, the model has generated. So we kind of create the confusion matrix and we will print it, and this is how the confusion matrix looks. As the name suggests, it is a matrix, and the key point out here is that the accuracy of the model is determined by how many numbers are there in the diagonal. The more the numbers in the diagonal, the better the accuracy is. Okay, and first of all, the total sum of all the numbers in this whole matrix is equal to the number of observations in the test data set. That is the first thing, right? So if you add up all these numbers, that will be equal to the number of observations in the test data set. And then out of that, the maximum number of them should be in the diagonal. That means the accuracy is pretty good. If the numbers in the diagonal are less and in all other places there are a lot of numbers, which means the accuracy is very low. The diagonal indicates a correct prediction. This means that the actual value is same as the predicted value. Here again, actual value is same as the predicted value, and so on, right? So the moment you see a number here, that means the actual value is something and the predicted value is something else, right? Similarly here, the actual value is something and the predicted value is something else. So that is basically how we read the confusion matrix. Now, how do we find the accuracy? You can actually add up the total values in the diagonal. So it's like 38 plus 44 plus 43 and so on, and divide that by the total number of test observations. That will give you the percentage accuracy using a confusion matrix. Now let us visualize this confusion matrix in a slightly more sophisticated way using a heat map. So we will create a heat map with we'll add some colors as well. It's like a more visually more appealing. So that's the whole idea. So let me run this piece of code, and this is how the heat map looks. And as you can see here, the diagonals again are all the values are here, most of the values. So which means this seems to be reasonably accurate. And yeah, basically the accuracy score is 94%. This is calculated, as I mentioned, by adding all these numbers divided by the total test values, or the total number of observations in test data set. Okay, so this is the confusion matrix for logistic regression. Alright, so now that we have seen the confusion matrix, let's take a quick sample and see how well the system has classified, and we will take a few examples of the data. So if we see here, we picked up randomly a few of them. So this is number 4, which is the actual value, and also the predicted value. Both are 4. This is an image of 0. So the predicted value is also 0. Actual value is of course 0. Then this is the image of 9. So this has also been predicted correctly, 9, and actual value is 9. And this is the image of 1. And again, this has been predicted correctly as like the actual value. Okay, so this was a quick demo of logistic regression, how to use logistic regression to identify images.
What is a decision tree? Let's go through a very simple example before we dig in deep. Decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. Let's start with a simple question. How to identify a random vegetable from a shopping bag? So we have this group of vegetables in here, and we can start off by asking a simple question, is it red? And if it's not, then it's going to be the purple fruit to the left, probably an eggplant. If it's true, it's going to be one of the red fruits. Is the diameter greater than 2? If false, it's going to be what looks to be a red chili. And if it's true, it's going to be a bell pepper from the capsicum family. So it's a capsicum. Problems that decision tree can solve. So let's look at the two different categories the decision tree can be used on. It can be used on the classification, the true, false, yes, no, and it can be used on regression, where we figure out what the next value is in a series of numbers or a group of data. In classification, the classification tree will determine a set of logical if-then conditions to classify problems. For example, discriminating between 3 types of flowers based on certain features. In regression, a regression tree is used when the target variable is numerical or continuous in nature. We fit the regression model to the target variable using each of the independent variables. Each split is made based on the sum of squared error. Before we dig deeper into the mechanics of the decision tree, let's take a look at the advantages of using a decision tree, and we'll also take a glimpse at the disadvantages. The first thing you'll notice is that it's simple to understand, interpret, and visualize. It really shines here because you can see exactly what's going on in a decision tree. Little effort is required for data preparation, so you don't have to do special scaling. There's a lot of things you don't have to worry about when using a decision tree. It can handle both numerical and categorical data. data, as we discovered earlier, and nonlinear parameters don't affect its performance. So even if the data doesn't fit an easy curved graph, you can still use it to create an effective decision or prediction. If we're going to look at the advantages of a decision tree, we also need to understand the disadvantages of a decision tree. The first disadvantage is overfitting. Overfitting occurs when the algorithm captures noise in the data. That means you're solving for one specific instance instead of a general solution for all the data. High variance. The model can get unstable due to small variation in data. Low bias tree. A highly complicated decision tree tends to have a low bias, which makes it difficult for the model to work with new data. Decision tree important terms. Before we dive in further, we need to look at some basic terms. We need to have some definitions to go with our decision tree and the different parts we're going to be using. We'll start with entropy. Entropy is a measure of randomness or unpredictability in the data set. For example, we have a group of animals. In this picture, there's 4 different kinds of animals, and this data set is considered to have a high entropy. You really can't pick out what kind of animal it is based on looking at just the 4 animals as a big clump of entities. So as we start splitting it into subgroups, we come up with our second definition, which is information gain. Information gain. It is a measure of decrease in entropy after the data set is split. So in this case, based on the color yellow, we've split one group of animals on one side as true and those who aren't yellow as false. As we continue down the yellow side, we split based on the height, true or false equals 10, and on the other side, height is less than 10, true or false. And as you see, as we split it, the entropy continues to be less and less and less, and so our information gain is simply the entropy E1 from the top and how it's changed to E2 in the bottom. And we'll look at the deeper math, although you really don't need to know a huge amount of math when you actually do the programming in Python, because it'll do it for you. But we'll look on the actual math at how they compute entropy. Finally, we went over the different parts of our tree, and they call the leaf node. Leaf node carries the classification or the decision, so it's the final end at the bottom. The decision node has 2 or more branches. This is where we're breaking the group up into different parts. And finally, you have the root node. The topmost decision node is known as the root node. How does a decision tree work? Wonder what kind of animals I'll get in the jungle today? Maybe you're the hunter with a gun, or if you're more into photography, you're a photographer with a camera. So let's look at this group of animals and let's try to classify different types of animals based on their features using a decision tree. So the problem statement is to classify the different types of animals based on their features using a decision tree. The data set is looking quite messy and the entropy is high in this case. So let's look at a training set or a training data set. And we're looking at color, we're looking at height, and then we have our different animals. We have our elephants, our giraffes, our monkeys, and our tigers. And they're of different colors and shapes. Let's see what that looks like and how do we split the data. We have to frame the conditions that split the data in such a way that the information gain is the highest. Note, gain is a measure of decrease in entropy after splitting. So the formula for entropy is the sum, that's what this symbol looks like, that looks like kind of like a funky E, of K, where I equals 1 to K. K would represent the number of the different animals in there, where value, or P, value of I, would be the percentage of that animal, times the log base 2 of the same, the percentage of that animal. Let's try to calculate the entropy for the current data set and take a look at what that looks like. And don't be afraid of the math. You don't really have to memorize this math. Just be aware that it's there and this is what's going on in the background. And so we have 3 giraffes, 2 tigers, 1 monkey, 2 elephants, a total of 8 animals gathered. And if we plug that into the formula, we get an entropy that equals 3 over 8. So we have 3 giraffes, a total of 8, times the log. Usually they use base 2 on the log. So log base 2 of 3 over 8 plus, in this case let's say it's the elephants, 2 over 8, 2 elephants over a total of 8 times log base 2, 2 over 8, plus 1 monkey over a total of 8, log base 2, 1 over 8, and plus 2 over 8 of the tigers, log base 2 over 8. And if we plug that into our computer or calculator, I obviously can't do logs in my head, we get an entropy equal to 0.571. The program will actually calculate the entropy of the data set similarly after every split to calculate the gain. Now we're not going to go through each set one at a time to see what those numbers are. We just want you to be aware that this is a formula or the mathematics behind it. Gain can be calculated by finding the difference of the subsequent entropy values after a split. Now we will try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking that the gain we get out of them. The condition that gives us the highest gain will be used to make the first split. Can you guess what that first split will be just by looking at this image? As a human, it's probably pretty easy to split it. Let's see if you're right. If you guessed the color yellow, you're correct. Let's say the condition that gives us the maximum gain is yellow. So we will split the data based on the color yellow. If it's true, that group of animals goes to the left. If it's false, it goes to the right. The entropy after the splitting has decreased considerably. However, we still need some splitting at both the branches to attain an entropy value equal to 0. So we decide to split both the nodes using height as a condition. Since every branch now contains single label type, we can say that entropy in this case has reached the least value. And here you see we have the giraffes, the tigers, the monkey, and the elephants all separated into their own groups. This tree can now predict all the classes of animals present in the dataset with 100% accuracy. That was easy. Use case, loan repayment prediction. Let's get into my favorite part and open up some Python and see what the programming code and the scripting looks like. In here, we're going to want to do a prediction. And we start with this individual here who's requesting to find out how good his customers are going to be, whether they're going to repay their loan or not for his bank. And from that, we want to generate a problem statement to predict if a customer will repay loan amount or not, and then we're going to be using the decision tree algorithm in Python. Let's see what that looks like, and let's dive into the code. In our first few steps of implementation, we're going to start by importing the necessary packages that we need from Python, and we're going to load up our data and take a look at what the data looks like. So the first thing I need something to edit my Python and run it in. So let's flip on over, and here I'm using the Anaconda Jupyter Notebook. Now you can use any Python IDE you like to run it in, but I find the Jupyter Notebook's really nice for doing things on the fly. And let's go ahead and just paste that code in the beginning. And before we start, let's talk a little bit about what we're bringing in. And then we're going to do a couple things in here where I have to make a couple changes as we go through this first part of the import. The first thing we bring in is Numpy as NP. That's very standard. When we're dealing with mathematics, especially with very complicated machine learning tools, you almost always see the Numpy come in for your numbers. It's called NumPy. It has your mathematics in there. In this case, we actually could take it out, but generally you'll need it for most of your different things you work with. And then we're going to use pandas as PD. That's also a standard. The pandas is a data frame setup, and you can liken this to taking your basic data and storing it in a way that looks like an Excel spreadsheet. So as we come back to this, when you see NP or PD, those are very standard uses, you'll know that that's the pandas, and I'll show you a little bit more when we explore the data in just a minute. Then we're going to need to split the data, so I'm going to bring in our train, test, and split, and this is coming from the sklearn package cross-validation. In just a minute, we're going to change that, and we'll go over that too. And then there's also the sk.tree import decision tree classifier. That's the actual tool we're using. Remember I told you don't be afraid of the mathematics, it's going to be done for you. Well, the decision tree classifier has all that mathematics in there for you, so you don't have to figure it back out again. And then we have sklearn.metrics for accuracy score. We need to score our setup. That's the whole reason we're splitting it between the training and testing data. And finally, we still need the sklearn import tree. And that's just the basic tree function is needed for the decision tree classifier. And finally, we're going to load our data down here. And I'm going to run this, and we're going to get two things on here. One, we're going to get an error, and two, we're going to get a warning. Let's see what that looks like. So the first thing we had is we have an error. Why is this error here? Well, it's looking at this and it says, I need to read a file. And when this was written, the person who wrote it, this is their path where they stored the file. So let's go ahead and fix that. And I'm going to put in here my file path. I'm just going to call it full file name. And you'll see it's on my C drive, and there's this very lengthy setup on here where I stored the data2.csv file. Don't worry too much about the full path because on your computer it'll be different. The data.2csv file was generated by Simplilearn. If you want a copy of that, you can comment down below and request it here in the YouTube. And then if I'm going to give it a name, full file name, I'm going to go ahead and change it here to full file name. So let's go ahead and run it now and see what happens. And we get a warning. When you're coding, understanding these different warnings and these different errors that come up is probably the hardest lesson to learn. So let's just go ahead and take a look at this and use this as an opportunity to understand what's going on here. If you read the warning, it says the cross-validation is depreciated. So it's a warning on it's being removed. And it's going to be moved in favor of the model selection. So if we go up here, we have sklearn.cross-validation. And if you research this and go to the sklearn site, you'll find out that you can actually just swap it right in there with model selection. And so when I come in here and I run it again, that removes a warning. What they've done is they've had two different developers develop it in two different branches. And then they decided to keep one of those and eventually get rid of the other one. That's all that is, and very easy and quick to fix. Before we go any further, I went ahead and opened up the data from this file. Remember the data file we just loaded on here, the data_2.csv. Let's talk a little bit more about that and see what that looks like both as a text file, because it's a comma-separated variable file, and in a spreadsheet. This is what it looks like as a basic text file. You can see at the top they've created a header, and it's got 5 columns, and each column has data in it. And let me flip this over because we're also going to look at this in an actual spreadsheet so you can see what that looks like. And here I've opened it up in the OpenOffice Calc, which is pretty much the same as Excel, and zoomed in, and you can see we've got our columns and our rows of data. A little easier to read in here. We have a result, yes, yes, no. We have initial payment, last payment, credit score, house number. If we scroll way down, we'll see that this occupies 1,001 lines of code, or lines of data, with the first one being a column and then 1,000 lines of data. Now, as a programmer, if you're looking at a small amount of data, I usually start by pulling it up in different sources so I can see what I'm working with. But in larger data, you won't have that option. It'll just be too large. So you need to either bring in a small amount that you can look at it like we're doing right now, or we can start looking at it through the Python code. So let's go ahead and move on and take the next couple steps to explore the data using Python. Let's go ahead and see what it looks like in Python to print the length and the shape of the data. So let's start by printing the length of the database. We can use a simple len function from Python. And when I run this, you'll see that it's 1,000 long. And that's what we expected. There's 1,000 lines of data in there if you subtract the column head. And this is one of the nice things when we did the balanced data from the Panda read CSV. You'll see that the header is row 0, so it automatically removes a row and then shows the data separate. It does a good job sorting that data out for us. And then we can use a different function, and let's take a look at that. And again, we're going to utilize the tools in Panda. And since the balance underscore data was loaded as a Panda data frame, we can do a shape on it. And let's go ahead and run the shape and see what that looks like. What's nice about this shape is not only does it give me the length of the data, we have 1,000 lines, it also tells me there's 5 columns. So when we were looking at the data, we had 5 columns of data. And then let's take one more step to explore the data using Python. And now that we've taken a look at the length and the shape, let's go ahead and use the pandas module for head, another beautiful thing in the data set that we can utilize. So let's put that on our sheet here, and we have print data set and balance data.head. And this is a pandas print statement of its own. So it has its own print feature in there. And then we went ahead and gave a label for our print job here of data set, just a simple print statement. And when we run that, and let's just take a closer look at that. Let me zoom in here. There we go. Pandas does such a wonderful job of making this a very clean, readable data set. So you can look at the data, you can look at the column headers, you can have it, when you put it as the head, it prints the first 5 lines of the data. And we always start with 0. So we have 5 lines, we have 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5. That's a standard scripting and programming set, is you want to start with the 0 position. And that is what the data head does. It pulls the first 5 rows of data, puts it in a nice format that you can look at and view. Very powerful tool to view the data. So instead of having to flip and open up an Excel spreadsheet or open Office Calc or trying to look at a Word doc where it's all scrunched together and hard to read, you can now get a nice open view of what you're working with. We're working with a shape of 1,000 long, 5 wide, so we have 5 columns, and we do the full data head. You can actually see what this data looks like. The initial payment, last payment, credit scores, house number. So let's take this, now that we've explored the data, and let's start digging into the decision tree. So in our next step, we're going to train and build our data tree. And to do that, we need to first separate the data out. We're going to separate it into 2 groups so that we have something to actually train the data with, and then we have some data on the side to test it, to see how good our model is. Remember, with any of the machine learning, you always want to have some kind of test set to weigh it against, so you know how good your model is when you distribute it. Let's go ahead and break this code down and look at it in pieces. So first we have our X and Y. Where do X and Y come from? Well, X is going to be our data, and Y is going to be the answer or the target. You can look at it as source and target. In this case, we're using X and Y to denote the data in and the data that we're actually trying to guess what the answer is going to be. And so to separate it, we can simply put in X equals the balance of the data.values. The first brackets means that we're going to select all the lines in the database. So it's all the data. And the second one says we're only going to look at columns 1 through 5. Remember, we always start with 0. 0 is a yes or no, and that's whether the loan went default or not. So we want to start with 1. If we go back up here, that's the initial payment, and it goes all the way through the house number. Well, if we want to look at 1 through 5, we can do the same thing for Y, which is the answers, and we're going to set that just equal to the 0 row. So it's just the 0 row, and then it's all rows going in there. So now we've divided this into 2 different data sets. One of them with the data going in, and one with the answers. Next, we need to split the data. And here you'll see that we have it split into 4 different parts. The first one is your X training, your X test, your Y train, your Y test. Simply put, we have X going in, where we're going to train it, and we have to know the answer to train it with. And then we have X test, where we're going to test that data. And we have to know in the end what the Y was supposed to be. And that's where this train test split comes in, that we loaded earlier in the modules. This does it all for us. And you can see they set the test size equal to 0.3, so that's roughly 30% will be used in the test. And then we use a random state, so it's completely random which rows it takes out of there. And then finally we get to actually build our decision tree. And they've called it here CLF_entropy. That's the actual decision tree, or decision tree classifier. And in here they've added a couple variables, which we'll explore in just a minute. And then finally, we need to fit the data to that. So we take our CLF entropy that we created, and we fit the X train, and since we know the answers for X train or the Y train, we go ahead and put those in. And let's go ahead and run this. And what most of these sklearn modules do is when you set up the variable, in this case when we set the CLF entropy equal to decision tree classifier, it automatically prints out what's in that decision tree. There's a lot of variables you can play with in here, and it's quite beyond the scope of this tutorial to go through all of these and how they work. But we're working on entropy, that's one of the options. We've added that it's completely a random state of 100, so 100%. And we have a max depth of 3. Now the max depth, if you remember above when we were doing the different graphs of animals, means it's only going to go down 3 layers before it stops. And then we have minimal samples of leaves as 5. So it's going to have at least 5 leaves at the end. So I'll have at least 3 splits, or I'll have no more than 3 layers, and at least 5 end leaves with the final result at the bottom. Now that we've created our decision tree classifier, not only created it but trained it, let's go ahead and apply it and see what that looks like. So let's go ahead and make a prediction and see what that looks like. We're going to paste our predict code in here. And before we run it, let's just take a quick look at what's it's doing here. We have a variable yPredict that we're going to do. And we're going to use our variable CLF entropy that we created. And then you'll see .predict. And it's very common in the sklearn modules that their different tools have the predict when you're actually running a prediction. In this case, we're going to put our X-test data in here. Now, if you delivered this for use, an actual commercial use, and distributed it, this would be the new loans you're putting in here to guess whether the person's going to be pay them back or not. In this case, though, we need to test out the data and just see how good our sample is, how good of our tree does at predicting the loan payments. And finally, since Anaconda Jupyter Notebook works as a command line for Python, we can simply put the yPredictEn to print it. I could just as easily have put the print and put brackets around yPredictEn to print it out. We'll go ahead and do that. It doesn't matter which way you do it. And you'll see right here that it runs a prediction. This is roughly 300 in here. Remember, it's 30% of 1,000, so you should have about 300 answers in here. And this tells you which each one of those lines of our test went in there, and this is what our yPredict came out. So let's move on to the next step, where we're going to take this data and try to figure out just how good a model we have. So here we go. Since sklearn does all the heavy lifting for you and all the math, we have a simple line of code to let us know what the accuracy is. And let's go ahead and go through that and see what that means and what that looks like. Let's go ahead and paste this in, and let me zoom in a little bit. There we go. So you have a nice full picture. And we'll see here we're just going to do a print accuracy is, and then we do the accuracy score. And this was something we imported earlier, if you remember at the very beginning. Let me just scroll up there real quick so you can see where that's coming from. That's coming from here, down here, from sklearn.metrics import accuracy score. And you could probably run a script, make your own script to do this very easily. How accurate is it? How many out of 300 do we get right? And so we put in our y-test, that's the one we ran the predict on. And then we put in our yPredictEn, that's the answers we got. And we're just going to multiply that by 100, because this is just going to give us an answer as a decimal. And we want to see it as a percentage. And let's run that and see what it looks like. And if you see here, we got an accuracy of 93.66667. So when we look at the number of loans and we look at how good our model fit, we can tell people it has about a 93.6 fitting to it. So just a quick recap on that. We now have accuracy set up on here. And so we have created a model that uses the decision tree algorithm to predict whether a customer will repay the loan or not. The accuracy of the model is about 94.6%. The bank can now use this model to decide whether it should approve the loan request from a particular customer or not. And so this information is really powerful. We may not be able to, as individuals, understand all these numbers because they have thousands of numbers that come in. But you can see that this is a smart decision for the bank to use a tool like this to help them to predict how good their profit's going to be off of the loan balances and how many are going to default or not. So why random forest? It's always important to understand why we use this tool over the other ones. What are the benefits here? And so with the random forest, the first one is there's no overfitting. If you use of multiple trees, reduce the risk of overfitting. Training time is less. Overfitting means that we have fit the data so close to what we have as our sample that we pick up on all the weird parts. And instead of predicting the overall data, you're predicting the weird stuff, which you don't want. High accuracy. Runs efficiently on large database. For large data, it produces highly accurate predictions. In today's world of big data, this is really important. And this is probably where it really shines. This is where random forest really comes in. It estimates missing data. Data in today's world is very messy. So when you have a random forest, it can maintain the accuracy when a large proportion of the data is missing. What that means is if you have data that comes in from 5 or 6 different areas, and maybe they took one set of statistics in one area, and they took a slightly different set of statistics in the other, so they have some of the same shared data, but one is missing like the number of children in the house if you're doing something over demographics, and the other one is missing the size of the house. It will look at both of those separately and build 2 different trees, and then it can do a very good job of guessing which one fits better, even though it's missing that data. Let us dig deep into the theory of exactly how it works. And let's look at what is random forest. Random forest, or random decision forest, is a method that operates by constructing multiple decision trees. The decision of the majority of the trees is chosen by the random forest as the final decision. And we have some nice graphics here. We have a decision tree, and they actually use a real tree to denote the decision tree, which I love. And given a random, some kind of picture of a fruit, this decision tree decides that the output is it's an apple. And we have a decision tree 2, where we have that picture of the fruit goes in, and this one decides that it's a lemon. And the decision 3 tree gets another image, and it decides it's an apple. And then this all comes together in what they call the random forest. And this random forest then looks at it and says, okay, I got 2 votes for apple, 1 vote for lemon. The majority is apples, so the final decision is apples. To understand how the random forest works, we first need to dig a little deeper and take a look at the random forest and the actual decision tree and how it builds that decision tree. In looking closer at how the individual decision trees work, we'll go ahead and continue to use the fruit example, since we're talking about trees and forests. A decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So in here we have a bowl of fruit, and if you look at that, it looks like they switched from lemons to oranges. We have oranges, cherries, and apples. And the first decision of the decision tree might be, is the diameter greater than or equal to 3? And if it says false, it knows that they're cherries because everything else is bigger than that. So all the cherries fall into that decision. So we have all that data we're training. We can look at that. We know that that's what's going to come up. Is the color orange? Well, it goes, orange or red? Well, if it's true, then it comes out as the orange. And if it's false, that leaves apples. So in this example, it sorts out the fruit in the bowl, or the images of the fruit. A decision tree, these are very important terms to know because these are very central to understanding the decision tree and when working with them. The first is entropy. Everything on the decision tree and how it makes those decisions is based on entropy. Entropy is a measure of randomness or unpredictability in the data set. Then they also have information gain, the leaf node, the decision node, and the root node. We'll cover these other 4 terms as we go down the tree. But let's start with entropy. So starting with entropy, we have here a high amount of randomness. What that means is that whatever's coming out of this decision, if it was going to guess based on this data, it wouldn't be able to tell you whether it's a lemon or an apple. It would just say it's a fruit. So the first thing we want to do is we want to split this apart. And we take the initial data set, and we're going to create a data set 1 and a data set 2. We just split it in 2. And if you look at these new data sets, after splitting them, the entropy of each of those sets is much less. So for the first one, whatever comes in there, it's going to sort that data and it's going to say, okay, if this data goes this direction, it's probably an apple. And if it goes into the other direction, it's probably a lemon. So that brings us up to information gain. It is the measure of decrease in the entropy after the data set is split. What that means in here is that we've gone from one set, which has a very high entropy, to 2 lower sets of entropy. And we've added in the values of E1 for the first one and E2 for the second 2, which are much lower. And so that information gain is increased greatly in this example. And so you can find that the information gain simply equals decision E1 minus E2. As we're going down our list of definitions, we'll look at the leaf node. And the leaf node carries the classification or the decision. So we look down here to the leaf node. We finally get to our set 1 or our set 2. When it comes down there and it says, okay, this object's gone into set 1, if it's gone into set 1, it's going to be split by some means, and we'll either end up with apples on the leaf node or a lemon on the leaf node, and on the right it'll either be an apple or lemons. Those leaf nodes, or those final decisions or classifications, that's the definition of leaf node in here. If we're going to have a final leaf where we make the decision, we should have a name for the nodes above it, and they call those decision nodes. A decision node has 2 or more branches. And you can see here where we have the 5 apples and 1 lemon, and in the other case the 5 lemons and 1 apple. They have to make a choice of which tree it goes down based on some kind of measurement or information given to the tree. And that brings us to our last definition. The root node, the topmost decision node, is known as the root node. And this is where you have all of your data and you have your first decision it has to make, or the first split in information. So far, we've looked at a very general image with the fruit being split. Let's look and see exactly what that means to split the data and how do we make those decisions on there. Let's go in there and find out, how does a decision tree work? So let's try to understand this, and let's use a simple example, and we'll stay with the fruit. We have a bowl of fruit, and so let's create a problem statement, and the problem is we want to classify the different types of fruits in the bowl based on different features. The data set in the bowl is looking quite messy, and the entropy is high in this case. So if this bowl was our decision maker, it wouldn't know what choice to make. It has so many choices. Which one do you pick? Apple, grapes, or lemons? And so we look in here. We're going to start with a training set. So this is our data that we're training our data with. And we have a number of options here. We have the color, and under the color we have red, yellow, purple. We have a diameter, 331, 331, and we have a label, apple, lemon, grapes, apple, lemon, grapes. And how do we split the data? We have to frame the conditions to split the data in such a way that the information gain is the highest. And it's very key to note that we're looking for the best gain. We don't want to just start sorting out the smallest piece in there. We want to split it the biggest way we can. And so we measure this decrease in entropy, that's what they call it, entropy, there's our entropy, after splitting. And now we'll try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking the gain that we get out of them. The conditions that give us the highest gain will be used to make the first split. So let's take a look at these different conditions. We have color, we have diameter, and if we look underneath that, we have a couple different values. We have diameter equals 3, color equals yellow, red, diameter equals 1. And when we look at that, you'll see over here we have 1, 2, 3, 4 threes. That's a pretty high selection. So let's say the condition gives us a maximum gain of 3. So we have the most pieces fall into that range. So our first split from our decision node is we split the data based on the diameter. Is it greater than or equal to 3? If it's not, that's false, it goes into the grape bowl. And if it's true, it goes into a bowl full of lemon and apples. The entropy after splitting has decreased considerably. So now we can make two decisions. If you look at, they're very much less chaos going on there. This node has already attained an entropy value of 0, as you can see. There's only one kind of label left for this branch. So no further splitting is required for this node. However, this node on the right still requires a split to decrease the entropy further. So we split the right node further based on color. If you look at this, if I split it on color, that pretty much cuts it right down the middle. It's the only thing we have left in our choices of color and diameter too. And if the color is yellow, it's going to go to the right bowl, and if it's false, it's going to go to the left bowl. So the entropy in this case is now 0. So now we have 3 bowls with 0 entropy. There's only one type of data in each one of those bowls. So we can predict a lemon with 100% accuracy. And we can predict the apple also with 100% accuracy, along with our grapes up there. So we've looked at kind of a basic tree in our forest, but what we really want to know is, how does a random forest work as a whole? So to begin our random forest classifier, let's say we already have built 3 trees. And we're going to start with the first tree that looks like this. Just like we did in the example, this tree looks at the diameter. If it's greater than or equal to 3, it's true, otherwise it's false. So one side goes to the smaller diameter, one side goes to larger diameter. And if the color is orange, it's going to go to the right, true. We're using oranges now instead of lemons. And if it's red, it's going to go to the left, false. We build a second tree very similar, but it's split differently. Instead of the first one being split by a diameter, this one, when they created it, if you look at that first bowl, it has a lot of red objects. So it says, is the color red? Because that's going to bring our entropy down the fastest. And so, of course, if it's true, it goes to the left. If it's false, it goes to the right. And then it looks at the shape, false or true, and so on and so on. And tree 3 is the diameter equal to 1. And it came up with this because there's a lot of cherries in this bowl. So that would be the biggest split on there, is the diameter equal to 1. That's going to drop the entropy the quickest. And as you can see, it splits it into true. If it goes false, and they've added another category, does it grow in the summer? And if it's false, it goes off to the left. If it's true, it goes off to the right. Let's go ahead and bring these three trees so you can see them all in one image. So this would be three completely different trees categorizing a fruit. And let's take a fruit. Now let's try this. And this fruit, if you look at it, we've blackened it out. You can't see the color on it, so it's missing data. Remember, one of the things we talked about earlier is that a random forest works really good if you're missing data, if you're missing pieces. So this fruit has an image, but maybe the person had a black and white camera when they took the picture. And we're going to take a look at this, and it's going to have, they put the color in there, so ignore the color down there. But the diameter equals 3. We find out it grows in the summer equals yes, and the shape is a circle. And if you go to the right, you can look at what one of the decision trees did. This is the third one. Is the diameter greater than or equal to 3? Is the color orange? Well, it doesn't really know on this one, but if you look at the value, it'd say true, and you go to the right. Tree 2 classifies it as cherries. Is the color equal red? Is the shape a circle? True, it is a circle. So this would look at it and say, oh, that's a cherry. And then we go to the other classifier, and it says, is the diameter equal 1? Well, that's false. Does it grow in the summer? True. So it goes down and looks at as oranges. So how does this random forest work? The first one says it's an orange. The second one said it was a cherry. And the third one says, it's an orange. And you can guess that if you have 2 oranges and one says it's a cherry, when you add that all together, the majority of the vote says orange. So the answer is, it's classified as an orange, even though we didn't know the color and we're missing data on it. I don't know about you, but I'm getting tired of fruit. So let's switch, and I did promise you we'd start looking at a case example and get into some Python coding. Today we're going to use the case, the iris flower analysis. Ooh, this is the exciting part as we roll up our sleeves and actually look at some Python coding. Before we start the Python coding, we need to go ahead and create a problem statement. Wonder what species of iris do these flowers belong to? Let's try to predict the species of the flowers using machine learning in Python. Let's see how it can be done. So here we begin to go ahead and implement our Python code. And you'll find that the first half of our implementation is all about organizing and exploring the data coming in. Let's go ahead and take this first step, which is loading the different modules into Python, and let's go ahead and put that in our favorite editor, whatever your favorite editor is. In this case, I'm going to be using the Anaconda Jupyter Notebook, which is one of my favorites. Certainly there's Notepad++ and Eclipse and dozens of others, or just even using the Python terminal window. Any of those will work just fine to go ahead and explore this Python coding. So here we go. Let's go ahead and flip over to our Jupyter Notebook. And I've already opened up a new page for Python 3 code, and I'm just going to paste this right in there. And let's take a look and see what we're bringing into our Python. The first thing we're going to do is from the sklearn.datasets import load iris. Now this isn't the actual data, this is just the module that allows us to bring in the data, the load iris. And the iris is so popular, it's been around since 1936 when Ronald Fisher published a paper on it, and they're measuring the different parts of the flower and based on those measurements predicting what kind of flower it is. And then if we're going to do a random forest classifier, we need to go ahead and import a random forest classifier from the sklearn module. So sklearn.ensemble import random forest classifier. And then we want to bring in 2 more modules. And these are probably the most commonly used modules in Python and data science with any of the other modules that we bring in. And one is going to be pandas. So we're going to import pandas as PD. PD is the common term used for pandas. And pandas is basically creates a data format for us where when you create a pandas data frame, it looks like an Excel spreadsheet. And you'll see that in a minute when we start digging deeper into the code. Pandas is just wonderful because it plays nice with all the other modules in there. And then we have Numpy, which is our numbers Python. And the numbers Python allows us to do different mathematical sets on here. We'll see right off the bat, we're going to take our NP and we're going to go ahead and seed the randomness with it with 0. So np.random.seed is seeding that as 0. This code doesn't actually show anything. We're going to go ahead and run it because I need to make sure I have all those loaded. And then let's take a look at the next module on here. The next 6 slides, including this one, are all about exploring the data. Remember I told you half of this is about looking at the data and getting it all set. So let's go ahead and take this code right here, the script, and let's get that over into our Jupyter Notebook. And here we go. We've gone ahead and run the imports. And I'm going to paste the code down here. And let's take a look and see what's going on. The first thing we're doing is we're actually loading the iris data. And if you remember up here, we loaded the module that tells it how to get the iris data. Now we're actually assigning that data to the variable iris. And then we're going to go ahead and use the df to define data frame. And that's going to equal PD. And if you remember, that's pandas as PD. So that's our pandas. And panda data frame. And then we're looking at iris data. And columns equals iris feature names. And we're going to do the df head. And let's run this so you can understand what's going on here. The first thing you want to notice is that our df has created what looks like an Excel spreadsheet. And in this Excel spreadsheet, we have set the columns. So up on the top, you can see the 4 different columns. And then we have the data, iris.data, down below. It's a little confusing without knowing where this data is coming from. So let's look at the bigger picture. And I'm going to go print. I'm just going to change this for a moment. And we're going to print all of iris and see what that looks like. So when I print all of iris, I get this long list of information. And you can scroll through here and see all the different titles on there. What's important to notice is that first off, there's a brackets at the beginning. So this is a Python dictionary. And in a Python dictionary, you'll have a key or a label. And this label pulls up whatever information comes after it. So feature names, which we actually used over here under columns, is equal to an array of sepal length, sepal width, petal width. These are the different names they have for the 4 different columns. And if you scroll down far enough, you'll also see data down here. Oh goodness, it came up right towards the top. And data is equal to the different data we're looking at. Now there's a lot of other things in here like target. We're going to be pulling that up in a minute. And there's also the names, the target names, which is further down. And we'll show you that also in a minute. Let's go ahead and set that back to the head. And this is one of the neat features of pandas and panda data frames is when you do df.head or the panda data frame.head, it'll print the first 5 lines of the data set in there, along with the headers if you have it. In this case, we have the column headers set to iris features. And in here, you'll see that we have 0, 1, 2, 3, 4. In Python, most arrays always start at 0. So when you look at the first 5, it's going to be 0, 1, 2, 3, 4, not 1, 2, 3, 4, 5. So now we've got our iris data imported into a data frame. Let's take a look at the next piece of code in here. And so in this section here of the code, we're going to take a look at the target. And let's go ahead and get this into our notebook, this piece of code, so we can discuss it a little bit more in detail. So here we are in our Jupyter notebook. I'm going to put the code in here. And before I run it, I want to look at a couple things going on. So we have df species. And this is interesting because right here you'll see where I have df species in brackets, which is the key code for creating another column. And here we have iris.target. Now these are both in the pandas setup on here. So in pandas we can do either one. I could have just as easily done iris and then in brackets target, depending on what I'm working on. Both are acceptable. Let's go ahead and run this code and see how this changes. And what we've done is we've added the target from the iris data set as another column on the end. Now what species is, this is what we're trying to predict. So we have our data, which tells us the answer for all these different pieces. And then we've added a column with the answer. That way, when we do our final setup, we'll have the ability to program our neural network to look for this different data and know what a setosa is, or a varicolor, which we'll see in just a minute, or virginica. Those are the 3 that are in there. And now we're going to add one more column. I know, we're organizing all this data over and over again. It's kind of fun. There's a lot of ways to organize it. What's nice about putting everything onto one data frame is I can then do a printout and it shows me exactly what I'm looking at. And I'll show you where that's different, where you can alter that and do it slightly differently. But let's go ahead and put this into our script up to date now. And here we go. We're going to put that down here. And we're going to run that. And let's talk a little bit about what we're doing. Now, we're exploring data, and one of the challenges is knowing how good your model is. Did your model work? And to do this, we need to split the data up. And we split it into 2 different parts. They usually call it the training and the testing. And so in here, we're going to go ahead and put that in our database so you can see it clearly. And we've set it df. Remember, you can put brackets. This is creating another column. Is train, so we're going to use part of it for training. And this equals np, remember that stands for numpy, .random.uniform. So we're generating a random number between 0 and 1. And we're going to do it for each of the rows. That's where the length df comes from. So each row gets a generated number. And if it's less than 0.75, it's true. And if it's greater than 0.75, it's false. This means we're going to take 75% of the data, roughly, because there's a randomness involved, and we're going to use that to train it. And then the other 25% we're going to hold off to the side and use that to test it later on. So let's flip back on over and see what the next step is. So now that we've labeled our database for which is training and which is testing, let's go ahead and sort that into two different variables, train and test. And let's take this code and let's bring it into our project. And here we go, let's paste it on down here. And before I run this, let's just take a quick look at what's going on here. Is we have up above, we created, remember there's our def.head, which prints the first 5 rows. And we've added a column is train at the end. And so we're going to take that, we're going to create 2 variables. We're going to create 2 new data frames. One's called train, one's called test, 75% in train, 25% in test. And then to sort that out, we're going to do that by doing df, our main original data frame with the iris data in it. And if df is train equals true, that's going to go in the train. And if df is train equals false, it goes in the test. And so when I run this, we're going to print out the number in each one. Let's see what that looks like. And you'll see that it puts 118 in the training module, and it puts 32 in the testing module, which lets us know that there was 150 lines of data in here. So if you went and looked at the original data, you could see that there's 150 lines. And that's roughly 75% in one and 25% for us to test our model on afterward. So let's jump back to our code and see where this goes. In the next 2 steps, we want to do one more thing with our data, and that's make it readable to humans. I don't know about you, but I hate looking at zeros and ones. So let's start with the features, and let's go ahead and take those and make those readable to humans. And let's put that in our code. Let's see, here we go, paste it in. And you'll see here we've done a couple very basic things. We know that the columns in our data frame, again this is a panda thing, the df columns, and we know the first 4 of them, 0, 1, 2, 3, that'd be the first 4, are going to be the features or the titles of those columns. And so when I run this, you'll see down here that it creates an index, SEPA length, SEPA width, petal length, and petal width. And this should be familiar because if you look up here, here's our column titles going across, and here's the first 4. One thing I want you to notice here is that when you're in a command line, whether it's Jupyter Notebook or you're running command line in the terminal window, if you just put the name of it, it'll print it out. This is the same as doing print features. And the shorthand is you just put features in here. If you're actually writing a code and saving the script and running it by remote, you really need to put the print in there. But for this, when I run it, you'll see it gives me the same thing. But for this, we want to go ahead and we'll just leave it as features because it doesn't really matter. And this is one of the fun thing about Jupyter Notebooks is I'm just building the code as we go. And then we need to go ahead and create the labels for the other part. So let's take a look and see what that. For our final step in prepping our data, before we actually start running the training and the testing, is we're going to go ahead and convert the species on here into something the computer understands. So let's put this code into our script and see where that takes us. Alright, here we go. We've set y equal to pd.factorize train species of 0. So let's break this down just a little bit. We have our pandas right here, pd. Factorize. What is factorize doing? I'm going to come back to that in just a second. Let's look at what train species is and why we're looking at the group 0 on there. And let's go up here, and here is our species. Remember this that we created this whole column here for species? And then it has Setosa, 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 and if you scroll down enough, you'd also see Virginica and Varicolor. we need to convert that into something the computer understands, zeros and ones. So the trained species of 0, because this is in the format of an array of arrays, so you have to have the 0 on the end. And then species is just that column. Factorize goes in there and looks at the fact that there's only 3 of them. So when I run this, you'll see that y generates an array that's equal to, in this case it's the training set, and it's zeros, ones, and twos representing the 3 different kinds of flowers we have. So now we have something the computer understands, and we have a nice table that we can read and understand. And now, finally, we get to actually start doing the predicting. So here we go. We have 2 lines of code. Oh my goodness, that was a lot of work to get to 2 lines of code. But there is a lot in these 2 lines of code. So let's take a look and see what's going on here and put this into our full script that we're running. And let's paste this in here. And let's take a look and see what this is. We're creating a variable CLF, and we're going to set this equal to the random forest classifier. And we're passing 2 variables in here, and there's a lot of variables you can play with. As far as these 2 are concerned, they're very standard. In jobs, all that does is to prioritize it. Not something to really worry about. Usually when you're doing this on your own computer, you do in jobs equals 2. If you're working in a larger or big data and you need to prioritize it differently, this is what that number does, is it changes your priorities and how it's going to run across the system and things like that. And then the random state is just how it starts. 0 is fine for here. But let's go ahead and run this. We also have clf.fit train features, y. And before we run it, let's talk about this a little bit more. clf.fit. So we're training it. We are actually creating our random forest classifier right here. This is the code that does everything. And we're going to take our training set. Remember, we kept our test off to the side. And we're going to take our training set with the features, and then we're going to go ahead and put that in, and here's our target, the y. So the y is 0, 1, and 2 that we just created, and the features is the actual data going in that we put into the training set. And let's go ahead and run that. And this is kind of an interesting thing because it printed out the random forest classifier and everything around it. And so when you're running this in your terminal window or in a script like this, this automatically treats this just like when we were up here and I typed in y and it printed out y instead of print y. This does the same thing. It treats this as a variable and prints it out. But if you're actually running your code, that wouldn't be the case. And what is printed out is it shows us all the different variables we can change. And if we go down here, you can actually see in jobs equals 2. You can see the random state equals 0. Those are the 2 that we sent in there. You would really have to dig deep to find out all these different meanings of all these different settings on here. Some of them are self-explanatory if you kind of think about it a little bit, like max features is auto. So all the features that we're putting in there is just going to automatically take all 4 of them. Whatever we send it, it'll take. Some of them might have so many features because you're processing words. There might be like 1.4 million features in there because you're doing legal documents, and that's how many different words are in there. At that point, you probably want to limit the maximum features that you're going to process. And leaf nodes, that's the end nodes. Remember we had the fruit, and we're talking about the leaf nodes. Like I said, there's a lot in this. We're looking at a lot of stuff here. So you might have, in this case, there's probably only 3 leaf nodes, maybe 4. You might have thousands of leaf nodes, at which point you do need to put a cap on that and say, okay, you can only go so far, and then we're going to use all of our resources on processing this. And that really is what most of these are about, is limiting the process and making sure we don't overwhelm a system. And there's some other settings in here. Again, we're not going to go over all of them. Warm start equals false. Warm start is if you're programming it one piece at a time externally. Since we're not going to continually to train this particular learning tree. And again, like I said, there's a lot of things in here that you'll want to look up more detail from the sklearn. And if you're digging in deep and running a major project on here. For today though, all we need to do is fit or train our features and our target y. So now we have our training model. What's next? If we're going to create a model, we now need to test it. Remember, we set aside the test feature, test group, 25% of the data. So let's go ahead and take this code and let's put it into our script and see what that looks like. Okay, here we go. And we're going to run this. And it's going to come out with a bunch of zeros, ones, and twos, which represents the three type of flowers, the setosa, the virginica, and the versicolor. And what we're putting into our predict is the test features. And I always kind of like to know what it is I am looking at. So real quick, we're going to do test features. And remember, features is an array of sepal length, sepal width, petal length, petal width. So when we put it in this way, it actually loads all these different columns that we loaded into features. So if we did just features, let me just do features in here so you can see what features looks like. This is just playing with pandas data frames. You'll see that it's an index. So when you put an index in like this into test features, into test, it then takes those columns and creates a panda data frames from those columns. And in this case, we're going to go ahead and put those into our predict. So we're going to put each one of these lines of data, the 5.0, 3.4, 1.5, 0.2, and we're going to put those in and we're going to predict what our new forest classifier is going to come up with. And this is what it predicts. It predicts 0, 0, 0, 1, 2, 1, 1, 2, 2, 2. And again, this is the flower type, setosa, virginica, and versicolor. So now that we've taken our test features, let's explore that. Let's see exactly what that data means to us. So the first thing we can do with our predicts is we can actually generate a different prediction model. When I say different, we're going to view it differently. It's not that the data itself is different. So let's take this next piece of code and put it into our script. So we're pasting it in here, and you'll see that we're doing predict, and we've added underscore proba for probability. So there's our clf.predict probability. So we're running it just like we ran it up here, but this time with this we're going to get a slightly different result. And we're only going to look at the first 10. So you'll see down here, instead of looking at all of them, which was 27, you'll see right down here that this generates a much larger field on the probability. And let's take a look and see what that looks like and what that means. So when we do the predict underscore proba for probability, it generates 3 numbers. So we had 3 leaf nodes at the end. And if you remember from all the theory we did, this is the predictors. The first one is predicting a 1 for setosa. It predicts a 0 for virginica, and it predicts a 0 for versicolor, and so on and so on and so on. And let's, you know what, I'm going to change this just a little bit. Let's look at 10 to 20, just because we can. And we start to get in a little different of data, and you'll see right down here, it gets to this one, this line right here. And this line has 0, 0.5, 0.5. And so if we're going to vote, and we have 2 equal votes, it's going to go with the first one. So it says setosa gets 0 votes, virginica gets 0.5 votes, versicolor gets 0.5 votes, but let's just go with the virginica since these 2 are equal, and so on down the list. You can see how they vary on here. So now we've looked at both how to do a basic predict of the features, and we've looked at the predict probability. Let's see what's next on here. So now we want to go ahead and start mapping names for the plants. We want to attach names so that it makes a little more sense for us. And that's what we're going to do in these next 2 steps. We're going to start by setting up our predictions and mapping them to the names. So let's see what that looks like. And let's go ahead and paste that code in here and run it. And this goes along with the next piece of code. So we'll skip through this quickly and then come back to it a little bit. So here's iris.targetNames. And if you remember correctly, this was the names that we've been talking about this whole time, the setosa, virginica, versicolor. And then we're going to go ahead and do the prediction again. We could have just set a variable equal to this instead of rerunning it each time. But we're going to go ahead and run it again, clf.predict test features. Remember that returns the 0s, the 1s, and the 2s. And then we're going to set that equal to predictions. So this time we're actually putting it in a variable. And when I run this, it distributes, and it comes out as an array, and the array is setosa, 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 setosa. We're only looking at the first 5. We could actually let's do the first 25, just so we can see a little bit more on there. And you'll see that it starts mapping it to all the different flower types, the versicolor and the virginica in there. And let's see how this goes with the next one. So let's take a look at the top part of our species in here, and we'll take this code and put it in our script. And let's put that down here and paste it. There we go. And we'll go ahead and run it. And let's talk about both these sections of code here and how they go together. The first one is our predictions. And I went ahead and did predictions through 25. Let's just do 5. And so we have setosa, 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 setosa. That's what we're predicting from our test model. And then we come down here and we look at test species. I remember I could have just done test.species.head. And you'll see it says setosa, 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 setosa. And they match. So the first one is what our forest is doing. And the second one is what the actual data is. Now, we need to combine these so that we can understand what that means. We need to know how good our forest is, how good it is at predicting the features. So that's where we come up to the next step, which is lots of fun. We're going to use a single line of code to combine our predictions and our actuals so we have a nice chart to look at. And let's go ahead and put that in our script in our Jupyter notebook here. Let's see, let's go ahead and paste that in, and then because I'm on the Jupyter notebook, I can do a Control minus so you can see the whole line there. There we go, resize it. And let's take a look and see what's going on here. We're going to create in pandas, remember PD stands for pandas, and we're doing a crosstab. This function takes 2 sets of data and creates a chart out of them. So when I run it, you'll get a nice chart down here, and we have the predicted species. So across the top you'll see the Setosa versicolor virginica and the actual species, Setosa versicolor virginica. And so the way to read this chart, and let's go ahead and take a look on how to read this chart here. When you read this chart, you have Setosa where they meet, you have versicolor where they meet, and you have virginica where they meet. And they're meeting where the actual and the predicted agree. So this is the number of accurate predictions. So in this case it equals 30. If you add 13 plus 5 plus 12, you get 30. And then we notice here where it says virginica, but it was supposed to be versicolor. This is inaccurate. So now we have two inaccurate predictions and 30 accurate predictions. So we'll say that the model accuracy is 93. That's just 30 divided by 32. And if we multiply it by 100, we can say that it is 93% accurate. So we have a 93% accuracy with our model. I did want to add one more quick thing in here on our scripting before we wrap it up. So let's flip back on over to my script. In here, we're going to take this line of code from up above. I don't know if you remember it, but predicts equals the iris.target_names. So we're going to map it to the names. And we're going to run the prediction, and we read it on test features. But we're not just testing it, we want to actually deploy it. So at this point, I would go ahead and change this. And this is an array of arrays. This is really important when you're running these to know that. So you need the double brackets. And I could actually create data. Maybe let's just do 2 flowers. So maybe I'm processing more data coming in. And we'll put 2 flowers in here. And then I actually want to see what the answer is. So let's go ahead and type in preds and print that out. And when I run this, you'll see that I've now predicted 2 flowers that maybe I measured in my front yard as versicolor and versicolor. Not surprising since I put the same data in for each one. This would be the actual end product going out to be used on data that you don't know the answer for. Last week, my son and I visited a fruit shop. Dad, is that an apple or a strawberry? So the question comes up, what fruit did I just pick up from the fruit stand? After a couple of seconds, you could figure out that it was a strawberry. So let's take this model a step further, and why not build a model which can predict an unknown data? And in this, we're going to be looking at some sweet strawberries or crispy apples. We want it to be able to label those two and decide what the fruit is. And we do that by having data already put in. So we already have a bunch of strawberries, we know are strawberries, and they're already labeled as such. We already have a bunch of apples, we know are apples and are labeled as such. Then once we train our model, that model then can be given the new data, and the new data is this image. In this case you can see a question mark on it, and it comes through and goes, it's a strawberry. In this case we're using the support vector machine model. SVM is a supervised learning method that looks at data and sorts it into one of 2 categories. And in this case, we're sorting the strawberry into the strawberry side. At this point, you should be asking the question, how does the prediction work? Before we dig into an example with numbers, let's apply this to our fruit scenario. We have our support vector machine. We've taken it and we've taken a labeled sample of data, strawberries and apples, and we draw on a line down the middle between the two groups. This split now allows us to take new data, in this case an apple and a strawberry, and place them in the appropriate group based on which side of the line they fall in. And that way we can predict the unknown. As colorful and tasty as the fruit example is, let's take a look at another example with some numbers involved, and we can take a closer look at how the math works. In this example, we're going to be classifying men and women, and we're going to start with a set of people with a different height and a different weight. And to make this work, we'll have to have a sample data set of female, where we have their height and weight, 174, 65, 174, 88, and so on. And we'll need a sample data set of the male. They have a height 179, 90, 180 to 80, and so on. Let's go ahead and put this on a graph so we have a nice visual. So you can see here we have two groups based on the height versus the weight. And on the left side, we're going to have the women. On the right side, we're going to have the men. Now, if we're going to create a classifier, let's add a new data point and figure out if it's male or female. So before we can do that, we need to split our data first. We can split our data by choosing any of these lines. In this case, we draw in two lines through the data in the middle that separates the men from the women. But to predict the gender of a new data point, we should split the data in the best possible way. And we say the best possible way because this line has a maximum space that separates the two classes. Here you can see there's a clear split between the two different classes, and in this one there's not so much a clear split. This doesn't have the maximum space that separates the two. That is why this line best splits the data. We don't want to just do this by eyeballing it. And before we go further, we need to add some technical terms to this. We can also say that the distance between the points in the line should be as far as possible. In technical terms, we can say the distance between the support vector and the hyperplane should be as far as possible. And this is where the support vectors are the extreme points in the data set. And if you look at this data set, they have circled 2 points which seem to be right on the outskirts of the women and one on the outskirts of the men. And hyperplane has a maximum distance to the support vectors of any class. Now you'll see the line down the middle, and we call this the hyperplane because when you're dealing with multiple dimensions, it's really not just a line but a plane of intersections. And you can see here where the support vectors have been drawn in dashed lines. The math behind this is very simple. We take d plus, the shortest distance to the closest positive point, which would be on the men's side, and d minus is the shortest distance to the closest negative point, which is on the women's side. The sum of d plus and d minus is called the distance margin, or the distance between the two support vectors that are shown in the dashed lines. And then, by finding the largest distance margin, we can get the optimal hyperplane. Once we've created an optimal hyperplane, we can easily see which side the new data fits in. And based on the hyperplane, we can say the new data point belongs to the male gender. Hopefully that's clear how that works on a visual level. As a data scientist, you should also be asking what happens if the hyperplane is not optimal. If we select a hyperplane having low margin, then there is a high chance of misclassification. This particular SVM model, the one we discussed so far, is also called or referred to as the LSVM. So far so clear, but a question should be coming up. We have our sample data set, but instead of looking like this, what if it looked like this, where we have two sets of data, but one of them occurs in the middle of another set? You can see here where we have the blue and the yellow, and then blue again on the other side of our data line. In this data set, we can't use a hyperplane. So when you see data like this, it's necessary to move away from a 1D view of the data to a two-dimensional view of the data. And for the transformation, we use what's called a kernel function. The kernel function will take the 1D input and transfer it to a two-dimensional output. As you can see in this picture here, the 1D when transferred to a two-dimensional makes it very easy to draw a line between the two data sets. What if we make it even more complicated? How do we perform an SVM for this type of data set? Here you can see we have a two-dimensional data set where the data is in the middle surrounded by the green data on the outside. In this case, we're going to segregate the two classes. We have our sample data set, and if you draw a line through, it's obviously not an optimal hyperplane in there. So to do that, we need to transfer the 2D to a 3D array. And when you translate it into a 3-dimensional array using the kernel, you can see where you can place a hyperplane right through it and easily split the data. Before we start looking at a programming example and dive into the script, let's look at the advantage of the support vector machine. We'll start with high-dimensional input space, or sometimes referred to as the curse of dimensionality. We looked at earlier 1 dimension, 2 dimension, 3 dimension. When you get to 1,000 dimensions, a lot of problems start occurring with most algorithms that have to be adjusted for. The SVM automatically does that in high dimensional space. One high dimensional space that we work on is sparse document vectors. This is where we tokenize the words in documents so we can run our machine learning algorithms over them. I've seen ones get as high as 2.4 million different tokens. That's a lot of vectors to look at. And finally, we have regularization parameter. The regularization parameter, or lambda, is a parameter that helps figure out whether we're going to have a bias or overfitting of the data. Whether it's going to be overfitted to a very specific instance or it's going to be biased to a high or low value. With the SVM, it naturally avoids the overfitting and bias problems that we see in many other algorithms. These 3 advantages of the support vector machine make it a very powerful tool to add to your repertoire of machine learning tools. Now, we did promise you a use case study where we're actually going to dive into some Python programming. And so we're going to go into a problem statement and start off with the zoo. So in the zoo example, we have family members going to the zoo, and we have the young child going, "Dad, is that a group of crocodiles or alligators?" Well, that's hard to differentiate. And zoos are a great place to start looking at science and understanding how things work, especially as a young child. And so we can see the parents sitting here thinking, well, what is the difference between a crocodile and an alligator? Well, one, crocodiles are larger in size, alligators are smaller in size. Snout width, the crocodiles have a narrow snout, and alligators have a wider snout. And of course, in the modern day and age, the father's sitting here thinking, how can I turn this into a lesson for my son? And he goes, let a support vector machine segregate the 2 groups. I don't know if my dad ever told me that, but that would be funny. Now, in this example, we're not going to use actual measurements and data. We're just using that for imagery. And that's very common in a lot of machine learning algorithms and setting them up. But let's roll up our sleeves, and we'll talk about that more in just a moment as we break into our Python script. So here we arrive in our actual coding. And I'm going to move this into a Python editor in just a moment. But let's talk a little bit about what we're going to cover. First, we're going to cover in the code the setup, how to actually create our SVM. And you're going to find that there's only 2 lines of code that actually create it, and the rest of it is done so quick and fast that it's all here in the first page. And we'll show you what that looks like as far as our data, because we're going to create some data. I talked about creating data just a minute ago. And so we'll get into the creating data here, and you'll see this nice correction of our 2 blobs, and we'll go through that in just a second. And then the second part is we're going to take this and we're going to bump it up a notch. We're going to show you what it looks like behind the scenes. But let's start with actually creating our setup. I like to use the Anaconda Jupyter Notebook because it's very easy to use, but you can use any of your favorite Python editors or setups and go in there. But let's go ahead and switch over there and see what that looks like. So here we are in the Anaconda Python Notebook, or Anaconda Jupyter Notebook with Python. We're using Python 3. I believe this is 3.5, but it should be work in any of your 3x versions. And you'd have to look at the sklearn and make sure if you're using a 2x version or an earlier version. And let's go ahead and put our code in there. And one of the things I like about the Jupyter Notebook is I can go up to View, and I'm going to go ahead and toggle the line numbers on to make it a little bit easier to talk about. And we can even increase the size because this is edited in this case I'm using Google Chrome Explorer, and that's how it opens up for the editor. Although like I said, any editor will work. Now the first step is going to be our imports. And we're going to import 4 different parts. The first 2 I want you to look at are line 1 and line 2 are Numpy as NP and matplotlibary.pyplot as PLT. Now, these are very standardized imports when you're doing work. The first one is the numbers Python. We need that because part of the platform we're using uses that for the Numpy array. And I'll talk about that in a minute so you can understand why we want to use a Numpy array versus the standard Python array. And normally it's pretty standard setup to use NP for Numpy. The matplot library is how we're going to view our data. So this has, you do need the NP for the sklearn module, but the matplot library is purely for our use for visualization. And so you really don't need that for the SVM, but we're going to put it there so you have a nice visual aid and we can show you what it looks like. That's really important at the end when you finish everything, so you have a nice display for everybody to look at. And then finally, I'm gonna jump one ahead to line number 4. That's the sklearn.datasets.samples generator import make blobs. And I told you that we were going to make up data. And this is a tool that's in the sklearn to make up data. I personally don't want to go to the zoo, get in trouble for jumping over the fence, and probably get eaten by the crocodiles or alligators as I work on measuring their snouts and width and length. Instead, we're just going to make up some data. And that's what that make blobs is. It's a wonderful tool if you're ready to test your setup and you're not sure about what data you're going to put in there. You can create this blob and it makes it real easy to use. And finally, we have our actual SVM, the sklearn import SVM on line 3. So that covers all our imports. We're going to create, remember I used the make blobs to create data. And we're going to create a capital X and a lowercase y equals make blobs in samples equals 40. So we're going to make 40 lines of data. It's going to have 2 centers with a random state equals 20. So each group's going to have 20 different pieces of data in it. And the way that looks is that we'll have under X an XY plane. So I'll have 2 numbers under X, and Y will be 0 or 1. That's the 2 different centers. So we have yes or no, in this case alligator or crocodile. That's what that represents. And then I told you that the actual sklearn or the SVM is in 2 lines of code. And we see it right here with CLF equals svm.svc kernel equals linear, and I set C equal to 1. Although in this example, since we are not regularizing the data, because we want it to be very clear and easy to see, I went ahead, you can set it to 1,000 a lot of times when you're not doing that. But for this thing, linear, because it's a very simple linear example, we only have the 2 dimensions, and it'll be a nice linear hyperplane. It'll be a nice linear line instead of a full plane. So we're not dealing with a huge amount of data. And then all we have to do is do clf.fit x, y. And that's it. CLF has been created, and then we're going to go ahead and display it. And I'm going to talk about this display here in just a second, but let me go ahead and run this code. And this is what we've done, is we've created 2 blobs. You'll see the blue on the side and then kind of an orangish on the other side. That's our 2 sets of data. One represents crocodiles and one represents alligators. And then we have our measurements. In this case, we have like the width and length of the snout. And I did say I was going to come up here and talk just a little bit about our plot. And you'll see PLT, that's what we imported. We're going to do a scatter plot. That means we're just putting dots on there. And then look at this notation. I have the capital X, and then in brackets I have a colon, comma, 0. That's from Numpy. If you did that in a regular array, you'll get an error in a Python array. You have to have that in a Numpy array. It turns out that our make blobs returns a Numpy array. And this notation is great because what it means is the first part is the colon. It means we're going to do all the rows. That's all the data in our blob we created under capital X. And then the second part has a comma 0. We're only going to take the first value. And then if you notice, we do the same thing, but we're going to take the second value. Remember, we always start with 0 and then 1. So we have column 0 and column 1. And you can look at this as our XY plots. The first one is the X plot, and the second one is the Y plot. So the first one is on the bottom, 0, 2, 4, 6, 8, and 10. And then the second one, X of the 1, is the 4, 5, 6, 7, 8, 9, 10 going up the left-hand side. S equals 30 is just the size of the dot, so we can see them instead of real tiny dots. And then CMap equals plt.cm.paired. And you'll also see the C equals Y. That's the color. We're using 2 colors, 0, 1, and that's why we get the nice blue and the 2 different colors for the alligator and the crocodile. Now you can see here that we did this, the actual fit was done in 2 lines of code. A lot of times there'll be a third line where we regularize the data. We set it between like -1 and 1, and we reshape it. But for this, it's not necessary, and it's also kind of nice because you can actually see what's going on. And then if we wanted to actually run a prediction. Let's take a look and see what that looks like. And to predict some new data, and we'll show this again as we get towards the end of digging in deep, you can simply assign your new data. In this case, I am giving it a width and length 3, 4 and a width and length 5, 6. And note that I put the data as a set of brackets, and then I have the brackets inside. And the reason I do that is because when we're looking at data, it's designed to process a large amount of data coming in. We don't want to just process 1 line at a time. And so in this case, I'm processing 2 lines and then I'm just going to print, and you'll see clf.predict new data. So the clf and the .predict part is going to give us an answer, and let's see what that looks like. And you'll see 0, 1. So predicted the first one, the 3, 4, is going to be on the one side, and the 5, 6 is going to be on the other side. So one came out as an alligator, and one came out as a crocodile. Now that's a pretty short explanation for the setup, but really we want to dig in and see what's going on behind the scenes. And let's see what that looks like. So the next step is to dig in deep and find out what's going on behind the scenes. And also put that in a nice pretty graph. We're going to spend more work on this than we did actually generating the original model. And you'll see here that we go through a few steps, and I'll move this over to our editor in just a second. We come in, we create our original data. It's exactly identical to the first part, and I'll explain why we redid that and show you how not to redo that. And then we're going to go in there and add in those lines. We're going to see what those lines look like and how to set those up. And finally, we're going to plot all that on here and show it, and you'll get a nice graph with what we saw earlier when we were going through the theory behind this, where it shows the support vectors and the hyperplane. And those are done where you can see the support vectors as the dashed lines and the solid line, which is the hyperplane. Let's get that into our Jupyter notebook. Before I scroll down to a new line, I want you to notice line 13. It has plot show. And we're going to talk about that here in just a second, but let's scroll down to a new line down here, and I'm going to paste that code in. And you'll see that the plot show has moved down below. Let's scroll up a little bit. And if you look at the top here of our new section, 1, 2, 3, and 4 is the same code we had before. And let's go back up here and take a look at that. We're going to fit the values on our SVM, and then we're going to plot scatter it, and then we're going to do a plot show. So you should be asking, why are we redoing the same code? Well, when you do the plot show, that blanks out what's in the plot. So once I've done this plot show, I have to reload that data. Now we could do this simply by removing it up here, rerunning it, and then coming down here, and then we wouldn't have to rerun these first 4 lines of code. Now in this, it doesn't matter too much, and you'll see the plot show is down here and then removed right there on line 5. I'll go ahead and just delete that out of there because we don't want to blank out our screen. We want to move on to the next setup. So we can go ahead and just skip the first 4 lines because we did that before. And let's take a look at the AX equals plt.gca. Now right now, we're actually spending a lot of time just graphing. That's all we're doing here. Okay, so this is how we display a nice graph with our results and our data. AX is very standard used variable when you're talking about PLT, and it's just setting it to that axis, the last axis in the PLT. It can get very confusing if you're working with many different layers of data on the same graph, and this makes it very easy to reference the AX. So this reference is looking at the PLT that we created and we already mapped out our 2 blobs on. And then we want to know the limits. So we want to know how big the graph is. We can find out the x limit and the y limit simply with the get x limit and get y limit commands, which is part of our matplot library. And then we're going to create a grid. And you'll see down here we've set the variable xx equal to np.linespace, x limit 0, x limit 1, 30. And we've done the same thing for the y space. And then we're going to go in here and we create a mesh grid. And this is a Numpy command. So we're back to our numbers Python. Let's go through what these Numpy commands mean with the line space and the mesh grid. We've taken xx, small s xx equals np line space, and we have our x limit 0 and our x limit 1, and we're going to create 30 points on it. And we're going to do the same thing for the y-axis. Now, this has nothing to do with our evaluation. It's all we're doing is we're creating a grid of data. And so we're creating a set of points between 0 and the x limit. We're creating 30 points, and the same thing with the y. And then the mesh grid loops those all together, so it forms a nice grid. So if we were going to do this, say, between the limit 0 and 10 and do 10 points, we would have a 0, 0, 1, 1, 0, 1, 0, 2, 0, 3, 0, 4 to 10, and so on. You can just imagine a point at each corner of one of those boxes. And the mesh grid combines them all, so we take the YY and the XX we created and creates the full grid. And we've set that grid into the YY coordinates and the XX coordinates. Now remember, we're working with Numpy and Python. we like to separate those. We like to have, instead of it being x comma 1, x comma y, and then x2 comma y2, and in the next set of data it would be a column of x's and a column of y's. And that's what we have here, is we have a column of y's, and we put it as a capital YY, and a column of x's, capital XX, with all those different points being listed. And finally we get down to the Numpy VStack. Just as we created those in the mesh grid, we're now going to put them all into one array, XY array. Now that we've created the stack of data points, we're going to do something interesting here. We're going to create a value z, and the z equals the CLF. That's our support vector machine we created and we've already trained. And we have a dot decision function, and we're going to put the XY in there. So here we have all this data. We're going to put that XY in there, that data, and we're going to reshape it. And you'll see that we have the XX.shape in here. This literally takes the XX, resets it up connected to the Y, and the Z value lets us know whether it is the left-hand side. It's going to generate 3 different values, the Z value does. And it'll tell us whether that data is a support vector to the left, the hyperplane in the middle, or the support vector to the right. So it generates 3 different values for each of those points. And those points have been reshaped so that they're right on a line, on those 3 different lines. So we've set all of our data up. We've labeled it to 3 different areas, and we've reshaped it, and we've just taken 30 points in each direction. If you do the math, you have 30 times 30, so that's 900 points of data, and we separated it between the 3 lines and reshaped it to fit those 3 lines. We can then go back to our matplot library, where we've created the AX, and we're going to create a contour. And you'll see here where we have contour, capital XX, capital YY. These have been reshaped to fit those lines. Z is the labels. So now we have the 3 different points with the labels in there, and we can set the colors equals K. And I told you we had 3 different labels, but we have 3 levels of data. The alpha just makes it kind of see-through, so it's only 0.5 of the value in there. So when we graph it, the data will show up from behind it, wherever the lines go. And finally, the line styles. This is where we set the 2 support vectors to be dash dash lines, and then a single one is just a straight line. That's what all of that setup does. And then finally, we take our ax.scatter. We're going to go ahead and plot the support vectors, but we've programmed it in there so that they look nice, like the dash dash line and the dash line on that grid. And you can see here, when we do the CLF dot support vectors, we are looking at column 0 and column 1. And then again, we have the S equals 100, so we're going to make them larger. And the line width equals 1, face colors equals none. Let's take a look and see what that looks like when we show it. And you can see when we get down to our end result, it creates a really nice graph. We have our 2 support vectors in dashed lines, and they have the near data. So you can see those 2 points, or in this case the 4 points, where those lines nicely cleave the data. And then you have your hyperplane down the middle, which is as far from the 2 different points as possible, creating the maximum distance. So you can see that we have our nice output for the size of the body and the width of the snout, and we've easily separated the 2 groups of crocodile and alligator. Congratulations! You've done it. We've made it. Of course, these are pretend data for our crocodiles and alligators, but this hands-on example will help you to encounter any support vector machine projects in the future. And you can see how easy they are to set up and look at in depth. Today we're going to cover the K nearest neighbors, referred to as KNN. And KNN is really a fundamental place to start in the machine learning. It's the basis of a lot of other things, and just the logic behind it is easy to understand and incorporated in other forms of machine learning. So today, what's in it for you? Why do we need KNN? What is KNN? How do we choose the factor K? When do we use KNN? How does KNN algorithm work? And then we'll dive into my favorite part, the use case. Predict whether a person will have diabetes or not. That is a very common and popular used data set as far as testing out models and learning how to use the different models in machine learning. By now, we all know machine learning models make predictions by learning from the past data available. So we have our input values, our machine learning model builds on those inputs of what we already know, and then we use that to create a predicted output. Is that a dog? Little kid looking over there and watching the black cat cross their path. No, dear, you can differentiate between a cat and a dog based on their characteristics. Cats. Cats have sharp claws, uses to climb, smaller length of ears, meows and purrs, doesn't love to play around. Dogs, they have dull claws, bigger length of ears, barks, loves to run around. You usually don't see a cat running around people, although I do have a cat that does that, where dogs do. And we can look at these, we can say, we can evaluate the sharpness of the claws, how sharp are their claws, and we can evaluate the length of the ears, and we can usually sort out cats from dogs based on even those two characteristics. Now tell me if it is a cat or a dog. An odd question, usually little kids know cats and dogs by now, unless they live in a place where there's not many cats or dogs. So if we look at the sharpness of the claws, the length of the ears, and we can see that the cat has smaller ears and sharper claws than the other animals. Its features are more like cats. It must be a cat. Sharp claws, length of ears, and it goes in the cat group. Because KNN is based on feature similarity, we can do classification using KNN classifier. So we have our input value, the picture of the black cat. It goes into our trained model, and it predicts that this is a cat coming out. So what is KNN? What is the KNN algorithm? K nearest neighbors is what that stands for. It's one of the simplest supervised machine learning algorithms, mostly used for classification. So we want to know, is this a dog or it's not a dog? Is it a cat or not a cat? It classifies a data point based on how its neighbors are classified. KNN stores all available cases and classifies new cases based on a similarity measure. And here we've gone from cats and dogs right into wine, another favorite of mine. KNN stores all available cases and classifies new cases based on a similarity measure. And here you see we have a measurement of sulfur dioxide versus the chloride level, and then the different wines they've tested and where they fall on that graph based on how much sulfur dioxide and how much chloride. K in KNN is a perimeter that refers to the number of nearest neighbors to include in the majority of the voting process. And so if we add a new glass of wine there, red or white, we want to know what the neighbors are. In this case, we're going to put K equals 5. We'll talk about K in just a minute. A data point is classified by the majority of votes from its 5 nearest neighbors. Here, the unknown point would be classified as red since 4 out of 5 neighbors are red. So how do we choose K? How do we know K equals 5? I mean, that was the value we put in there, so we're going to talk about it. How do we choose the factor K? KNN algorithm is based on feature similarity. Choosing the right value of K is a process called parameter tuning and is important for better accuracy. So at K equals 3, we can classify, we have a question mark in the middle, as either a square or not. Is it a square or is it, in this case, a triangle? And so if we set K equals to 3, we're going to look at the 3 nearest neighbors. We're going to say this is a square. And if we put K equals to 7, we classify as a triangle, depending on what the other data is around it. And you can see as the K changes, depending on where that point is, that drastically changes your answer. And we jump here where we go, how do we choose the factor of K? You'll find this in all machine learning. Choosing these factors, that's the face you get. It's like, oh my gosh, did I choose the right K? Did I set it right, my values in whatever machine learning tool you're looking at, so that you don't have a huge bias in one direction or the other. And in terms of KNN, the number of K, if you choose it too low, the bias is based on, it's just too noisy. It's right next to a couple things and it's going to pick those things and you might get a skewed answer. And if your K is too big, then it's going to take forever to process. So you're going to run into processing issues and resource issues. So what we do, the most common use, and there's other options for choosing K, is to use the square root of n. So n is a total number of values you have, and you take the square root of it. In most cases, you also, if it's an even number, so if you're using, like in this case, squares and triangles, if it's even, you want to make your K value odd. That helps it select better. So in other words, you're not going to have a balance between two different factors that are equal. So usually you take the square root of n, and if it's even, you add 1 to it or subtract 1 from it, and that's where you get the K value from. That is the most common use, and it's pretty solid. It works very well. When do we use KNN? We can use KNN when data is labeled. So you need a label on it. We know we have a group of pictures with dogs, dogs, cats, cats. Data is noise free. And so you can see here, when we have a class and we have like underweight, 140, 23, Hello Kitty, normal, that's pretty confusing. We have a high variety of data coming in, so it's very noisy, and that would cause an issue. Data set is small, so we're usually working with smaller data sets where you might get into a gig of data if it's really clean, it doesn't have a lot of noise. Because KNN is a lazy learner, i.e. it doesn't learn a discriminative function from the training set. So it's very lazy, so if you have very complicated data and you have a large amount of it, you're not going to use the KNN. But it's really great to get a place to start. Even with large data, you can sort out a small sample and get an idea of what that looks like using the KNN. And also just using for smaller data sets, KNN works really good. How does the KNN algorithm work? Consider a data set having two variables, height in centimeters and weight in kilograms. And each point is classified as normal or underweight. So we can see right here we have two variables, true, false. They're either normal or they're not. They're underweight. On the basis of the given data, we have to classify the below set as normal or underweight using KNN. So if we have new data coming in that says 57 kilograms and 177 centimeters, is that going to be normal or underweight? To find the nearest neighbors, we'll calculate the Euclidean distance. According to the Euclidean distance formula, the distance between 2 points in the plane with the coordinates x, y, and ab is given by distance d equals the square root of x minus a squared plus y minus b squared. And you can remember that from the two edges of a triangle. We're computing the third edge since we know the x side and the y side. Let's calculate it to understand clearly. So we have our unknown point, and we placed it there in red, and we have our other points where the data is scattered around. The distance d1 is the square root of 170 minus 167 squared plus 57 minus 51 squared, which is about 6.7. And distance 2 is about 13. And distance 3 is about 13.4. Similarly, we will calculate the Euclidean distance of unknown data point from all the points in the data set. And because we're dealing with small amount of data, that's not that hard to do, and it's actually pretty quick for a computer. And it's not a really complicated math, so you can just see how close is the data based on the Euclidean distance. Hence, we have calculated the Euclidean distance of unknown data point from all the points as shown, where x1 and y1 equal 57 and 170, whose class we have to classify. So now we're looking at that, we're saying, well, here's the Euclidean distance. Who's going to be their closest neighbors? Now let's calculate the nearest neighbor at k equals 3. And we can see the three closest neighbors puts them at normal. And that's pretty self-evident. When you look at this graph, it's pretty easy to say, okay, we're just voting. Normal, 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 3 votes for normal. This is going to be a normal weight. So majority of neighbors are pointing towards normal. Hence, as per KNN algorithm, the class of 57,170 should be normal. So a recap of KNN. Positive integer k is specified along with a new sample. We select the k entries in our database which are closest to the new sample. We find the most common classification of these entries. This is the classification we give to the new sample. So as you can see, it's pretty straightforward. We're just looking for the closest things that match what we got. So let's take a look and see what that looks like in a use case in Python. So let's dive into the predict diabetes use case. So use case, predict diabetes. The objective, predict whether a person will be diagnosed with diabetes or not. We have a data set of 768 people who were or were not diagnosed with diabetes. And let's go ahead and open that file and just take a look at that data. And this is in a simple spreadsheet format. The data itself is comma separated, very common set of data, and it's also a very common way to get the data. And you can see here we have columns A through I. That's what 1, 2, 3, 4, 5, 6, 7, 8. 8 columns with a particular attribute, and then the 9th column, which is the outcome, is whether they have diabetes. As a data scientist, the first thing you should be looking at is insulin. Well, if someone has insulin, they have diabetes because that's why they're taking it. And that could cause issue in some of the machine learning packages, but for a very basic setup, this works fine for doing the KNN. And the next thing you notice is it didn't take very much to open it up. I can scroll down to the bottom of the data. There's 768. It's pretty much a small data set. At 769, I can easily fit this into my RAM on my computer. I can look at it, I can manipulate it, and it's not going to really tax just a regular desktop computer. You don't even need an enterprise version to run a lot of this. So let's start with importing all the tools we need. And before that, of course, we need to discuss what IDE I'm using. Certainly you can use any particular editor for Python, but I like to use for doing very basic visual stuff the Anaconda, which is great for doing demos, with the Jupyter Notebook. And just a quick view of the Anaconda Navigator, which is the new release out there, which is really nice. You can see under Home, I can choose my application. We're going to be using Python 3.6. I have a couple different versions on this particular machine. If I go under Environments, I can create a unique environment for each one, which is nice. And there's even a little button there where I can install different packages. So if I click on that button and open the terminal, I can then use a simple pip install to install different packages I'm working with. Let's go ahead and go back under Home, and we're going to launch our notebook. And I've already, kind of like the old cooking shows, I've already prepared a lot of my stuff, so we don't have to wait for it to launch because it takes a few minutes for it to open up a browser window. In this case, it's going to open up Chrome because that's my default that I use. And since the script is pre-done, you'll see I have a number of windows open up at the top, the one we're working in. And since we're working on the KNN predict whether a person will have diabetes or not, let's go ahead and put that title in there. And I'm also going to go up here and click on Cell. Actually, we want to go ahead and first insert a cell below, and then I'm going to go back up to the top cell, and I'm going to change the cell type to Markdown. That means this is not going to run as Python. It's a Markdown language. So if I run this first one, it comes up in nice big letters, which is kind of nice. Remind us what we're working on. And by now, you should be familiar with doing all of our imports. We're going to import the pandas as PD, import Numpy as NP. Pandas is the pandas data frame, and Numpy is a number array. Very powerful tools to use in here. So we have our imports. So we've brought in our pandas, our Numpy, our two general Python tools. And then you can see over here we have our train test split. By now you should be familiar with splitting the data. We want to split part of it for training our thing and then training our particular model. And then we want to go ahead and test the remaining data just to see how good it is. Pre-processing, a standard scalar preprocessor, so we don't have a bias of really large numbers. Remember in the data we had like number of pregnancies isn't going to get very large, where the amount of insulin they take can get up to 256. So 256 versus 6. That will skew results, so we want to go ahead and change that so that they're all uniform between -1 and 1. And then the actual tool. This is the K-neighbors classifier we're going to use. And finally, the last three are 3 tools to test, all about testing our model. How good is it? We just put down test on there. And we have our confusion matrix, our F1 score, and our accuracy. So we have our 2 general Python modules we're importing, and then we have our 6 modules specific from the sklearn setup. And then we do need to go ahead and run this so that these are actually imported. There we go. And then move on to the next step. And so in this set, we're going to go ahead and load the database. We're going to use pandas. Remember, pandas is PD. And we'll take a look at the data in Python. We looked at it in a simple spreadsheet, but usually I like to also pull it up so that we can see what we're doing. So here's our data set equals pd.readcsv. That's a pandas command. And the diabetes folder I just put in the same folder where my IPython script is. If you put it in a different folder, you'd need the full length on there. We can also do a quick length of the data set. That is a simple Python command, len for length. We might even, let's go ahead and print that. We'll go print. And if you do it on its own line, length.dataset in the Jupyter Notebook, it'll automatically print it. But when you're in most of your different setups, you want to do the print in front of there. And then we want to take a look at the actual data set. And since we're in pandas, we can simply do dataset head. And again, let's go ahead and add the print in there. If you put a bunch of these in a row, the dataset 1 head, dataset 2 head, it only prints out the last one. So I always like to keep the print statement in there. But because most projects only use one data frame, pandas data frame, doing it this way doesn't really matter. The other way works just fine. And you can see when we hit the run button, we have the 768 lines, which we knew, and we have our pregnancies. It's automatically given a label on the left. Remember, the head only shows the first 5 lines. So we have 0 through 4. And just a quick look at the data, you can see it matches what we looked at before. We have pregnancy, glucose, blood pressure, all the way to age, and then the outcome on the end. And we're going to do a couple things in this next step. We're going to create a list of columns where we can't have 0. There's no such thing as 0 skin thickness or 0 blood pressure, 0 glucose. Any of those, you'd be dead. So not a really good factor if they have a 0 in there because they didn't have the data. And we'll take a look at that because we're going to start replacing that information with a couple of different things. And let's see what that looks like. So first we create a nice list. As you can see, we have the values we talked about: glucose, blood pressure, skin thickness. And this is a nice way when you're working with columns, is to list the columns you need to do some kind of transformation on. Very common thing to do. And then for this particular setup, we certainly could use there's some some Panda tools that will do a lot of this, where we can replace the NA. But we're going to go ahead and do it as a dataset column equals dataset column.replace. This is still pandas. You can do it direct. There's also one that you look for your NAN. A lot of different options in here. But the NAN, Numpy NAN is what that stands for, is none, it doesn't exist. So the first thing we're doing here is we're replacing the 0 with a Numpy none. There's no data there. That's what that says. That's what this is saying right here. So put the 0 in, and we're going to replace zeros with no data. So if it's a 0, that means the person's, well, hopefully not dead. Hopefully they just didn't get the data. The next thing we want to do is we're going to create the mean, which is the integer from the data set from the column dot mean, where we skip NAs. We can do that. That is a pandas command there, the skip NA. So we're going to figure out the mean of that data set. And then we're going to take that data set column and we're going to replace all the NP-NAN with the means. Why did we do that? And we could have actually just taken this step and gone right down here and just replaced 0 and skip anything except you could actually, there's a way to skip zeros and then just replace all the zeros. But in this case, we want to go ahead and do it this way. So you can see that we're switching this to a non-existent value. Then we're going to create the mean. Well, this is the average person. So if we don't know what it is, if they did not get the data and the data is missing, one of the tricks is you replace it with the average. What is the most common data for that? This way you can still use the rest of those values to do your computation, and it kind of just brings that particular value, those missing values, out of the equation. Let's go ahead and take this and we'll go ahead and run it. Doesn't actually do anything, so we're still preparing our data. If you wanted to see what that looks like, we don't have anything in the first few lines, so it's not going to show up, but we certainly could look at a row. Let's do that. Let's go into our data set. Let's print a data set, and let's pick, in this case, let's just do glucose. And if I run this, this is going to print all the different glucose levels going down, and we thankfully don't see anything in here that looks like missing data, at least on the ones it shows. You can see it skipped a bunch in the middle, because that's what it does. If you have too many lines in Jupyter Notebook, it'll skip a few and go on to the next in a data set. Let me go and remove this, and we'll just zero out that. And of course, before we do any processing, before proceeding any further, we need to split the data set into our train and testing data. That way we have something to train it with and something to test it on. And you're going to notice we did a little something here with the pandas database code. There we go, my drawing tool. We've added in this right here off the data set. And what this says is that the first one in pandas, this is from the PD pandas, it's going to say within the data set, we want to look at the I location, and it is all rows. That's what that says. So we're going to keep all the rows, but we're only looking at column 0 to 8. Remember, column 9, here it is right up here, we printed it in here, is outcome. Well, that's not part of the training data, that's part of the answer. Yes, column 9, but it's listed as 8, number 8. So 0 to 8 is 9 columns. So 8 is the value. And when you see it in here, 0, this is actually 0 to 7. It doesn't include the last one. And then we go down here to Y, which is our answer, and we want just the last one, just column 8. And you can do it this way with this particular notation. And then if you remember, we imported the train test split. That's part of the sklearn right there. And we simply put in our X and our Y. We're going to do random state equals 0. You don't have to necessarily seed it. That's a seed number. I think the default is 1 when you seed it. I'd have to look that up. And then the test size. Test size is 0.2. That simply means we're going to take 20% of the data and put it aside so that we can test it later. That's all that is. And again, we're going to run it. Not very exciting. So far, we haven't had any printout other than to look at the data. But that is, a lot of this is prepping this data. Once you prep it, the actual lines of code are quick and easy. And we're almost there with the actual running of our KNN. We need to go ahead and scale the data. If you remember correctly, we're fitting the data in a standard scaler, which means instead of the data being from 5 to 303 in one column, and the next column is 1 to 6, we're going to set that all so that all the data is between -1 and 1. That's what that standard scaler does. Keeps it standardized. And we only want to fit the scaler with the training set, but we want to make sure the testing set is, the X test going in is also transformed, so it's processing it the same. So here we go with our standard scaler. We're going to call it SC_X for the scaler. and we're going to import the standard scalar into this variable, and then our xtrain equals sc underscore x dot fit transform. So we're creating the scalar on the xtrain variable, and then our xtest, we're also going to transform it. So we've trained and transformed the xtrain, and then the xtest isn't part of that training. It isn't part of training the transformer. It just gets transformed. That's all it does. And again, we're going to go ahead and run this. And if you look at this, we've now gone through these steps, all three of them. We've taken care of replacing our zeros for key columns that shouldn't be zero, and we replace that with the means of those columns. That way that they fit right in with our data models. We've come down here and we split the data, so now we have our test data and our training data, and then we've taken and we've scaled the data. So all of our data going in. Now, no, we don't train the Y part, the Y train and Y test. That never has to be trained. It's only the data going in. That's what we want to train in there. Then define the model using k-neighbors classifier and fit the train data in the model. So we do all that data prep. And you can see down here we're only going to have a couple lines of code where we're actually building our model and training it. That's one of the cool things about Python and how far we've come. It's such an exciting time to be in machine learning because there's so many automated tools. Let's see, before we do this, let's do a quick length of, and let's do Y. Let's just do length of Y. And we get 768. And if we import math, we do math dot square root. Let's do Y train. There we go. It's actually supposed to be X train. Before we do this, let's go ahead and do import math and do math square root length of Y test. And when I run that, we get 12.409. I wanted to show you where this number comes from we're about to use. 12 is an even number, so if you're ever voting on things, remember the neighbors all vote, don't want to have an even number of neighbors voting, so we want to do something odd. And let's just take one away and we'll make it 11. Let me delete this out of here. That's one of the reasons I love Jupyter Notebook, because you can flip around and do all kinds of things on the fly. So we'll go ahead and put in our classifier. We're creating our classifier now, and it's going to be the k-neighbors classifier. In neighbors equal 11. Remember we did 12 minus 1 for 11, so we have an odd number of neighbors. P equals 2, because we're looking for are they diabetic or not, and we're using the Euclidean metric. There are other means of measuring the distance. You could do like square means value. There's all kinds of measure this, but the Euclidean's the most common one, and it works quite well. It's important to evaluate the model. Let's use the confusion matrix to do that. And we're going to use the confusion matrix, wonderful tool, and then we'll jump into the F1 score, and finally accuracy score, which is probably the most commonly used quoted number when you go into a meeting or something like that. So let's go ahead and paste that in there, and we'll set the CM equal to confusion matrix, Y test, Y predict. So those are the two values we're going to put in there, and let me go ahead and run that and print it out. And the way you interpret this is you have the Y predicted, which would be your title up here. We could do, let's just do PRED, predicted across the top, and actual going down. Actual. It's always hard to write in here, actual. That means that this column here down the middle, that's the important column. And it means that our prediction said 94, and prediction and the actual agreed on 94 and 32. This number here, the 13 and the 15, those are what was wrong. So you could have like three different, if you're looking at this across three different variables instead of just two, you'd end up with the third row down here and the column going down the middle. So in the first case we have and I believe the 0 is the 94 people who don't have diabetes. The prediction said that 13 of those people did have diabetes and were at high risk. And the 32 that had diabetes, it had correct. But our prediction said another 15. Out of that 15, it classified as incorrect. So you can see where that classification comes in and how that works on the confusion matrix. And then we're going to go ahead and print the F1 score. Let me just run that. And you see we get a 0.69 in our F1 score. The F1 takes into account both sides of the balance of false positives. Where if we go ahead and just do the accuracy account, and that's what most people think of, is it looks at just how many we got right out of how many we got wrong. So a lot of people, when you're a data scientist and you're talking to other data scientists, they're going to ask you what the F1 score or the F score is. If you're talking to the general public or the decision makers in the business, they're going to ask what the accuracy is. And the accuracy is always better than the F1 score. But the F1 score is more telling. It lets us know that there's more false positives than we would like on here. But 82%, not too bad for a quick flash look at people's different statistics and running an sklearn and running the KNN, the K nearest neighbor on it. So we have created a model using KNN, which can predict whether a person will have diabetes or not, or at the very least whether they should go get a checkup and have their glucose checked regularly or not. The print accuracy score, we got the 0.818, was pretty close to what we got, and we can pretty much round that off and just say we have an accuracy of 80%. Tells us it is a pretty fair fit in the model.
What is K-means clustering? K-means clustering is an unsupervised learning algorithm. In this case, you don't have labeled data, unlike in supervised learning. So you have a set of data and you want to group them. And as the name suggests, you want to put them into clusters, which means objects that are similar in nature, similar in characteristics, need to be put together. So that's what K-means clustering is all about. The term K is basically a number. So we need to tell the system how many clusters we need to perform. So if k is equal to 2, there will be 2 clusters. If k is equal to 3, it's 3 clusters, and so on and so forth. That's what the k stands for. And of course, there is a way of finding out what is the best or optimum value of k for a given data. We will look at that. So that is k-means clustering. So let's take an example. K-means clustering is used in many scenarios, but let's take an example of cricket, the game of cricket. Let's say you received data of a lot of players from maybe all over the country or all over the world, and this data has information about the runs scored by the people or by the player and the wickets taken by the player. And based on this information, we need to cluster this data into 2 clusters, batsmen and bowlers. So this is an interesting example. Let's see how we can perform this. So we have the data, which consists of primarily 2 characteristics, which is the runs and the wickets. So the bowlers basically take wickets and the batsmen score runs. There will be, of course, a few bowlers who can score some runs, and similarly there will be some batsmen who would have taken a few wickets. But with this information, we want to cluster those players into batsmen and bowlers. So how does this work? Let's say this is how the data is. So there is information on the y-axis about the runs scored and on the x-axis about the wickets taken by the players. So if we do a quick plot, this is how it would look. And when we do the clustering, we need to have the clusters like shown in the third diagram out here. So we need to have a cluster which consists of people who have scored high runs, which is basically the batsmen, and then we need a cluster with people who have taken a lot of wickets, which is typically the bowlers. There may be a certain amount of overlap, but we will not talk about it right now. So with k-means clustering, we will have here, that means k is equal to 2, and we will have 2 clusters, which is batsmen and bowlers. So how does this work? The way it works is, the first step in k-means clustering is the allocation of 2 centroids randomly. So 2 points are assigned as so-called centroids. So in this case, we want 2 clusters, which means k is equal to 2. So 2 points have been randomly assigned as centroids. Keep in mind, these points can be anywhere. They are random points. They are not really the centroids. Centroid means it's a central point of a given data set, but in this case, when it starts off, it's not really the centroid. Okay, so these points, though in our presentation here we have shown them one point closer to these data points and another closer to these data points, they can be assigned randomly anywhere. Okay, so that's the first step. The next step is to determine the distance of each of the data points from each of the randomly assigned centroids. So for example, we take this point and find the distance from this centroid and the distance from this centroid. This point is taken and the distance is found from this centroid and this centroid, and so on and so forth. So for every point, the distance is measured from both the centroids, and then whichever distance is less, that point is assigned to that centroid. So for example, in this case, visually it is very obvious that all these data points are assigned to this centroid and all these data points are assigned to this centroid. And that's what is represented here in blue color and in this yellow color. The next step is to actually determine the central point or the actual centroid for these two clusters. So we have this one initial cluster, this one initial cluster, but as you can see, these points are not really the centroid. Centroid means it should be the central position of this data set, central position of this data set. So that is what needs to be determined as the next step. So the central point or the actual centroid is determined and the original randomly allocated centroid is repositioned to the actual centroid of these new clusters. And this process is actually repeated. Now what might happen is some of these points may get reallocated. In our example, that is not happening probably, but it may so happen that the distance is found between each of these data points once again with these centroids. And if it is required, some points may be reallocated. We will see that in a later example, but for now we will keep it simple. So this process is continued till the centroid repositioning stops, and that is our final cluster. So this is so after iteration, we come to this position, this situation where the centroid doesn't need any more repositioning, and that means our algorithm has converged. Convergence has occurred, and we have the cluster, two clusters, we have the clusters with a centroid. So this process is repeated. The process of calculating the distance and repositioning the centroid is repeated till the repositioning stops, which means that the algorithm has converged and we have the final cluster with the data points and the centroids. So this is what you're going to learn from this session. We will talk about the types of clustering, what is k-means clustering, application of k-means clustering. K-means clustering is done using distance measure, so we will talk about the common distance measures, and then we will talk about how k-means clustering works and go into the details of k-means clustering algorithm, and then we will end with a demo and a use case for k-means clustering. So let's begin. First of all, what are the types of clustering? There are primarily two categories of clustering: hierarchical clustering and then partitional clustering. And each of these categories are further subdivided into agglomerative and divisive clustering and k-means and fuzzy c-means clustering. Let's take a quick look at what each of these types of clustering are. In hierarchical clustering, the clusters have a tree-like structure, and hierarchical clustering is further divided into agglomerative and divisive. Agglomerative clustering is a bottom-up approach. We begin with each element as a separate cluster and merge them into successively larger clusters. So for example, we have A, B, C, D, E, F. We start by combining B and C, form one cluster, D, E, and E, form one more. Then we combine D, E, and F, one more bigger cluster, and then add B, C to that, and then finally A to it. Compared to that, divisive clustering or divisive clustering is the top-down approach. We begin with the whole set and proceed to divide it into successively smaller clusters. So we have A, B, C, D, E, F. We first take that as a single cluster and then break it down into A, B, C, D, E, and F. Then we have partitional clustering split into two subtypes: k-means clustering and fuzzy c-means. In k-means clustering, the objects are divided into the number of clusters mentioned by the number k. That's where the k comes from. So if we say k is equal to 2, the objects are divided into two clusters, C1 and C2. And the way it is done is the features or characteristics are compared, and all objects having similar characteristics are clubbed together. So that's how k-means clustering is done. We will see it in more detail as we move forward. And fuzzy c-means is very similar to k-means in the sense that it clubs objects that have similar characteristics together, but while in k-means clustering, two objects cannot belong to, or any object, a single object cannot belong to two different clusters, in c-means objects can belong to more than one cluster. So that is the primary difference between k-means and fuzzy c-means. So what are some of the applications of k-means clustering? K-means clustering is used in a variety of examples or variety of business cases in real life, starting from academic performance, diagnostic systems, search engines, and wireless sensor networks, and many more. So let us take a little deeper look at each of these examples. Academic performance. So based on the scores of the students are categorized into A, B, C, and so on. Clustering forms a backbone of search engines. When a search is performed, the search results need to be grouped together. The search engines very often use clustering to do this. And similarly, in case of wireless sensor networks, the clustering algorithm plays the role of finding the cluster heads, which collects all the data in its respective cluster. So clustering, especially k-means clustering, uses distance measure. So let's take a look at what is distance measure. So while these are the different types of clustering, in this video we will focus on k-means clustering. So distance measure tells how similar some objects are. So the similarity is measured using what is known as distance measure. And what are the various types of distance measures? There is Euclidean distance, there is Manhattan distance, then we have squared Euclidean distance measure and cosine distance measure. These are some of the distance measures supported by k-means clustering. Let's take a look at each of these. What is Euclidean distance measure? This is nothing but the distance between 2 points. So we have learnt in high school how to find the distance between 2 points. This is a little sophisticated formula for that, but we know a simpler one is square root of y2 minus y1 whole square plus x2 minus x1 whole square. So this is an extension of that formula. So that is the Euclidean distance between 2 points. What is the squared Euclidean distance measure? It's nothing but the square of the Euclidean distance, as the name suggests. So instead of taking the square root, we leave the square as it is. And then we have Manhattan distance measure. In case of Manhattan distance, it is the sum of the distances across the x-axis and the y-axis. And note that we are taking the absolute value so that the negative values don't come into play. So that is the Manhattan distance measure. Then we have cosine distance measure. In this case, we take the angle between the two vectors formed by joining the points from the origin. So that is the cosine distance measure. Okay, so that was a quick overview about the various distance measures that are supported by k-means. Now let's go and check how exactly k-means clustering works. Okay, so this is how k-means clustering works. This is like a flowchart of the whole process. There is a starting point, and then we specify the number of clusters that we want. Now there are a couple of ways of doing this. We can do by trial and error. So we specify a certain number, maybe k is equal to 3 or 4 or 5 to start with, and then as we progress we keep changing until we get the best clusters. Or there is a technique called elbow technique, whereby we can determine the value of k. What should be the best value of k? How many clusters should be formed? So once we have the value of k, we specify that, and then the system will assign that many centroids. So it picks randomly, that to start with, randomly that many points that are considered to be the centroids of these clusters. And then it measures the distance of each of the data points from these centroids and assigns those points to the corresponding centroid from which the distance is minimum. So each data point will be assigned to the centroid which is closest to it. And thereby we have k number of initial clusters. However, this is not the final clusters. The next step it does is, for the new groups, for the clusters that have been formed, it calculates the mean position, thereby calculates the new centroid position. The position of the centroid moves compared to the randomly allocated one. So it's an iterative process. Once again, the distance of each point is measured from this new centroid point, and if required, the data points are reallocated to the new centroids, and the mean position or the new centroid is calculated once again. If the centroid moves, then the iteration continues, which means the convergence has not happened. The clustering has not converged. So as long as there is a movement of the centroid, this iteration keeps happening. But once the centroid stops moving, which means that the cluster has converged or the clustering process has converged, that will be the end result. So now we have the final position of the centroid and the data points are allocated accordingly to the closest centroid. I know it's a little difficult to understand from this simple flowchart, so let's do a little bit of visualization and see if we can explain it better. Let's take an example. If we have a data set for a grocery shop. So let's say we have a data set for a grocery shop and now we want to find out how many clusters this has to be spread across. So how do we find the optimum number of clusters? There is a technique called the elbow method. So when these clusters are formed, there is a parameter called within sum of squares. And the lower this value is, the better the cluster is. That means all these points are very close to each other. So we use this within sum of squares as a measure to find the optimum number of clusters that can be formed for a given data set. So we create clusters, or we let the system create clusters of a variety of numbers, maybe of 10 clusters, and for each value of k, the within SS is measured, and the value of k which has the least amount of within SS or WSS, that is taken as the optimum value of k. So this is the diagrammatic representation. So we have on the y-axis the within sum of squares or WSS, and on the x-axis we have the number of clusters. So as you can imagine, if you have k is equal to 1, which means all the data points are in a single cluster, the within SS value will be very high because they are probably scattered all over. The moment you split it into 2, there will be a drastic fall in the within SS value. And that's what is represented here. But then as the value of k increases, the rate of decrease will not be so high. It will continue to decrease, but probably the rate of decrease will not be high. So that gives us an idea. So from here, we get an idea, for example, the optimum value of k should be either 2 or 3 or at the most 4. But beyond that, increasing the number of clusters is not dramatically changing the value in WSS because that pretty much gets stabilized. Okay, now that we have got the value of k, and let's assume that these are our delivery points, the next step is basically to assign two centroids randomly. So let's say C1 and C2 are the centroids assigned randomly. Now the distance of each location from the centroid is measured, and each point is assigned to the centroid which is closest to it. So for example, these points are very obvious that these are closest to C1, whereas this point is far away from C2. So these points will be assigned, which are close to C1 will be assigned to C1, and these points or locations which are close to C2 will be assigned to C2. And then, so this is how the initial grouping is done. This is part of C1 and this is part of C2. Then the next step is to calculate the actual centroid of this data, because remember, C1 and C2 are not the centroids. They've been randomly assigned points, and only thing that has been done was the data points which are closest to them have been assigned to them. But now in this step, the actual centroid will be calculated, which may be for each of these data sets somewhere in the middle. So that's like the mean point that will be calculated, and the centroid will actually be positioned or repositioned there. Same with C2. So the new centroid for this group is C2 in this new position, and C1 is in this new position. Once again, the distance of each of the data points is calculated from these centroids. Now remember, it's not necessary that the distance still remains or each of these data points still remain in the same group. By recalculating the distance, it may be possible that some points get reallocated. Like so. You see this? So this point earlier was closer to C2 because C2 was here, but after recalculating, repositioning, it is observed that this is closer to C1 than C2. So this is the new grouping. So some points will be reassigned. And again, the centroid will be calculated, and if the centroid doesn't change, so that is a repetitive process, iterative process. And if the centroid doesn't change, once the centroid stops changing, that means the algorithm has converged. And this is our final cluster with this as the centroid, C1 and C2 as the centroids, these data points as a part of each cluster. So I hope this helps in understanding the whole process, iterative process of k-means clustering. So let's take a look at the k-means clustering algorithm. Let's say we have x1, x2, x3, n number of points as our inputs, and we want to split this into k clusters, or we want to create k clusters. So the first step is to randomly pick k points and call them centroids. They are not real centroids because centroid is supposed to be a center point, but they are just called centroids. And we calculate the distance of each and every input point from each of the centroids. So the distance of x1 from C1, from C2, C3, each of the distances we calculate. And then find out which distance is the lowest and assign x1 to that particular random centroid. Repeat that process for x2. Calculate its distance from each of the centroids C1, C2, C3 up to Ck, and find which is the lowest distance and assign x2 to that particular centroid. Same with x3 and so on. So that is the first round of assignment that is done. Now we have k groups because we have assigned the value of k. So there are k centroids, and so there are k groups. All these inputs have been split into k groups. However, remember, we pick the centroids randomly, so they are not real centroids. So now what we have to do? We have to calculate the actual centroids for each of these groups, which is like the mean position. Which means that the position of the randomly selected centroids will now change, and they will be the mean positions of these newly formed k groups. And once that is done, we once again repeat this process of calculating the distance, right? So this is what we are doing as a part of step 4. We repeat step 2 and 3. So we again calculate the distance of x1 from the centroid C1, C2, C3, and then see which is the lowest value and assign x1 to that. Calculate the distance of x2 from C1, C2, C3 or whatever up to Ck, and find whichever is the lowest distance and assign x2 to that centroid, and so on. In this process, there may be some reassignment. x1 was probably assigned to cluster C2, and after doing this calculation, maybe now x1 is assigned to C1. So that kind of reallocation may happen. So we repeat the steps 2 and 3 till the position of the centroids don't change or stop changing, and that's when we have convergence. So let's take a detailed look at each of these steps. So we randomly pick k cluster centers. We call them centroids because they are not really the centroids. So let us name them C1, C2 up to Ck. And then step 2, we assign each data point to the closest center. So what we do, we calculate the distance of each x value from each c value. So the distance between x1, c1, distance between x1, c2, x1, c3, and then we find which is the lowest value, right? That's the minimum value we find, and assign x1 to that particular centroid. Then we go next to x2, find the distance of x2 from c1, x2 from c2, x2 from c3, and so on up to ck, and then assign it to the point or to the centroid which has the lowest value, and so on. So that is step number 2. In step number 3, we now find the actual centroid for each group. So what has happened? As a part of step number 2, we now have all the points, all the data points grouped into k groups. because we wanted to create K clusters, right? So we have K groups, each one may be having a certain number of input values, and they need not be equally distributed, by the way. Based on the distance, we will have K groups. But remember, the initial values of the C1, C2 were not really the centroids of these groups, right? We assigned them randomly. So now in step 3, we actually calculate the centroid of each group, which means the original point which we thought was the centroid will shift to the new position, which is the actual centroid for each of these groups. Okay. And we again calculate the distance. So we go back to step 2, which is what? We calculate again the distance of each of these points from the newly positioned centroids. And if required, we reassign these points to the new centroids. So as I said earlier, there may be a reallocation. So we now have a new set or a new group. We still have K groups, but the number of items and the actual assignment may be different from what was in step 2 here. Okay, so that might change. Then we perform step 3 once again to find the new centroid of this new group. So we have again a new set of clusters, new centroids, and new assignments. We repeat this step 2 again. Once again we find, and then it is possible that after iterating through 3 or 4 or 5 times, the centroid will stop moving, in the sense that when you calculate the new value of the centroid, that will be same as the original value, or there will be very marginal change. So that is when we say convergence has occurred, and that is our final cluster. That's the formation of the final cluster. Alright, so let's see a couple of demos of K-means clustering. We will actually see some live demos in Python Notebook, using Python Notebook. But before that, let's find out what's the problem that we are trying to solve. The problem statement is, let's say Walmart wants to open a chain of stores across the state of Florida, and it wants to find the optimal store locations. Now the issue here is, if they open too many stores close to each other, obviously they will not make profit. But if the stores are too far apart, then they will not have enough sales. So how do they optimize this? Now, for an organization like Walmart, which is an e-commerce giant, they already have the addresses of their customers in their database. So they can actually use this information or this data and use K-means clustering to find the optimal location. Now, before we go into the Python Notebook and show you the live code, I wanted to take you through very quickly a summary of the code in the slides, and then we will go into the Python Notebook. So in this block, we are basically importing all the required libraries like Numpy, Matplotlib, and so on. And we are loading the data that is available in the form of, let's say, the addresses. For simplicity's sake, we will just take them as some data points. Then the next thing we do is quickly do a scatter plot to see how they are related to each other with respect to each other. So in the scatter plot, we see that there are a few distinct groups already being formed. So you can actually get an idea about how the cluster would look and how many clusters, what is the optimal number of clusters. And then starts the actual K-means clustering process. So we will assign each of these points to the centroids and then check whether they are the optimal distance, which is the shortest distance, and assign each of the points, data points, to the centroids, and then go through this iterative process till the whole process converges. And finally, we get an output like this. So we have 4 distinct clusters, and which is, we can say that this is how the population is probably distributed across Florida state, and the centroids are like the location where the store should be, the optimum location where the store should be. So that's the way we determine the best locations for the store, and that's how we can help Walmart find the best locations for their stores in Florida. So now let's take this into Python notebook. Let's see how this looks when we are running the code live. Alright, so this is the code for k-means clustering in Jupyter Notebook. We have a few examples here which we will demonstrate how k-means clustering is used, and even there is a small implementation of k-means clustering as well. Okay, so let's get started. Okay, so this block is basically importing the various libraries that are required, like matplotlib and numpy and so on and so forth, which would be used as a part of the code. Then we are going and creating blobs which are similar to clusters. Now this is a very neat feature which is available in scikit-learn. Make blobs is a nice feature which creates clusters of data sets. So that's a wonderful functionality that is readily available for us to create some test data kind of thing. Okay, so that's exactly what we are doing here. We are using make blobs, and we can specify how many clusters we want. So centers we are mentioning here. So it will go ahead, and so we just mentioned 4. So it will go ahead and create some test data for us. And this is how it looks. As you can see visually also, we can figure out that there are 4 distinct classes or clusters in this data set, and that is what make blobs actually provides. Now from here onwards, we will basically run the standard k-means functionality that is readily available. So we really don't have to implement k-means itself. The k-means functionality or the function is readily available. You just need to feed the data and we'll create the clusters. So this is the code for that. We import k-means, and then we create an instance of k-means, and we specify the value of k. This n underscore clusters is the value of k. Remember, k-means k is basically the number of clusters that you want to create, and it is a integer value. So this is where we are specifying that. So we have k is equal to 4, and so that instance is created. We take that instance, and as with any other machine learning functionality, fit is what we use. The function, or the method rather, fit is what we use to train the model. Here there is no real training kind of thing, but that's the call. Okay, so we are calling fit, and what we are doing here, we are just passing the data. So x has these values, the data that has been created, right? So that is what we are passing here. And this will go ahead and create the clusters, and then we are using, after doing fit, we run the predict, which basically assigns for each of these observations which cluster it belongs to. All right, so it will name the clusters. Maybe this is cluster 1, this is 2, 3, and so on, or I will actually start from 0. Cluster 0, 1, 2, and 3 maybe, and then for each of the observations, it will assign based on which cluster it belongs to, it will assign a value. So that is stored in y underscore k-means. When we call predict, that is what it does. And we can take a quick look at these y underscore k-means, or the cluster numbers that have been assigned for each observation. So this is the cluster number assigned for observation 1, maybe this is for observation 2, observation 3, and so on. So we have how many? About, I think, 300 samples, right? So all the 300 samples, there are 300 values here. Each of them, the cluster number is given, and the cluster number goes from 0 to 3. So there are 4 clusters, so the numbers go from 0, 1, 2, 3. So that's what is seen here. Okay, now, so this was a quick example of generating some dummy data and then clustering that. Okay, and this can be applied if you have proper data. You can just load it up into X, for example, here, and then run the k-means. So this is the central part of the k-means clustering program example. So you basically create an instance, and you mention how many clusters you want by specifying this parameter n underscore clusters, and that is also the value of k, and then pass the data to get the values. Now, the next section of this code is the implementation of a k-means. Now, this is kind of a rough implementation of the k-means algorithm. So we will just walk you through. I will walk you through the code at each step what it is doing, and then we will see a couple of more examples of how k-means clustering can be used in maybe some real life examples, real life use cases. All right. So in this case here, what we are doing is basically implementing the k-means clustering, and there is a function or a library calculates for a given two pairs of points. It will calculate the distance between them and see which one is the closest and so on. So this is pretty much like what k-means does, right? So it calculates the distance of each point or each data set from predefined centroid, and then based on whichever is the lowest, this particular data point is assigned to that centroid. So that is basically available as a standard function, and we will be using that here. So as explained in the slides, the first step that is done in case of k-means clustering is to randomly assign some centroids. So as a first step, we randomly allocate a couple of centroids, which we are calling as centers. And then we put this in a loop and we take it through an iterative process. For each of the data points, we first find out using this function pairwise distance argument. For each of the points, we find out which center or which randomly selected centroid is the closest, and accordingly we assign that data or the data point to that particular centroid or cluster. And once that is done for all the data points, we calculate the new centroid by finding out the mean position with the center position, right? So we calculate the new centroid, and then we check if the new centroid is the coordinates or the position is the same as the previous centroid. The positions we will compare, and if it is the same, that means the process has converged. So remember, we do this process till the centroids or the centroid doesn't move anymore, right? So the centroid gets relocated each time this reallocation is done. So the moment it doesn't change anymore, the position of the centroid doesn't change anymore, we know that convergence has occurred. So till then, so you see here, this is like an infinite loop. While true is an infinite loop. It only breaks when the centers are the same. The new center and the old center positions are the same. And once that is done, we return the centers and the labels. Now, of course, as explained, this is not a very sophisticated and advanced implementation, very basic implementation, because one of the flaws in this is that sometimes what happens is the centroid, the position will keep moving, but the change will be very minor. So in that case, also that is actually convergence, right? So for example, the change is 0.0001. We can consider that as convergence. Otherwise, what will happen is this will either take forever or it will be never ending. So that's a small flaw here. So that is something, additional checks may have to be added here. But again, as mentioned, this is not the most sophisticated implementation. This is like a kind of a rough implementation of the k-means clustering. Okay, so if we execute this code, this is what we get as the output. So this is the definition of this particular function, and then we call that find underscore clusters, and we pass our data x and the number of clusters, which is 4. And if we run that and plot it, this is the output that we get. So this is, of course, each cluster is represented by a different color. So we have a cluster in green color, yellow color, and so on and so forth. And these big points here, these are the centroids. This is the final position of the centroids. And as you can see visually also, this appears like a kind of a center of all these points here, right? Similarly, this is like the center of all these points here, and so on. So this is the example, or this is an example of an implementation of k-means clustering. And next we will move on to see a couple of examples of how k-means clustering is used in maybe some real life scenarios or use cases. In the next example or demo, we are going to see how we can use k-means clustering to perform color compression. We will take a couple of images, so there will be 2 examples. and we will try to use k-means clustering to compress the colors. This is a common situation in image processing when you have an image with millions of colors, but then you cannot render it on some devices which may not have enough memory. So that is the scenario where something like this can be used. So before again we go into the Python notebook, let's take a look at quickly the code. As usual, we import the libraries and then we import the image, and then we will flatten it. So the reshaping is basically we have the image information is stored in the form of pixels, and if the image is like, for example, 427 by 640 and it has 3 colors, so that's the overall dimension of the initial image. We just reshape it and then feed this to our algorithm, and this will then create clusters of only 16 clusters. So this colors, there are millions of colors, and now we need to bring it down to 16 colors. So we use k is equal to 16, and this is how, when we visualize, this is how it looks. These are all about 16 million possible colors. The input color space has 16 million possible colors, and we just compress it to 16 colors. So this is how it would look when we compress it to 16 colors, and this is how the original image looks, and after compression to 16 colors, this is how the new image looks. As you can see, there is not a lot of information that has been lost, though the image quality is definitely reduced a little bit. So this is an example which we are going to now see in Python notebook. Let's go into the Python notebook. And once again, as always, we will import some libraries and load this image called flower.jpg. Okay, so we'll load that, and this is how it looks. This is the original image, which has, I think, 16 million colors, and this is the shape of this image, which is basically, what is the shape is nothing but the overall size, right? So this is 427 pixel by 640 pixel, and then there are 3 layers, which is this 3 basically is for RGB, which is red, green, blue. So color image will have that, right? So that is the shape of this. Now what we need to do is data. Let's take a look at how data is looking. So let me just create a new cell and show you what is in data. Basically, we have captured this information. So data is what, let me just show you here. All right, so let's take a look at China. What are the values in China? And if we see here, this is how the data is stored. This is nothing but the pixel values. Okay, so this is like a matrix, and each one has about for this 427 by 640 pixels. All right, so this is how it looks. Now the issue here is these values are large, the numbers are large, so we need to normalize them to between 0 and 1. Right, so that's why we will basically create one more variable, which is data, which will contain the values between 0 and 1, and the way to do that is divide by 255. So we divide China by 255 and we get the new values in data. So let's just run this piece of code, and this is the shape. So we now have also, what we have done is we changed using reshape, we converted into the 3-dimensional into a 2-dimensional data set. And let us also take a look at how, let me just insert probably a cell here and take a look at how data is looking. All right, so this is how data is looking, and now you see this is the values are between 0 and 1. Right, so if you earlier noticed, in case of China, the values were large numbers. Now everything is between 0 and 1. This is one of the things we need to do. All right, so after that, the next thing that we need to do is to visualize this, and we can take random set of maybe 10,000 points and plot it and check and see how this looks. So let us just plot this, And so this is how the original, the pixel distribution is. These are two plots. One is red against green and another is red against blue, and this is the original distribution of the color. So then what we will do is we will use k-means clustering to create just 16 clusters for the various colors and then apply that to the image. Now what will happen is, since the data is large because there are millions of colors, using regular k-means may be a little time consuming. So there is another version of k-means which is called mini batch k-means. So we will use that, which processes in, the overall concept remains the same, but this basically processes it in smaller batches. That's the only thing. Okay, so the results will pretty much be the same. So let's go ahead and execute this piece of code and also visualize this so that we can see that there are these. This is how the 16 colors would look. So this is red against green and this is red against blue. There is quite a bit of similarity between this original color schema and the new one, right? So it doesn't look very completely different or anything like that. Now we apply the newly created colors to the image, and we can take a look how this is looking now. We can compare both the images. So this is our original image and this is our new image. So as you can see, there is not a lot of information that has been lost. It pretty much looks like the original image. Yes, we can see that, for example, here there is a little bit, it appears a little dullish compared to this one, right? Because we kind of took off some of the finer details of the color, but overall the high level information has been maintained. At the same time, the main advantage is that now this is an image which can be rendered on a device which may not be that very sophisticated. Now let's take one more example with a different image. In the second example, we will take an image of the Summer Palace in China, and we repeat the same process. This is a high definition color image with millions of colors and also three-dimensional. Now we will reduce that to 16 colors using k-means clustering, and we do the same process like before. We reshape it and then we cluster the colors to 16, and then we render the image once again, and we will see that the quality of the image slightly deteriorates. As you can see here, this has much finer details in this which are probably missing here, but then that's the compromise because there are some devices which may not be able to handle this kind of high density images. So let's run this code in Python notebook. Alright, so let's apply the same technique for another picture which is even more intricate and has probably much complicated color schema. So this is the image. Now once again, we can take a look at the shape, which is 427 by 640 by 3. And this is the new data would look somewhat like this compared to the flower image. So we have some new values here, and we will also bring this. As you can see, the numbers are much big, so we will much bigger, so we will now have to scale them down to values between 0 and 1, and that is done by dividing by 255. So let's go ahead and do that and reshape it. Okay, so we get a two-dimensional matrix, and we will then, as a next step, we will go ahead and visualize this, how it looks, the 16 colors. And this is basically how it would look, 16 million colors. And now we can create the clusters out of this. The 16 k-means clusters we will create. So this is how the distribution of the pixels would look with 16 colors. And then we go ahead and apply this and visualize how it is looking for with the new, just the 16 colors. So once again, as you can see, this looks much richer in color, but at the same time, and this probably doesn't have, as we can see, it doesn't look as rich as this one, but nevertheless the information is not lost, the shape and all that stuff. And this can be also rendered on a slightly a device which is probably not that sophisticated. Okay, so that's pretty much it. So we have seen two examples of how color compression can be done using k-means clustering. And we have also seen in the previous examples of how to implement k-means, the code to roughly how to implement k-means clustering. And we use some sample data using blob to just execute the k-means clustering.
Hey everyone, welcome to this live session by Simplilearn. In today's session, we will take you through the most debated topic that has taken the world by storm. Yes, you guessed it right, we are talking about coronavirus. But before we proceed, make sure to subscribe to our channel and hit the bell icon to never miss an update. In this session, we will learn about what coronavirus really is, how did it emerge, and what are its symptoms. Then, we will see what has been its impact so far in terms of the total cases emerging, the total number of deaths reported, and the total number of recoveries across the globe. We will analyze the outbreak of coronavirus across different regions, visualize them using charts and graphs, and predict the number of upcoming confirmed cases for the next 10 days, that is, between the 16th of March to the 25th of March using linear regression model and support vector machines in Python. Finally, we'll look at the various safety measures that you can take to save yourself from getting attacked by coronavirus. Before we begin, let me clarify that this video majorly focuses on how you can use machine learning algorithms to make predictions on such sensitive issues. We will certainly cover the current scenario and the impact it has created worldwide, but there is nothing to panic at all. Make sure you take all the necessary precautions to stay safe. Also, the predictions may vary from the current situation that you see, as the data was taken from Kaggle that may have some variations. This is only to make you learn how you can perform analysis on such datasets and derive insights from the prediction. So let's start with what is coronavirus. Coronaviruses, first discovered in 1960s, are a family of viruses that cause illness ranging from common cold to severe diseases such as Middle East Respiratory Syndrome and severe acute respiratory syndrome. Coronaviruses can be transmitted between animals and human beings, and hence they are zoonotic. Now let's see how coronavirus emerged. In December 2019, the city of Wuhan in Hubei province, which is China's 7th largest city, comprising 11 million residents, became the center of a pneumonia outbreak of unknown cause. The Chinese health authorities conducted an immediate investigation of these cases to identify and control its spread by isolating suspected patients, closely monitoring their contacts, and obtaining detailed clinical and epidemiologic data. The source of coronavirus 2019 or COVID-19 is believed to be a wet market in Wuhan which sold both dead and live animals including fish and birds. Let's see the symptoms of coronavirus. COVID-19 is characterized by symptoms such as cold, cough, running nose, sore throat, and fever. Illness can be more severe for some people and can lead to pneumonia or breathing difficulties. Older people and people with other medical conditions such as asthma, diabetes, or heart disease may be more vulnerable to becoming severely ill. The novel coronavirus is now a public health emergency of international concern. People across the globe are racing to cut short their vacations and rebook flights home as most countries continue to lock down cities and towns amid the spread of coronavirus. As per the World Health Organization, till the 15th of March, the total deaths reported globally stood at 5,735, while more than 100,000 people were infected worldwide. On the 11th of March, the World Health Organization declared COVID-19 as pandemic. On the screen, you can see the total coronavirus cases till the 13th of March across the globe. Most of the countries have been affected by the spread of coronavirus. China, South Korea, Iran, Italy, France, Spain, and Germany are some of the countries that got hit the most. Next you see China, Italy, Iran, and the United States of America have the highest number of deaths reported till the 13th of March. The next map shows you the total recovered cases across different parts of the world. China, Italy, Iran, and South Korea have the most number of patients who have recovered. Now, let's move on to the most important part of this video, where we will analyze the outbreak of coronavirus cases across different countries and visualize them using different charts and graphs. The data has information from the 22nd of January till the 15th of March. Using this data, we will predict the upcoming cases for the next 10 days, using algorithms such as linear regression and support vector machines in Python. Now let me go ahead and show you the datasets that we will be using for this analysis. So for this analysis, we'll be using three CSV files. So here you can see I have opened all the three files. The first data set is regarding the confirmed cases. It has columns such as province or the state, country or the region, latitude, longitude, and the number of confirmed cases that came up in all these days. Similarly, the second data set is regarding the deaths of patients between 22nd of Jan till the 15th of March. And the third data set is regarding the number of recovered cases during the same time interval. Now, let's start with understanding the code for this demo, where we will use support vector machine and linear regression to build our model and predict the total number of confirmed cases that may come up in the next 10 days. Again, to clarify, our prediction may vary from the current scenario that you actually see, since this data set was taken from Kaggle, which is usually for learning purposes. I have already implemented the code on Jupyter Notebook. I'll run through each cell of code and explain to you what it does. First, we will import all the necessary libraries that are important for this analysis. As you can see, we are importing libraries such as Numpy and Pandas that are used for numerical computations and manipulations. Then, I'm importing Matplotlib library for visualizing the data and the model, followed by math and time. After that, from the sklearn library, I'm importing certain functions such as train test split, SVR to build the model, and so on. We are also using metric functions such as mean squared error and mean absolute error and so on. Now let me run this cell by hitting Shift plus Enter. We have successfully run that cell. Now we will load all the three datasets one by one. For that, I have used the pandas library and read_csv function, which you can see here. I have provided the location of the file followed by the file name and the extension of the file, which is .csv. I've loaded all the three datasets into three variable names. Now let me run all the three cells to import all the three datasets. I'll hit Shift Enter. Scroll down. We'll load the deaths dataset and the recovered dataset. Now to display the datasets, I'm using .head function to see the top 5 rows from the data. You can see the top 5 rows from the confirmed_cases dataset. Similarly, you can check the top 5 rows from the reported dataset, from the deaths reported dataset, and from the recovered cases as well. After that, I'm extracting all the column names from the confirmed cases data frame using the .keys function. Let me run it. So below you can see all the columns being displayed. Then we are extracting only the date columns that have information of confirmed cases, death cases, and recovered cases using the .loc function. The first parameter, that is colon, tells you we need all the rows, while the second parameter tells you that we need data from the fourth column till the last column, which are the date values. Now let me run all the three. Now you can go ahead to see the outbreak cases using confirmed.head. Here you can see it has only the date columns and the values for each of the dates. After that, in the next cell, I am finding the total confirmed cases, death cases, and the recovered cases and appending them to 4 empty lists. We are also calculating the total mortality rate, which is nothing but the total death sum divided by the total confirmed cases. You can see I have declared 4 empty lists, namely world cases, total deaths, mortality rate, and total recovered. Then I'm running a for loop taking the date variables into consideration. So for each of the date values, we are summing the total confirmed cases, the death cases, and the recoveries. After that, I'm appending the values to the 4 empty lists that we had created. Now let me run it. Moving ahead, let me display each of the newly created variables one by one. So if I run confirmed underscore sum, you can see the total number of confirmed cases, which is nearly 1,67,449. Now if I run this one, it will tell you the total number of deaths that have been reported, which is 6,440. And the total number of recoveries stand at 76,034. Similarly, if I run world cases, you can see this kind of an array which have been listed date-wise. In the next step, I'm converting all the dates and the cases in the form of a Numpy array using np.array function. Let me run it. Now I can display all the newly created arrays by passing the variable names. So if I run days since 22nd of Jan, you can see it will list you the total number of days that were present from the 22nd of Jan till the 15th of March. Now if I run world cases, you can see it has an array which has values of the total number of cases that emerged between 22nd of March till the 15th of March. Similarly, if I run the total deaths variable, you can see it lists all the death values between 22nd of Jan till 15th of March. And finally, for the total recovered cases. Now since our prediction will be for the next 10 days, so I have created a variable called days in future and assigned a value of 10. Then I'm adding the last 10 days to the total number of days we have. Now let me show you the value of future forecast by running this cell. You can see below, future forecast has given us a total of 64 days. Next, we are converting all the integers into date time values for better visualization. So let's run it. Now before we start building our code, let's visualize the data using different charts and graphs and see what has been the impact of coronavirus so far. For visualization, we need the latest data of 15th of March. So I have extracted the last column values for all the three data sets. Now let me display these for you. I'll run latest underscore confirmed. You can see it gives you all the values from the 15th of March. Similarly, I'll go ahead and run the remaining. Latest deaths gives you the total deaths that were reported on 15th of March across various regions. Similarly, for the latest recoveries as well. After that, I'm finding the list of unique countries using the .unique function. If I run this, so below you can see there are different countries. So that's Thailand, Japan, Singapore, Malaysia, all the countries across the globe. So in the next cell, I'm basically calculating the total number of confirmed cases by each country. So I have created two empty lists, namely country confirmed cases and no cases. If the cases are greater than 0, I'm appending the values to country confirmed cases, else I'm appending it to no cases. Next, I'm finding the number of cases per country or region. So you can see that China has the highest number of cases, followed by Italy and Iran. Now in this cell of code, we are finding the list of unique provinces using the .unique function again. Now there are certain countries that have been marked as provinces or states, such as the United Kingdom, Denmark and France. Those we are classifying as outliers and removing them from the list. Next, we are finding the number of confirmed cases per province, state or city. So for this, we have created two empty lists, namely province confirmed cases and no cases. If the cases are greater than 0, I'm appending them to province confirmed cases, else to no cases. I'm also removing the areas with no confirmed cases. Now, you can see the total number of cases per province, city or state. So here are the values. Coming to the next cell, in this piece of code, you're basically handling NaN or missing values. Let me just run it. Okay. So now that we have done with preparing the data for visualization, let's build different charts and graphs to see what we can derive from it. First, we'll plot a bar graph to see the total confirmed cases across different countries. In the beginning, I'm giving the size of the graph using plt.figure, so we have 32 by 32 size. Then, I'm passing the unique countries in the x-axis and the country confirmed cases in the y-axis. I have given a title to this graph, number of COVID-19 confirmed cases in countries. I've also given a label for the x-axis, which is number of COVID confirmed cases. We are using plt.show that will display the graph. Let me run it. As you can see, if I scroll down, China has the highest number of cases, followed by Italy, Iran, South Korea, Spain, Germany, France, and so on. Now I'll plot another bar graph to see the total confirmed cases between mainland China and outside mainland China. For mainland China, I'm finding the sum of all the cases where country or region equal to China, while for outside mainland China, I'm taking the sum of all the confirmed cases and subtracting China cases. Let me now run it. As you can see, the total number of cases outside China is more than mainland China. Now if you want, you can also print the exact values which I have done below. So the total cases outside mainland China is around 86,446, while in China it is close to 81,000. And the overall cases till 15th of March stand at 1,67,449. Another thing I have done is to show 10 countries that have the most number of confirmed cases, while the rest of the countries I have grouped into a category named Others. So, I have created two empty lists named Visual Unique Countries and Visual Confirmed Cases. I have taken the 10 countries based on the top 10 cases, while the Others category has the remaining cases. Now, let's visualize the 10 countries using a bar graph. So this is how the graph looks like. On the y-axis, you have the different country names. You also have the Others category. And on the x-axis, you have the number of cases. You can see China has the highest number of COVID-19 cases. Italy has the second highest, while other countries in total have the third highest cases. Now the same visualization you can do using a pie chart to check the total confirmed cases in 10 different countries. I've used a color scheme CSS4 colors. I've given the figure size 20 by 20. I'm using plt.pie function and plt.legend function to show the different countries. Let me just run it. So here is how the pie chart looks like. And to the right, you can see the different legends. So this color corresponds to China, while this one corresponds to Italy. This is actually Others, and so on. Here, I have created another pie chart to visualize the total confirmed cases in 10 different countries apart from China. It has the same code as above, but under plt.py, I have passed columns apart from China, and hence we are using 1:. Similarly, under plt.legend, we have values apart from China. Let me run it. So this is how the pie chart looks like. As you can see, Italy has the highest number of cases, followed by Iran and then South Korea. We also have others in this category which has pretty high number of confirmed cases. So now that we have visualized our data, let's start by building our model using a support vector machine algorithm. Support vector machine uses different parameters to build a model. These parameters are kernel, C, gamma, epsilon, shrinking, and SVM grid. Kernel specifies the kernel type to be used in the algorithm. It must be one of linear, poly, RBF, sigmoid, pre-computed, or callable. If nothing is given, RBF will be used. C is a regularization parameter. Gamma is the kernel coefficient of RBF, poly, and sigmoid. Epsilon specifies the epsilon tube within which no penalty is associated in the training loss function. Shrinking takes Boolean values, that is true or false. SVM grid has all the values passed as parameters to it. Then, with the help of randomized search CV function, we are building a model by passing the necessary parameters. Finally, we are fitting the data using SVM search.fit function and passing xtrain confirmed and ytrain confirmed. Let me now run it. This might take some time since we have an epoch or an iteration defined. Here we have given 40 iterations. Now we have successfully run that particular cell. Now let's find the best parameters for the model. So you can see the result. Shrinking is false, kernel it has taken as poly, gamma's value is 0.1, epsilon value is 0.01, and C value is also 0.01. Now you can find the best estimator using SVM search.bestestimator function and predict the future forecast using the predict function. I'll run this. If I run svm_confirmed, below you can see the results. Similarly, svm_predict will tell you the predicted values for all the dates. Now, you can check the values of the testing data after creating the model. For that, we'll create a plot with the SVM test predicted data and the y-test confirmed data. Then, I'll print the mean absolute error and the mean squared error values. So below, you can see the graph and the error values. Then, I'll plot the total number of coronavirus cases over time starting from 22nd of Jan. I've given a title, number of coronavirus cases over time. So there are X labels and Y labels defined. Let me now run it. So here is the graph. On the Y-axis, you can see the number of cases. And on the X-axis, you can see the total number of days. By looking at the graph, you can tell after 40 days, the cases were close to 90,000, and now after 50 plus days, the cases have reached nearly 1,60,000. The next plot shows you the total confirmed cases versus the SVM predicted cases that might come up. Let me now run it. Here you can see the graph. The blue line, which is this one, it represents all the confirmed cases, while the dotted purple line is the prediction from the SVM model, which is this one. Now, we'll predict the values of the cases for the next 10 days using the SVM algorithm. Here is the output. You can see it starts from the 16th of March till the 25th of March, that is the next 10 days after 15th of March. You can see the total number of upcoming cases each day. So on 16th of March, the model predicts there will be around 1,84,000 cases. On 17th of March, we might have 1,93,000 cases and so on. Let us now see how you can predict these cases using the linear regression model. So, we have imported the linear regression function from the scikit-learn library. I have fit the model with X-train and Y-train confirmed data, which is this one. For prediction, I have used X-test confirmed data and the future forecast data. Finally, in the end, I am printing the values of MAE and MSE for this model. Let me now go ahead and run this code. Below you can see it has given us the value for mean absolute error and mean squared error. Let's now plot the confirmed values from the test data and the linear predicted data. So this is how the graph looks like. Like we did for the SVM model, we can also plot a graph to show the number of coronavirus cases over time since 22nd of Jan. I'll run this. So here is the graph. The blue line depicts the confirmed cases, while the yellow line tells the linear regression predictions. Now, I'll go ahead and predict the cases for the next 10 days using linear regression. Here, you can see the predictions. It is different from that of the SVM model, which had a higher number of cases. Now, we'll plot the total number of deaths over time. Let me run it. So as you can see from the graph, on the x-axis we have time, that is the number of days. On the y-axis we have the number of deaths. So by day 50, the number of deaths reported have crossed 5,000. In the next cell, we are plotting a graph to visualize the total mortality rate of coronavirus cases over time. I'll hit Shift Enter. So here is the graph of mortality rate of coronavirus cases over time. Then I'm plotting the total number of coronavirus cases recovered over time. As you can see from the graph, nearly 75,000 people have recovered from this pandemic. In the next plot, I'm checking the number of coronavirus cases based on deaths and recoveries. So below is how the graph looks like. The green line represents the number of recoveries and the red line represents the number of deaths. As you can see, there are a lot of recovered cases, which is good news. And finally, we are checking the total number of coronavirus deaths versus recoveries in a single plot. So here is the graph. The x-axis has the number of recoveries, while the y-axis has the number of deaths reported so far. With that, we have come to the end of the demo to analyze coronavirus outbreak globally. Now let me address a few questions that our viewers are asking related to coronavirus and about this prediction analysis. First question I can see here is how coronavirus spreads and how to protect yourself. So coronavirus spreads in a similar way to flu or the common cold, basically in large droplets produced by coughs or sneezes. Germs can live on surfaces for several hours. Public Health England defines the spread as having close contact with a virus carrier within 2 meters of the person for 15 minutes. As mentioned, there is no vaccine as of now. To protect yourself, you need to take precautionary measures such as regularly washing your hands, staying away from crowded places like malls and pubs, and using masks. Another question which I can see on the chat window is who started the coronavirus? To be honest, there are a number of crazy conspiracy theories that have been circulating that the virus somehow escaped from a Chinese lab, either by accident or design. However, this is categorically untrue, and scientists studying its genetic code have linked it to bats. It probably then jumped to other animals, which passed it on to humans. One more question is, can we use time series analysis and other type of algorithms to make predictions of the cases? Of course you can. You can use time series analysis to predict the upcoming cases. But it would be recommended for you to have individual data from different countries. You can also use algorithms such as Bayesian ridge and logistic regression. There's another question, can we also predict the death cases and the recovered cases for the next 10 days? Surely you can predict both the parameters. You just need to provide the total deaths and the total recovered cases information to the splitting step, where we are dividing the dataset. With that, I think we have covered most of the important questions related to this topic. Machine learning is the future, and yours can begin today. Comment below with your email ID to get our latest machine learning career guide. Let your journey begin. Finally, it's our duty to tell you the important safety precautions that you can take to ensure you are not suffering from the spread of coronavirus, since there is no coronavirus vaccine yet. So here are the measures that you can follow. Clean your hands often with soaps and sanitizers. Avoid close contact with people who are ill. Always wear a face mask when you are out. Practice respiratory hygiene. Please avoid gathering in crowded places. Do stay at home if you are sick. And most importantly, seek medical care early if you have fever, cough, or difficulty breathing. And with that, we have reached the end of this session. Welcome to another live session by Simplilearn. I would like to thank you all for actively participating in these sessions on YouTube and Facebook. Today, we will understand how to perform stock market prediction using machine learning. So what really is stock market? A stock market is a place or a public market where you can buy and sell shares for publicly listed companies. The stocks, which are also known as equities, represent ownership in the company. The stock exchange is the mediator that allows the buying and selling of shares. Amsterdam Stock Exchange is the oldest stock exchange that were established in 1602. The top stock exchanges in the United States are the New York Stock Exchange, Nasdaq, American Stock Exchange, and Chicago Board Operations Exchange. In India, we have the Bombay Stock Exchange, or the BSE, that was established in 1875 and it's Asia's first stock exchange. We also have the National Stock Exchange, or NSE. Now, let's understand the importance of stock market. Stock markets help companies to raise capital. If stock markets did not exist, then companies would have to resort to borrowing loans from the banks to raise money for expansion. This would be a trouble for the company, as they would have to repay the loans with interest. With stock markets, companies have the free hand to create an initial public offering and raise large amounts of cash without having to worry about repayment. Another reason why the stock market is important is it helps generate personal wealth. For an individual investor, the stock market provides a platform to invest your income and earn a share of the company's profit. Stock markets serve as an indicator of the state of the economy. That is, the stock market serves as a barometer for the economy. A rise or fall in the prices of shares indicates what cycle the economy is in, such as a recession or a boom. The stock market is considered to be one of the most widely used sources for people to invest money in. Investors are always looking to invest in companies with high growth potential. If the stock market is performing well, this increases investment from local investors. It also attracts foreign direct investment as people abroad invest in the local stock exchange. With that, let's now understand stock market prediction. Stock market prediction helps you determine the future value of company stock and other financial instruments traded on an exchange. The whole idea of predicting stock prices is to gain significant profits. Predicting how the stock market will perform is a difficult task to do. There are a lot of other factors involved in the prediction, such as physical and psychological factors, rational and irrational behavior, etc. All these factors combine to make share prices dynamic and volatile. This makes it very difficult to predict stock prices with high accuracy. So we will use machine learning techniques to predict the stock prices of two different companies, Tesla and Google. We'll be using linear regression algorithm and long short-term memory networks for building our prediction models. So first, let's understand the basics of linear regression. Linear regression is a very popular statistical technique used for solving machine learning problems. It is a supervised learning algorithm for predicting the output of a continuous target variable. It can be used to predict the total revenue of a company or the total units expected to be sold of a certain product. It can also be used for weather prediction and stock price prediction. Now here is an example to predict the total number of ice creams a vendor or a company can sell based on the temperature of the day. You can see the green dots represent the actual data points. So the x-axis has the input variable, that is temperature, and the y-axis has the target variable, that is units sold. Linear regression uses the linear equation formula y is equal to mx plus c, where m is the slope of the line, c is the intercept. We find the coefficients and plot the regression line. So in this graph, the red line is our regression line. The best fit line should have the least square distance between the original data points and the predicted values. Now, let's see how to predict the stock prices of Tesla using the linear regression model. So this is the CSV dataset that we will be using for our prediction. We have information from the 29th of June 2010 till the 15th of May 2019. Here, open column means the price at which a stock started trading when the market opened on a particular day. The close column refers to the price of an individual stock when the stock exchange closed market for the day. It represents the last buy-sell order executed between two traders. The high column is the highest price at which a stock traded during a period. The low is the lowest price of the period. Volume is the total amount of trading activity during a period of time. The adjusted closing price is a calculation adjustment made to the stock's closing price. It is more complex and accurate than the closing price. The adjustment made to the closing price depicts the true price of the stock because the outside factors could have altered the true price. Now before I begin the demo, I want to tell you that if you want to get a copy of the source code files and the datasets that I'll be using in this session, then please put your email IDs in the chat section of the video. Also, please subscribe to our channel and hit the bell icon to stay updated with all the latest trending technologies. So here is my Jupyter notebook where I have implemented my linear regression code. So I'll run through each cell of code and explain what it does. First, we'll import the necessary libraries for building our model. So I'm importing pandas, numpy and matplotlib for numerical computation, data manipulation and data visualization. We'll also import the plotly library for building our graphs. Now, if you are using Plotly for the first time, you'll have to install it and then import it onto Jupyter. Let me run this cell. So I have successfully imported all my libraries. Next, I load the Tesla stock price dataset using the pandas library and the read_csv function. I'll also give the location where my CSV dataset is present. Now let me import the dataset. I'll hit Shift Enter. So now I have successfully imported my dataset. Now let's see my datasets. For that I'll use the head function. I'll write Tesla.head. So this will return the top 5 rows from the dataset. In the next cell, I'm using the info function to find the total rows and columns in my dataset. The info function will also return the data type of the variables and check if there are any null values. There you go. So we have total 7 columns and there are 2193 entries. Here you can see the data type of each column and each column has non-null values. Moving ahead, in the next step, we are converting the date column into datetime format using pandas library and to_datetime function. Up next, let's do some exploratory data analysis and get more insights from our data. I'm using the print function and a formatted string literal, that is f. These strings contain replacement fields which are expressions delimited by curly braces. You can see here. Here I'm finding out the data frame contains stock prices between what dates and the total number of days. So the total number of days can be calculated by subtracting the maximum date value and the minimum date value. So let me go ahead and run it. You can see our stock prices are from 29th of June 2010 till 15th of March 2019, and the total number of days are 3181 days. Now let's see some summary statistics for our data using the describe function. So the describe function gives you the count, mean, standard deviation, the maximum and minimum from each column, the 25th quartile, the 50th quartile, and the 75th quartile. Let me now go ahead and create a box plot to visually check our outliers. I'm considering 5 columns: open, high, low, close, and adjusted close. So this is how our box plot looks like. In this cell, we'll plot a graph using the Plotly library that we have imported. We are setting the layout for our graph using the go layout function. I'm providing a title to the graph. I'm also setting my x-axis for giving the title. So the x-axis will have the date column. You can see it here. We're also defining the title font, the family, size, and color. Similarly, I'm providing the layout for the y-axis. You can see it here. Finally, I'm passing my data list and the layout created to plot variable. Let me go ahead and run it. Now I'll plot my graph using the iplot function. There you go. So we have the stock prices of Tesla plotted in this graph. On x-axis, we have the year from 2011 till 2019, and on the y-axis, you have the price, which is basically the close column. You can see from the graph that initially during 2011 or 2010, the stock prices were growing a little lower than expected, but towards 2015, 16, and 17 onwards, the stock prices grew higher. Now, coming to the most important part, that is to build the linear regression model. So in this cell, I'm importing the necessary libraries and their respective functions. First, I'm importing the train_test_split function from the scikit-learn library. Next, I'm also importing some pre-processing functions like min-max scaler and standard scaler from sklearn library. Also, for evaluating the model and finding the accuracy, we'll use the mean squared error and R squared error from scikit-learn matrix library. Let me run it. So we have successfully imported our required libraries. Moving ahead, in the current step, we are splitting the data into training and testing sets. The x variable contains the independent features and the y variable has the dependent variable or the target variable, that is close column. I'm taking the test data size as 0.3 or 30% of the total, and I'm assigning a random state of 101. Let's run it. Okay. Now, I'll perform feature scaling on the xtrain dataset. For that, I'm using the standard scaler.fit function and passing in my xtrain data. Standardization of a dataset is a common requirement for any machine learning algorithm. They might behave badly if the individual features are not normally distributed. So that's why feature scaling is important. With that, it's time for us to import the linear regression function from the scikit-learn library. Now, using a variable lm, which stands for linear model, I'll declare a linear regression function, and then I'll use the fit method to pass the training datasets, that is xtrain and ytrain. So let me run it. Now we have successfully created our linear regression model. Next, we'll plot the graph for actual and predicted values for the training dataset. Here, we'll be creating a scatter plot and draw our prediction line. So I have used the go.scatter function. I'm using markers for plotting the actual data points, and I have used a line to draw the prediction line. Let me run it. Now to plot the graph, I use the iplot function. If I scroll down, you can see on the x-axis we have the day column or the day variable, and on the y-axis we have the prices of our stocks. The blue dots represent the actual stock values. If I hover over these blue dots, you can see the actual values, and the red line is a predicted regression line. The final step will calculate the scores for evaluating our model. So here we are using two matrices. One is r-squared error and mean squared error. For finding the r-squared error, we have used r2_score function, and I'm passing my ytrain as well as xtrain using the lmpredict function. Similarly, for finding the r-squared error for testing dataset, I'm using ytest and lmpredict for xtest. Likewise, to find the mean squared error value, I've used the ytrain and ytest data along with predicted xtrain and xtest data. Now let me run it. Below you can see the two matrix scores. So our r-squared error score is around 0.86 for the training set, and it's around the same value of 0.86 for testing data set, and similarly you can see the mean squared error as well. With that, you saw how to predict the Tesla stock prices using linear regression model in Python. If you want to get a copy of the source code files and the datasets that I'm using in this session, then please put your email IDs in the chat section. We'll share the files over email. Also, please subscribe to our channel and stay updated with all the latest technologies. Now, we will understand about long short-term memory networks. So LSTMs are a type of recurrent neural networks for learning long-term dependencies. It is commonly used for processing and predicting on the basis of time series data. From the image on the left, you can see LSTMs have a chain-like structure. Instead of having a single neural network layer, there are 4 interacting layers communicating with each other in a very special way. Now LSTMs work in a 3-step process. The first step in LSTM is to decide which information to be omitted from the cell in that particular time step. It is decided by the help of a sigmoid function. It looks at the previous state, that is ht-1, and the current input state, that is xt, and computes the function. In the second layer, there are 2 parts. One is the sigmoid function and the other is the tanh function, or the hyperbolic tangent function. In the sigmoid function, it decides which values to let through, that is 0 or 1. The hyperbolic tangent function gives the weightage to the values which are passed, deciding their level of importance from -1 to +1. In the third step, it decides what will be your final output. First, it will run a sigmoid layer which decides which parts of the cell state make it to the output. Then, we put the cell state through the tanh function to push the values to be between -1 and +1, and multiply it by the output of the sigmoid gate. Now let's go to our Jupyter notebook and implement a long short-term memory network to predict the stock prices of Google. Before that, let me first show you the dataset that we will be using. So this is my Jupyter lab, and on the left you can see we have our Google datasets. So we will be using two datasets for this demo, a training dataset and a testing dataset. Let me show you how the training dataset looks like. I'll open with CSV table. So this is our training dataset of Google. It has the same columns like date, open, high, low, close and volume. And if I scroll down, you can see we have data from 2012 till 2016. Let me close this. Now let me open my Google test dataset. So this is my test dataset, and we'll be using this dataset to evaluate our model. So first, let me go ahead and import all the libraries that we'll be needing to build our LSTM model. You can see I'm importing the Numpy, Pandas and Matplotlib library for numerical computation, data manipulation and data visualization. We are also importing min-max scalar function from scikit-learn preprocessing library. Then we have some built-in functions from the Keras library, such as sequential to analyze a sequence of data, then dense, LSTM and dropout to measure the dropout rate. I'll hit Shift Enter to run this cell. You can see it says we are using TensorFlow backend. Now let me go ahead and import the Google training dataset using read_CSV function from Pandas. I have imported my dataset. Now if you want to check the head of the dataset, you can use data.head. Run again. So it will display the top 5 rows from the dataset. Similarly, now let's see the total rows and columns we have in this dataset and the data types of each variable. We'll use the info function for this. You can see this is my output. So we have a total of 6 columns and 1258 entries. And here you can see the data type. So date it has taken as object, open it has taken as float, high it has taken as float. Similarly, close and volume column it has taken as object. Now we will do some pre-processing of data to transform our closing price variable to a numeric type. Drop the non-available data and keep only the close column for training the data. Now to convert the close column into numeric, I have used pd.to_numeric function. Now to drop my missing values, I have used drop any function. And similarly, to consider only closing column as my training data, I am using iloc or index location. Now let me run it. Now let's once again see the data types. If I scroll down, you can see we have changed the close column data type to float. Earlier it was object, now it's float. Next, we will rescale our data into values between 0 and 1 for better performances. For that, you can use the min-max scalar function and give the range. Then I have used fit_transform method to transform the values. And then I am also printing the shape of my training data. Let me run it. Now we will prepare our data for training. First, we need to prepare our input sequences with 60 time steps of X train data alongside the respective Y train labels. Next, we'll be adding another axis for the batch size, since the input for an LSTM network is a 3D tensor, so it will have a sequence length, the time steps and batch size. Now, we'll build a model containing 4 layers of LSTM network, all followed by a dropout layer. On the top, we'll also have a final dense layer, which is this one. All of this compiled using an Adam optimizer and a mean squared error as a loss function. Let me run it. Next, I'll train the data using 20 epochs and batch size of 32 using the model.fit function and passing my xtrain and ytrain data. This will take some time to run since it will complete 20 iterations. So you can see it has started with first epoch and it will run for 20 epochs. Now we are into our second epoch. You can see the loss that was incurred during the training of the first epoch. Meanwhile, when our model is getting trained, if you have any questions, please put it in the chat section. You can see we have completed our fifth epoch as well. Now we are into our seventh epoch. Now we have entered our 15th epoch. Now we are almost about to finish our training. We have entered into our final epoch now. I think we have successfully completed training our model. Next, let's visualize the loss that was incurred during the training process for each epoch. I'm using the matplotlib library and the plot function. I have given a title to my visualization. I've also defined my x labels and y labels. So below you can see this is how the graph looks like. On the top you can see the title, that is training model loss. You can see the loss has been a steep decline. With that, let's test the model using a new dataset. We'll continue with the same steps of importing the dataset. So you can see I'm using the read_csv function to import my test Google dataset. Then we'll convert the close column into a numeric type. I'll then drop the missing values and select the closing price columns for testing. Next, I'm selecting the labels for white test data. Finally, we are providing the input array for the model and converting the x-test data into a Numpy array and printing its shape. Let me hit Shift Enter to run it. In the next cell, I am predicting the model output using the model.predict function and passing the x-test data. So let me run it. Now if you want to check the values of y prediction, you can just give the variable name and hit Shift Enter. So these are my values. It's not in a proper order or a proper format. Now, to plot the data between actual and predicted stock prices, we'll use the inverse underscore transform function over ypred data. And finally, we'll plot the graph in order to visualize the actual stock price and the predicted stock price. I'm using the matplotlib library and I'll pass in the data. We're also providing a title to the plot, the X labels and the Y labels. So this is how the graph looks like. On the x-axis you have time and on the y-axis you have the stock price. The red line indicates actual stock price while the green line indicates the predicted stock price. With that, we have successfully created our model and predicted the stock price values using long short-term memory networks. If you have any questions, please put it in the chat section. We'll be happy to help you. Hi everyone. Welcome to this really interesting video on data analysis of the 2021 World Happiness Report using Python. So today we will perform some exploratory data analysis using Python libraries to analyze, visualize and draw insights from 2021 World Happiness data. Before I begin, make sure to subscribe to the Simplilearn channel and hit the bell icon to never miss an update. First, let's understand what the World Happiness Report 2021 is all about. The International Happiness Day is celebrated every year since 2013 on 20th of March to emphasize the importance of happiness in the daily lives of people. So the United Nations Sustainable Development Solutions Network published the World Happiness Report on 19th of March 2021 that ranks the world's 149 countries on how happy the citizens perceive themselves to be based on various indicators. The happiness study ranks the countries on the basis of questions from the Gallup World Poll. The results are then equated with other factors such as GDP, life expectancy, generosity, etc. This year it focused on the effects of the COVID-19 pandemic and how people all over the world have managed to survive and prosper. So using this 2021 data, we will answer critical questions such as the top 10 most corrupt countries. We will plot a graph to understand how the happiness score is related to the freedom of making life choices. We'll look at the life expectancy of 10 happiest and 10 least happy nations. So these are a few examples, but we will explore more about the data in detail in our demo session. Let's get started. So first I'll show you the data set we'll be using in this demo. So this data has been collected from Kaggle. Let me show you that. So this is the CSV dataset that we have downloaded from Kaggle.com. So you can see here World Happiness Report 2021, and we will share the dataset link in the description of the video. You can click on the link to download the dataset. Now we have information about 149 countries. You can see it here. Count is 149. Let me go to the top and I'll run through the columns that are there in this dataset. So the first column is the country name. So we have 149 different countries, and then we have something called as regional indicator. We can call this as just the region. So you can see we have different regions. I've applied a filter. We have Central and Eastern Europe. Then we have Commonwealth of Independent States. So these include countries such as Russia. Then we have East Asia, Latin America and Caribbean. We also have South Asia, Southeast Asia, Sub-Saharan Africa, Western Europe and other regions. I'll just cancel this. And then we have the happiness score column that has been sorted in descending order. So we have Finland, Denmark and Switzerland, who are the top 3 happiest nations. Now if I scroll down, we have countries like Rwanda, Zimbabwe and Afghanistan, which are the least 3 happy countries. Now there are a few columns that we won't be using in our analysis, so we will learn how to exclude those columns and keep only the relevant ones. So columns such as standard error of ladder score, then we have upper whiskers and lower whisker column. So we are going to ignore these columns. We are only concerned about the GDP column, which is this one. Then we have the social support or the social status column. Then we have the health life expectancy, freedom to make life choices, generosity, and perceptions of corruption. And there are a few other columns you can see to the right, and these columns are not of our interest, so we are going to ignore them. Now let's head over to our Jupyter notebook, and we'll start by importing all the necessary libraries for analysis and data visualization. Okay, so I'm on my Jupyter notebook. So first step, I'll just rename this notebook to, let's say, happiness report data analysis. I'll click on rename. Alright, now we'll start by importing our libraries. So first library I'm going to import is Numpy as NP. Then I have import pandas as PD. Then I'll import two data visualization libraries, Seaborn and Matplotlib. So I'll say import Seaborn as SNS, and then import Matplotlib dot pyplot, which is the module name, as PLT, and I'll say percentage matplotlib inline. Okay, now let me just go ahead and run this. Alright. Well, now let's set the parameters that control the general style of the plots. The style parameters control properties like the color of the background and whether a grid is enabled by default or not. So for that, I'll say SNS dot set underscore style. I'll give it as dark grid. Next, I'll say plt dot rc params, which stands for runtime configuration parameters. I'm going to set my font size to, let's say, 15. Then I'll say plt dot rc params. Now I'm going to set the figure size, so I'll say figure dot fig size. Let's say 10,7. Next, I'll just copy this, paste it here. Now we are going to set the face color, so I'll say figure dot face color. I want to set it to peach color, so I'm going to pass in my RGB values for peach. I'm going to set it in terms of hex code. So for peach, the value is FF E 5B and 4. Now let me run it. Okay. Now it's time to load our data set. So for that, I'll create a variable called data, and I'll use the pandas library followed by the read underscore CSV function, because our data set that we saw is a CSV data set, which is this one. Now inside the parenthesis, I'll pass in the location of my data file. So I have my data here, World Happiness Report 2021. I'll just copy this location and will paste it here, and make sure the location is within quotes, and you need to change it to either / or double backslash. So here I'm using double backslash, so let me just include one more backslash, and then I'm going to pass in the file name, which is world happiness report 2021.csv, which is the extension of the file. Now let me run it. Alright, now to display the first 5 rows of information, you can use the head function. So I'm writing data, which is my variable that holds the data frame. So data.head, there you go. You can see here we have printed the first 5 rows from the dataset. You have the country name, regional indicator, happiness score. Then we have information about the GDP, life expectancy, generosity. Then we have corruption data, and these are some of the columns that we are not bothered about. So we are going to drop these columns from our analysis. Now we are going to do that. So I'll create a variable called data columns, which are of our interest. So I am going to take only specific columns. I need the country name, so I have taken country name. Make sure the column names are within single quotes. So I have my country name. Next I want the second column, which is regional indicator. Give a comma. We also need the happiness score. Next I need the logged GDP per capita data. So I'll take that column. I'll say logged GDP per capita. Give a comma. My next column would be social support. Give a comma here. My next column would be health life expectancy. So I'll write health life expectancy. Let's give another comma, and we'll take the next column as well, which is freedom to make life choices. So I'll write that column name, freedom to make life choices. And finally we'll take the next 2 columns, that is generosity and perceptions of corruption. So within single quotes I'll say generosity, give a comma, and we're going to include the final column which is of our interest, that is perceptions of corruption. Let me have a recheck to ensure that I have put the column names correctly, otherwise it will throw an error. Now let me go ahead and run this cell. I'll hit Shift Enter. Alright, so we have successfully taken the columns that we'll be using for an analysis. Now I'm going to say data equal to data. I'll pass in my new variable, that is data underscore columns, and I'm going to copy all the data. So I'll say dot copy. Let's run it. Okay, this should be data underscore columns. Alright, now let's rename all these columns. We'll make it more simpler and easy to understand. So I'll say, let's say my new variable is happy underscore dir, which stands for data frame, equal to, I'll say data dot, we'll use the rename function, and using a dictionary we will rename our columns. So I have used a curly bracket. I'm going to pass in my first column, which is country name. I'll just paste it here. Then I'm going to give a colon, and again within single quotes I'll say country underscore name. So this is going to be my new column name. I'll give a comma. We'll take the next column, which is regional indicator. I'll paste it here, give a colon, and the new column would be small r regional underscore indicator. Now similarly we'll do this for all the remaining columns in the dataset. Okay, now I have renamed all my columns. You can see it here. Let's run it. Now we are going to display the head of the dataset again. So I'll say happy underscore df dot head. There you go. So we have only those columns that are of our interest. So I have the country name, regional indicator, happiness score, GDP, social support, life expectancy, freedom to make life choices. Then I have generosity and perceptions of corruption. Cool. Now we are going to check whether any of the columns have any null values. So for that I'll say happy underscore df dot, I'm going to use the isNull function. I'll give another dot and we are going to find the sum for each of the columns. You can see from the data we do not have any null values in any of the columns in the dataset. It is all 0. Okay, now let's get started with our first visualization. That is, we'll create a plot between happiness score and the GDP for different regions. So for that I'll give a comment as plot between happiness and GDP. I'll just scroll down. Cool. First I'm going to set the RC parameters. So I'll say plt dot RC params. Within square brackets I'm going to give my figure size. So I'll say figure dot fig size equal to, let's say my figure size is 15,7. I'll set the title, that is plt dot title of my plot, to, let's say, plot between happiness score and GDP. Next I'm going to say SNS dot, let's create a scatter plot. So I'll say SNS dot scatter plot. I'm going to define my x-axis and the y-axis for the plot. Let's say in the x-axis we have my data frame happy underscore df dot, this should be an underscore. I'll say a column name as happiness underscore score, give a comma, and in the y-axis we'll have my data frame name, that is happy underscore df dot, we'll have the GDP column, that is logged underscore GDP underscore per underscore capita. Let's give a comma and we'll pass in hue for the color. Let's say for hue I'm going to use the regional column or the regional indicator column. So I'll say happy underscore df dot regional underscore indicator. And then I'm going to give the size of the dots as, let's say, 200. Then I'll give a semicolon. Come to the next line. I'll say plt dot, let me just scroll down. Now we are going to define the legend. So I'll say plt dot legend, and in legend we'll have the location. Let's say I want to put the legend at upper left corner. So I'll say LOC, which is for location, equal to upper left, give a comma, and then say font size of my legend, let's say be 10. Make sure this is within quotes. Then I'm going to pass my x-axis labels and the y-axis labels. So I'll say plt.x label. Let's say the x label is happiness score and my y label is GDP per capita. So I'll say plt.y label. Within single quotes I'll say GDP per capita. There's an error here. There should be plot. Alright, so I have written my code to create a scatter plot. Let's run it and see the result. There is some error here. Okay, this should be regional indicator and not indicatory. There's a spelling mistake. Let's run it again. Alright, so here you can see we have a nice scatter plot. On the top you can see we have the title of the plot, that is plot between happiness score and GDP. On the x-axis we have the happiness score from 0 to 8 and above, and on the y-axis you have the GDP per capita. And if you see here, in this region we have countries from Western Europe which have the highest happiness score and the GDP per capita is also the highest. Around this region you can see here, which is for green, and in the legend you can see green is for Sub-Saharan Africa. So all these countries have low happiness score and even the GDP per capita is also low. And if you see the countries for Latin America and Caribbean, you see a lot of the values lie here. So they are all within the range of 5.5 to 7 in happiness score, and even the GDP per capita is more than 9 for most of them. Now even the happiness score is high for the countries that lie in the North America and ANZ region, and even their GDP per capita is also the highest. I can name a few countries such as Australia, New Zealand. We have Canada and United States of America, which belong to the North America and ANZ region. Cool. Now there is one country which you see here. This seems to be like an outlier, which means that this is the country which has the lowest happiness score and even the GDP per capita is also low, but it is not the lowest, because you can see here there are a few countries up here from the Sub-Saharan Africa which have the lowest GDP per capita, but the happiness score is higher than this value or this country. So we can assume that this country is Afghanistan, which has the lowest happiness score as per the 2021 happiness report data. Cool. Now we'll plot a pie plot to understand the GDP by region. So by this we can know which region has the highest percentage contribution to the world's GDP as per our data. So for that I'll create a variable GDP underscore region equal to, we'll use our data frame, that is happy underscore df dot, I'm going to use the group by function, and after that I'm going to use my column, that is region. So we have named the column as regional underscore indicator, so I'm going to group it by this region column, and I'm going to sum the values of GDP. So I'm going to use the logged underscore GDP underscore per capita column, and after that I'm going to use the sum function, and let me just print GDP underscore region. You can see it here, we have the sum of all the countries for different regions and their GDP all total. Now this data we are going to plot it in the form of a pie plot. So I'll say GDP underscore region dot plot dot pi. We are going to plot it in terms of percentage, so I'm going to use a parameter called AutoPCT equal to, then I'm going to pass in my format, so I'll say percentage 1.1 f percentage, then I'll say plt dot title. Let's see, the title of my pie plot is going to be GDP by region, and I'll say plt dot y label, which is going to be blank. Let's run it. Okay, so here you can see we have the peach background at the back because we had assigned a peach face color. You can see it here. So for the first scatter plot also we had the peach color at the back, and now you can see we have Sub-Saharan Africa contributing 20.7% to the world's GDP. The reason being we have around 34 countries in the Sub-Saharan Africa, and we have the Western European countries contributing to 16.2% of the GDP. To check the least, we have North America and ANZ region because we only have 4 countries: America, Australia, Canada and New Zealand. So hence they are contributing only 3.1% to the world's GDP. Okay, now moving ahead, let's find the total number of countries in each region. So for this we are going to use the group by function that is part of the pandas library, and we'll count the total number of countries in each region. So I'll just give a comment as total countries. Alright, just scroll down. So I'll create a variable called total underscore country. I'm going to use my data frame that is happy underscore df dot. I'm going to use the group by function. I'll group the values based on the region column. So within single quotes I'll say regional underscore indicator, and then I'm going to find the total count of country names. So I'm using the column country underscore name, and after that I'll just use dot count. Now let's go ahead and print my variable that is total underscore country. Alright, now let me hit shift enter. Okay, so here you can see, alright, so for Sub-Saharan Africa there are total 36 countries and not 34 as I mentioned earlier. So hence you can see, because it has the highest number of countries, it is contributing the most to the world's GDP, that is 20.7%. Then we have the least number of countries in North America and ANZ, that is only 4. We have 6 countries in East Asia, and then we have 20 countries in Latin America and Caribbean, 12 countries in Commonwealth of Independent States, then we have 17 countries in Central and Eastern Europe. Cool. Now I'm going to show you how to create a correlation map so that we can see the relationship that exists between each of the variables that are present in our dataset. I'll just run through the code and we'll see the output. Okay, so here I have my code written for the correlation map that I want to create. So first of all, I'm going to compute the correlation matrix. So I have used the CORR function, which stands for correlation, and the method I'm going to use is Pearson method. Now here I have a Wikipedia page opened for Pearson correlation coefficient. So this is a nice article where you can understand what the Pearson correlation is all about. And then I'm going to set up the matplotlib figures. So I have used the subplots function and I have given the figure size as 10,5, and after that we are going to draw the heat map with the mask. So I am using the heat map function present in the Seaborn library, and then I have passed in my variable that is COR, which essentially stands for correlation. And then I have used mask, which is a Boolean array, or it can be a data frame, and it is an optional parameter. If it is passed, the data will not be shown in cells where the mask is true, and the cells with missing values are automatically masked. After that, I have used the CMap parameter, which stands for color map, so you can customize the colors in your heat map. And I'm going to create a heat map which is in square shape, so I have said square equal to true, and the axis I am going to pass it as AX, which I have defined here. So this is the matplotlib axis, and it is optional, so axis in which you want to draw the plot, otherwise you can use the current active axis. Now let me just go ahead and run this, and we'll see the heat map. There you go. So if I scroll down, here we have the correlation matrix, and since I had given my CMap as blue, and here you can see it is mostly blue, and we have the scale here. Now I'll tell you how to read this correlation matrix. So wherever the cells are in blue or dark blue color, this means that the variables have very high correlation, and all these cells where you see light blue color or grayish and white color, this indicates that the variables have very low correlation. For example, there is very low or almost negative correlation between happiness score and perceptions of corruption. So obviously, if the citizens of a country feel that there is a lot of corruption in the country, their happiness score would obviously be less or low. And if you see, there is also low correlation between happiness score and generosity. There is again low correlation between health life expectancy and perceptions of corruption. And if you see these places, there is really high correlation between the happiness score and GDP per capita. Again, for social support also there is very high correlation. Now if you see, even for social support and healthy life expectancy, there is very high correlation, but there is low correlation between making life choices and generosity, and there is negative correlation between corruption and freedom of making life choices. You can see it is almost white color, which means it falls around this region, so negative correlation. Similarly, for logged GDP per capita and corruption, there is negative correlation. Alright. Okay, now we are going to visualize a bar plot that will tell us the corruption in different regions. So I'll just give a comment, corruption in regions. Let me just scroll down. Okay, so I'll create a variable called corruption, which will be equal to my data frame, that is happy_df. Now first of all, I'm going to use the group by function to group all my regions. So I'll say regional_indicator, which is my column name present in the data set. And after this, I'm going to find the average of the corruption, that is perceptions of corruption. So I'm going to pass in my variable name, that is perceptions of corruption, and I'm going to use the mean function to find the average corruption in each of these regions. Now let me just go ahead and print my variable, that is corruption. If I run it, you can see here I have the values for the different regions, and from here you can see that Central and Eastern Europe has the highest perceptions of corruption as per the questions answered in the poll. And if you see the table, we have Western Europe and the North America region with the least perceptions of corruption. Now we are going to visualize this using a bar plot now. So first of all, I'll set my parameters by giving the figure size. I'll say fig size. It's rather figure dot fig size. I'll just add figure here. Okay, and now let's say I'll assign it as 12,8. Now I'll give a title to my plot, so I'll say plt dot title, and my title of the plot is going to be perception of corruption in various regions. Alright, then I'm going to define my X label. So I'll say X label will be regions, and we'll set the font size of the X label to, let's say, 13, or let it be 15. Then we are going to set the Y label. In Y label I'll have corruption index as the label name. Again we are going to set the font size to 15. Now I'm going to use X ticks parameter, since I want to rotate the axis labels in the x-axis by 30 degrees. So I'll say rotation equal to 30, and I'll say HA, which stands for horizontal alignment, equal to right. Make sure this right should be within single quotes. And finally I'll say plt dot bar, because I'm going to plot a bar graph. I'll say corruption dot index, comma, and then I'll say corruption dot perceptions of corruption, which is my column name. Alright, so I have my code ready for the bar plot. Now let me just go ahead and print the bar plot. Make sure everything is correct. I'll just hit shift enter. Okay, there is one mistake here. It says, okay, this should be X ticks and not X tick. Let me run it again. There you go. So if I scroll down, on the top you have the title, which is perception of corruption in various regions. On the x-axis you have the regions label, on the y-axis you have the corruption index. And if you see this, as per our table that we created, we have least corruption in North America and ANZ region. Then we have the next least corruption in Western Europe, but we have the highest corruption in Central and Eastern Europe as per their citizens' perception. Similarly, we have the second and third highest corruption in Latin America and Caribbean, as well as South Asia. Cool. Now moving ahead, I'm going to show you how you can find the life expectancy of the top 10 happiest countries and bottom 10 happy countries. So for that I'm going to run you through the code and we'll see the visualization side by side. Okay, so I have my code written in these two cells. So first I'm going to find out the top 10 happiest countries, and then I'm going to find the bottom 10 happiest countries. So for that I'm using the head function and I have passed in 10 since I want the top 10 country names, and to get the bottom 10 countries as per their happiness score I am using the tail function. So let me just run it. So we have saved the result in two variables, top underscore 10 and bottom underscore 10, and to create the bar plots we are using two different codes. So here you can see I have set my figure size and axis, and then I have my X label as country name. After that I am setting my title of the bar plot to top 10 happiest countries life expectancy. I've used my X tick labels and I'm rotating it by 45 degrees, and I have my horizontal alignment as right. You can see it here. We have used the bar plot function. I have the x-axis as country name and y-axis as healthy life expectancy column, and I have set my axis. Then I am using the X labels and Y labels as country name and life expectancy. And similarly I have my bar plot for the bottom 10 least happy countries life expectancy. Let's just run it and we'll see the result. There you go. Now if I scroll down, you can see we have two different bar plots. The first one is for the 10 happiest countries, and then we have the bottom 10 least happy countries. So if you see, on an average, the top 10 happiest countries life expectancy is above 70 years. So if you are from one of these countries, you are expected to live for more than 70 years. Now if you check the bottom 10 least happy countries, you see here Lesotho has less than 50 life expectancy age, and most of them are less than 60 years. So if you are from one of the top 10 happiest countries, you are expected to live 10 years more than these countries that lie in the bottom 10 region. Cool. Now moving ahead. Alright, so now we are going to see the plot between freedom to make life choices and the happiness score. For this I am going to use a scatter plot. So I'll first define my figure size. So I'll say plt dot rcparams, which stands for parameters. I'm going to pass in my figure size. So I'll say figure dot fig size equal to, let's say 15,7. Then using the Seaborn library and the scatterplot function, we'll pass in the x-axis. Let's say the x-axis is my data frame name happy_df, and I'll have the freedom to make life choices in the x-axis. So the column name is freedom_to_make_life and choices. I'll give a comma and we'll pass in the y-axis. Again I'm going to use my data frame name dot, and I'll have the happiness score. I'm also going to pass in a hue parameter to differentiate the different regions. So I'll say df dot regional_indicator, and I'll give the size of the dots or the bubbles as, let's say, 200. Now I'll say plt dot legend. I'll place the legend at upper left corner, so I'm giving the location, which is LOC equal to upper left, and font size, let it be 12. I'll say plt dot x label as freedom to make life choices, and my y label would be happiness score. Alright, now we have the code written for the scatter plot that I want to create. Let me just run it. There you go. So here we have the legend for the different regions, and we have the different colors for each of these regions. And you can see here I have on the x-axis freedom to make life choices, and on the y-axis we have the happiness score. So you can see it very clearly. For the countries that lie in the Western Europe region, the blue dots, the freedom to make life choices is more, and so is the happiness score. Then if you see the values in the green region, which is for Middle East and North Africa, the freedom to make life choices is lower, and hence the happiness score is also low. And for all these countries that are part of the sub-Saharan Africa, some of them have decent score for freedom to make life choices, but the happiness score is low again. Now if you focus on the pink dots, which is for the Southeast Asian countries, the happiness score is comparatively lower, but the freedom to make life choices is more than 0.8. Cool. And again we have one data point which is lying at the bottom. We can assume this is Afghanistan. So in Afghanistan the freedom to make life choices is very low, and even the happiness score is really low. Cool. Now moving to our next analysis, we are going to see the top 10 most corrupt countries. So first I am going to sort the perceptions of corruption column and find out the top 10 countries in the list. So for that I'm going to create a variable called country. I'll have my data frame name, that is happy_df dot sort underscore values by, I'm going to sort by column that is perceptions of corruption dot head, and I want to find the top 10 most corrupt countries as per the poll. And then I'm going to pass in the figure size. So I'll say plt dot rc params, and then I'm going to set the figure size. So I'll say figure dot fig size. Make sure there is no spelling mistake. Let's say the figure size is 12,6. I'll pass in the title. So I'll say plt dot title. Let's say the title of my plot is going to be countries with most perception of corruption. After that I'll say plt dot x label. In the x label I'll have country, and I'll set the font size to 13. Then I'll say plt dot y label. In y label I'll have the corruption index. Next I'll pass in the font size for the y label. Again it is going to be 13. Now I'll say plt dot x ticks. I'm going to rotate it by 30, and I'll say horizontal alignment equal to right, and then I'll have my bar function or the bar plot function. So I'll say plt dot bar. I'm going to pass in country dot country underscore name, and then we'll have my variable country dot the column name, that is perceptions of corruption. Alright, now if I run it, you can see here, so these are the countries with the least perceptions of corruption. So Singapore has the lowest corruption index, and then we have Rwanda, Denmark, Finland. Now if you want to see the countries with the highest perceptions of corruption, you need to change this head to tail of 10, since we are sorting it in ascending order. So we would want to know the bottom 10 countries. If I run it, there you go. So these are the countries with the most perception of corruption. You have Slovakia, Lesotho, Kosovo, there's Ukraine, Afghanistan, Bulgaria, Romania and Croatia. All of these countries have a corruption index of more than 0.85. Cool. Now coming to the final section of this interesting video on happiness report data analysis for 2021, I want to visualize a scatter plot that will tell us how the corruption varies in terms of happiness score. So I'll just say a comment as corruption versus happiness. Okay, so first of all I'll set my figure size. So I'll say plt.rc params. Within single quotes I'll give the figure size as 15,7. Then I'm going to use the scatterplot function that is part of the Seaborn library. In the x-axis I'll have my column that is corruption, or rather we'll have the happiness score in the x-axis. So I'll say happy_df dot column name that is happiness score. Let me give a comma, and in the y-axis we'll have the corruption column. So I'll say happy_df dot perceptions of corruption, and then in hue we'll have the region that is regional_indicator. So I'll say happy_df dot regional indicator, and I'm going to give the size of the dots. So I'll say s equal to 200. Then I'm going to say plt.legend. I'm going to put it at lower left corner this time. So I'm giving my location as lower left, and the font size of the legend I want is 14. After that I'll just say plt.xlabel as corruption and plt.ylabel as happiness score. Now this should rather be the opposite, since in the x-axis we have taken happiness score. So we'll put the happiness score label in x and I'll have corruption in y. Alright, so I have my scatterplot code ready. Let me just run it. There you go. So here you can see on the lower left I have the different regions, and on the x-axis I have the happiness score. On the y-axis I have the corruption index. Now you can see the general trend as per the scatter plot, that the countries with greater happiness score have lower corruption index. So you can see these countries which are from the Western European regions have highest happiness score, and their corruption is also really low. So all these blue countries, you can name a few: Finland, we have Sweden, we have Belgium, France, Netherlands, lying in these regions. We also have a few countries from North America and ANZ, which are essentially Australia. Then we also have Canada, US, and New Zealand. Okay, now if you focus on these green region, this region, now these are the countries from the sub-Saharan Africa, and most of the countries from these regions have a very low or less than 5 happiness score, but the corruption is also really high. You can see here they have almost more than 0.7 in the corruption index. Now you also have a country here which is from the Southeast Asia. We would like to give you a task. It would be really great if you can tell us in the comment section which country is this. It has more than 6 happiness score, but the corruption index is really low, which is less than 0.2. Now if you consider Middle East and North African regions, the darker green countries, here also if you see, the happiness score is less than 5 and the corruption index is also high. Now there are a few countries, the Commonwealth of Independent States, for example countries such as Uzbekistan, then you also have Kazakhstan, we have Russia, Armenia, belonging to these gray color dots. You also have Georgia and Ukraine as part of Commonwealth of Independent States. So here you see the corruption is below 0.6 for these countries and the happiness score is more than 5. Alright, so with that we have come to the end of this demo session on World Happiness Report 2021 data analysis using Python. Hi everyone, welcome to this exciting session by Simplilearn. Today we have a really interesting topic for you. In this video, we'll be analyzing the upcoming United States presidential election using Twitter sentiment analysis in Python. In the course of this session, we will understand in brief about the upcoming election, the candidates fighting the 2020 US election, and throw light on the result of the 2016 US election. We'll look at the election forecast by some of the popular news agencies, as well as poll analysis websites such as 538. Before we begin, I want to make it clear that this video is solely for learning purposes. We at Simplilearn do not lean towards any party in the United States or are biased towards any candidate. The analysis is based on what people have tweeted, and we will understand the mood and sentiment of the public. The main objective of this video is to help you understand how to extract tweets from Twitter handles using Python libraries, store it in a CSV file, and perform textual analysis. The results obtained are purely based on the data that we have collected. Let's begin. The battle for the 2020 US presidential election has begun, with the 59th United States presidential election scheduled to be held on the 3rd of November 2020. This will decide who will be in the White House for the next 4 years. All 435 seats in the United States House of Representatives, 35 of the 100 seats in the United States Senate, and office of the President of the United States will be contested. Both the Republican Party and the Democratic Party have nominated their respective president and vice presidential candidates. The incumbent president, Donald Trump, is the Republican nominee, while the 47th Vice President of the United States, Joe Biden, is the Democratic Party's nominee. The current Vice President, Mike Pence, is the Republican Party's vice presidential nominee and is running for a second term in office. Senator Kamala Harris of California was chosen by Joe Biden as his running mate on 11th of August 2020. Now, let's see the results of the last US presidential election in 2016. The Republican ticket of businessman Donald Trump and Indiana Governor Mike Pence had defeated the Democratic ticket of former Secretary of State Hillary Clinton and US Senator from Virginia Tim Kaine. Donald Trump received a total of 304 electoral votes, while Hillary Clinton got 227 electoral votes. A significant number of central states in the United States were swept by the Republican Party. It was surprising to see that Donald Trump getting nearly 46.4% popular vote as compared to Hillary Clinton, who got 48.5% votes. Donald Trump's victory came after crucial wins in the battleground states of Florida, Ohio, Iowa, North Carolina, and Pennsylvania. Will Donald Trump be re-elected to the White House, or are we going to see a new president and a vice president of the United States is the big question. Let's see what our pollsters have to say and what has been their forecast for the upcoming election. According to 538, Donald Trump has not gained ground since the final debate on 22nd of October. At this moment, Joe Biden is favored to win the election and he leads in both national and state polls. The Economist is analyzing polling, economic and demographic data to predict the US elections. Their model thinks Joe Biden is very likely to beat Donald Trump in the Electoral College. As per their forecast, Joe Biden has 96% chance of winning the Electoral College, and there's 99% chance of Biden winning the most votes. The Democrats have 75% chance of controlling the Senate, while the Republicans have around 25%. The Democrats are highly likely to keep their majority in the House of Representatives. Now, according to The Guardian, Joe Biden is leading Donald Trump in the national polls for the presidential election. But to keep in mind, this does not guarantee the Democratic candidate Joe Biden's victory. Hillary Clinton also had a clear lead over Donald Trump in the polls for almost the entire 2016 campaign. She ended up losing the Electoral College. Now the BBC forecast tells that Biden is leading national presidential polls with 51%. He has hovered around 50% in recent months and has had a 10-point lead on occasions. So clearly, Joe Biden is set to be the next US president. Let's wait and watch what happens on the 3rd of November. The voters of America will decide on 3rd of November whether Donald Trump remains in the White House for another 4 years. Let's perform a Twitter sentiment analysis to understand the sentiments of people tweeting about Donald Trump and Joe Biden by tagging them in their tweets. We have our code implemented already. I'll run through each line of code and explain our analysis in detail. The objective is to check the polarity of each tweet to figure out if it's positive, negative, or neutral. We'll compare the tweets of Donald Trump and Joe Biden to see who people are favoring the most. Finally, we learn to create a word cloud. I have already extracted the tweets and stored them in 2 separate CSV files. It takes some time to fetch 10,000 tweets, hence it won't be possible for me to show it to you live. If you want to know how we extracted the tweets for Donald Trump and Joe Biden, then please put your email IDs in the comment section of the video. We'll share the code file and the source file with you. Now you would need to install the Tweepy library, fetch the Twitter keys and access tokens, and then authenticate the Twitter API. I've extracted 5,000 tweets each for Donald Trump and Joe Biden, converted it into a data frame, and stored it in a CSV file. So let me open and show you both the files. So here is my data set for Donald Trump. On the top you can see Trump_data 5000, which means there are 5,000 tweets here. The first column has the number of tweets. It starts from 0 and goes all the way to 4,999. The next column is the text column, which has the content of the tweet. You can see they have tagged @real Donald Trump. There are links as well. There are special characters like emoticons. And the third column is the user, which means it's the username who had put that tweet. Similarly, I have another data for Biden. You can see these are for Joe Biden, and here you can see the content. They have tagged Kamala Harris also. Similarly, we have the username. Now let me take you straight to my Jupyter notebook where I have implemented the code. Okay, so first and foremost, let's import all the required libraries. So we have the Numpy library for numerical computation. Then we have the Pandas library for data manipulation. Next we are importing 2 libraries, Matplotlib and Seaborn, for data visualization. Then we have TextBlob and Word Cloud to get the sentiment and to build the word cloud. And finally we are importing the Plotly library for creating graphs. Let me run this cell. In the current cell, we'll import the datasets using read_CSV function present in the Pandas library. So I have passed in my location where the data file is, so I have placed it on my desktop. And the index underscore col parameter or column parameter refers to the columns to be used as the row labels of the data frame. Here 0 indicates that the first column will be used as row labels. Let me run it. Okay, now we have imported both the data files. Let me go ahead and print the shape of one of the data frames. So I'll write print. Let's say we'll check the shape of Biden data frame. So I'll write print Biden dot shape. I'll hit shift enter. You can see there are 5000 rows and there are 2 columns. One is the text column and the next column is the user column. Now let me go ahead and print the head of the datasets. So the head function will return the first 5 rows. I'll write Trump dot head. You can see these are the first 5 rows from the Trump data frame, and similarly if you want to check for Biden, I can write Biden dot head. You can see it here. Now you can also use the info method. So let me show you that. You can write Trump dot info, and this is the result. So it tells there are 5000 entries from 0 to 4999. There are 2 columns, and these are the number of rows, and similarly you have the data types. Okay, moving ahead, in the next cell I am displaying the 200th tweet present in the Trump data frame. So I have my data frame name mentioned, then I have my text column, and inside one more square bracket I have put 200, which means I want to see what's there in the 200th row. If I hit enter, so you can see this was the tweet, fake shit, fake president. Next, let me show you the tweet number 1000 for Biden. So I'll write Biden, and inside square brackets I'll give the text column, and the number is 1000. If I hit shift enter, so this is the tweet. Now the text blob function is used in natural language processing. The sentiment property returns a named tuple in the form of sentiment, in brackets, polarity and subjectivity. Let's check the sentiment of the 200th tweet made for Donald Trump. If I hit shift enter, you can see this was the polarity. Now minus 0.399 means the polarity was negative, and you can see the subjectivity is around 0.933. Similarly, let's check for Biden's tweet number 1000. So I'll write text blob, which is my function name, and inside brackets I'll give Biden, then pass in my column name, that is text, and I'll give the row number, which is 1000, and then I'll give the parameter or the attribute sentiment. If I hit shift enter, you can see the polarity and the subjectivity. Now moving ahead, here I have defined a function that will add another column called polarity to our 2 data frames, Trump and Biden. Let me run this. Okay. In the next cell, I have used the apply function that will return the polarity based on the tweets. You can see we have the apply function. This might take some time to run it. Okay, we are done now. Let me now display the top 5 rows of the data frame. So what I'll do is I'll click on this cell, go to insert, and I'll hit insert cell below. Let's do one more. Okay, now here I'll display the head of the data frame once again so that you can see the polarity column added. You can see it here. So for Donald Trump, we have the polarity. You can see the tweet and the polarity. Now 0.0, which means these are neutral, minus is negative, and anything that's in positive value indicates it's a positive tweet or it has positive polarity. Similarly, let's see for Biden. I'll write Biden.head. Okay, so here you can see the polarity for Biden. Now this 0.5 means it's a positive tweet. Okay, now I want to create another column called expression, where we will classify the tweets as positive, negative or neutral based on the polarity value. So I have used the np.where function, and the condition we have here is if polarity is greater than 0, it's a positive tweet, else if it is less than 0, it's a negative tweet, and if the polarity is equal to 0, it means it's a neutral tweet. Let me run this. Okay, so here you can see we have the column called expression, and it has classified the polarity based on negative, neutral as well as positive. Similarly, let's do the same for Biden data frame as well. Okay. Before moving ahead, if you want to get access to the source code and the datasets we have used in this demo, then please put your email address in the chat section. We'll send it to you via mail. Also, please subscribe to Simplilearn channel and hit the bell icon to never miss an update from Simplilearn. In the next cell of code, we have another function that will basically help us creating a bar plot based on the expression column from both the data frames. So this is my user-defined function name, and it has two parameters, reviews and title. You can see we have grouped the expression column and found out the count using the count function. Then we have created or converted it into a list. Similarly, below you can see here we have defined the color for the bars using RGB values. Now let me run it. Okay, so we have successfully created our user-defined function. Now let me go ahead and call the function and pass in my two parameters, reviews and title. So here we have the function name, and under reviews we have the data frame name Trump, and the title we have given as analysis for Trump. Let me run this. Okay, so you can see we have a horizontal bar plot. On the top you can see the title of the plot, which is analysis for Trump, and as per the tweets it has classified as positive, neutral or negative. If I hover over, you can see there were 2,831 neutral tweets, 1,211 positive tweets, and similarly there were 958 negative tweets for Donald Trump. Now let me call that function once again. So I'll write exp_graph, which is my function name. Then I'll pass in my parameters. This time I'll take Biden, and the title I'll put is analysis for Biden. If I run it, okay, you can see the plot for Biden now. If I hover over, there were 1,290 positive tweets for Biden and 747 negative tweets. Okay, let's scroll down. Now let me check the number of rows that have polarity equal to 0, the number of rows that have polarity less than 0 and greater than 0 for both the data frames using the dot shape attribute. So first we have for Trump. Now equal to 0 means we are checking the total number of neutral tweets. You can see the result. Now let's check for Biden. We have the result below. Let me run it. Okay. Now we'll drop those columns that have a polarity equal to 0 from both the data frames and display the shape. You can see we have the condition mentioned, and we have also used the drop function. So all the neutral tweets will be deleted, and I'm printing the shape of the data frame. There you go. So out of the 5,000 tweet, it has deleted all the neutral tweets or dropped all the neutral tweets, and this is the final result. In the current cell, we have defined another function called balanced_data. Now this will help us get an equal number of rows and columns and delete a specified number of rows. Let me run it. Alright. Now I'll call that function to delete 169 rows from the Trump's data frame and 37 rows from Biden's data frame. This will help us subset the data frames. You can see we have now 2000 tweets from each of the data frames. Up next, we'll create some visualizations to analyze the textual data. So first, I'm using the Seaborn library and creating a distribution plot for Donald Trump. If I hit Shift Enter, you can see this is the distribution plot. There are bars at the back and there's a trend line. Okay. Similarly, let me now create a box plot. So this is a box plot. Here you can see there are some outliers. Now let me add a few cells below so that I can show that plot for Biden. So I'll write SNS dot, I'll use the function dist plot, and under dist plot I'll give Biden underscore subset, and I'll pass in my column, that is polarity. Let me run it. So this is the distribution plot for Joe Biden. And now let me also create the box plot. So I'll use the Seaborn library and the box plot function. I'll pass in my data frame, which is Biden underscore subset, and I'll give my column name, that is polarity. I'll run it. So here you can see the box plot for Joe Biden. Let me tell you how you can create a cross table using the group by function. So before coming to this cell of code, let me insert cell above. Okay. Now using group by function, you can create a cross table. So I'll use the Trump underscore subset data frame, and then I'll give my group by function, and inside group by function I'll give my expression column, and I'll count the number of expressions. If I run this, you can see this is a cross table. Similarly, you can do it for Joe Biden as well. I'll just replace the names. I'll write Biden and the rest is the same. You can see this is the cross table for Biden underscore subset. Now moving ahead, let's find the polarity percentage for negative and positive tweets. To do this, I have defined a function called pol underscore percent, and we have two parameters declared, subset and total. Let me run this. Okay. Now here I am calling the above defined function and printing the polarity percentage for Biden and Trump. And I have mentioned my two parameters, subset and the total number. So these are the values. Moving ahead, now let's create a bar graph that will show the negative and positive polarity percentage for Donald Trump and Joe Biden. Let me hit Shift Enter. You can see we have a really good bar graph now. If I hover the mouse cursor, you can see Donald Trump had 27.825% of positive tweets and 22.17 negative. Similarly, Joe Biden had 31.6 positive tweets and 18.4 negative tweets. Now we want to find the public sentiment based on Trump and Biden tweets. Let me run this two cells first. Okay. Now for Donald Trump, the total positive polarity is a combination of Trump's total positive percentage and Biden's negative percentage. Similarly, For Joe Biden, the total positive polarity is a combination of Biden's total positive percentage and Trump's negative percentage. Let me run this. You can see the result here. Next, let's plot a horizontal bar graph to visualize the public sentiment. We have our X and Y labels defined. We also have set our bar colors with the help of RGB values, and we have the title as well. Now if I go up, you can see this is the public sentiment. So 26.88 is the percentage that is in favor of Joe Biden, and for Donald Trump you have 23.11. Now coming down, now in the next cell of code we have a user-defined function that will basically plot a table which has the most positive tweets for Donald Trump and Joe Biden. The condition we are checking is that the polarity should be equal to 1. So if it's close to 1 or equal to 1, which means the tweet has positive polarity. Let me run it. Okay, now let me go ahead and call the function now. Let me scroll over to the top. You can see these are the top 5 positive tweets for Donald Trump, and here you can see the top 5 positive tweets for Joe Biden. Likewise, let's check the polarity for most negative tweets. Here the condition will be the polarity should be equal to -1, which means it's highly negative. Let me run it. Okay, now let's go ahead and call the function negative tweets. So I'll write neg underscore tweets, and then inside bracket I'll give my parameters, which is Trump underscore subset, and then I'll give my title as negative tweets for Donald Trump. Okay, now I'll just copy this. We'll also check for Joe Biden, so I'll just replace this with Biden, and let's say negative tweet for Joe Biden. Let's run it. Okay, if I go on top, here you can see the top negative tweets for Donald Trump, and similarly we have the top 5 negative tweets for Joe Biden. Alright, finally let's see how to create a word cloud. Now word cloud is a method to show which words are most frequently occurring among the given text. I have defined a function called word cloud, you can see here, and it has 2 parameters, data and title. Inside the built-in function or the word cloud function, we have mentioned the max font size, the maximum words, scale value, there's also background color which is white. Okay, let's run it. Now this will create a word cloud. So let me go ahead and call the word cloud function and pass in the arguments. So I'll write word cloud, which is my user defined function, and I'll give my parameters Trump underscore subset, comma, I'll give my title as word cloud for Donald Trump. Let's say Donald Trump tweet replies. Okay. Similarly, let's do it for Joe Biden. I'll write word cloud Biden underscore subset, and then I'll give the title as word cloud for Joe Biden tweet replies. Okay, let me run it. There you go. you can see we have a nice word cloud. So on the top you can see the title which says word cloud for Donald Trump tweet replies. So here you can see some of the words like real Donald Trump, then there's president, love, right, all these. Similarly, if I scroll down, you can see the word cloud for Joe Biden tweet replies. You can see this is the handle Joe Biden, false. There are some other words like due, taxes, believe, even, will, it's fact. And you can see Kamala Harris name here. Okay, now that brings us to the end of this demo on Twitter sentiment analysis using text data. You learned how to classify tweets and find the polarity. We also looked at how to create interesting visualizations with this data and understood the mood of the public. Finally, you saw how to create a word cloud that had the most frequently occurring words in the tweets.
So welcome to this session where we will learn on time series analysis using R programming language. So this is basically a mini project where we will look at time series data and how we can analyze it, visualize it to basically find some important information or gather insights from the data. Now, when you talk about time series analysis, time series is basically any data set where your values are measured at different points in time. So when you talk about time series data, data is usually uniformly spaced at a specific frequency. For example, hourly weather measurements, you have daily counts of website visits, monthly sales total, and so on. So when you talk about time series, that can also be irregularly spaced and sporadic. For example, timestamp data in computer systems, event log, or history of 9/11 emergency calls. Now, when we work with time series data, for example, here I'm taking an energy data set, we can see how techniques such as time-based indexing, resampling, rolling windows can help us explore variations in electricity demand and renewable energy supply over time. Now, here we will look at some aspects of this data set which I am considering. So this is open power systems data set, and here is the data set I have. We can look at the data set. Now this is in a simple format. It has time. It basically has values for consumption, and then you have data for wind and solar and wind plus solar. So in certain cases you have only the date and the consumption, but then if we scroll down, we will also find data for wind, solar, wind plus solar, and so on. So this is a time series data set which we would want to work on. Sometimes you may also have the data collected which just does not have the time, but it may also have timestamp. That is, it would have, say, hour, minutes, and seconds, and that can also be worked upon. So let's consider this data set and let's work on this project where we will analyze this time series data set. Now here we can work on this time series data. We can basically create some data structures out of it, such as data frames. We can do some time-based indexing. We can visualize the data. We can look at the seasonality in the data, look at some frequencies, and also do some trend detection. Now, when you talk about this data set, it has electricity production and consumption, which is reported as daily totals in gigawatt hours. And here are the columns of the data, which I was just showing you. So you have data, you have consumption, you have wind, you have solar, and wind plus solar. So this is the data we have, and we will basically explore, say, electricity consumption and production in Germany, which has varied over time. So some of the questions which we can answer here is, when is electricity consumption typically highest and lowest? How do wind and solar power production vary with seasons of the year? What are the long-term trends in electricity consumption, solar power, and wind power? How do wind and solar power production compare with electricity consumption, and how has this ratio changed over time? We can also do wrangling or cleaning of this data or pre-processing of data and create a data frame, and then we can visualize this. Now let's see how do we do that. So I will open up my RStudio and let's look at the data set. So here is the data set. Now I'm picking it up from my machine. You can also pick it up from GitHub. So all the data sets or similar data sets can be found in my GitHub repository. And here I can look in the data sets. You will find a lot of different data sets here. There are some time series data sets such as power. I can search for power, or you have basically coal, or you have this OPSD Germany daily data set, and there are many other data sets which you can work on. Now, to get the documentation on this project, you can also look in my GitHub repository, and you can search for repositories, and then basically you can look in data science and R, and here there is a project folder where I've given the documentation, sample data set, and also your time series analysis related document. This is also the code which you can directly import in your RStudio, and you can practice or work on this project. So let's see how does that work. So first thing is we will create a data frame from this data set. Now here, if you see, I am using header as true so that it understands the heading of each column. I'm also giving row.names, and I'm specifying date. So there is this date column in the data set as I showed you earlier. Let's look at it again. So you have date, consumption, wind, solar, wind plus solar. So you can suggest that date should become the index column, which can be useful. So you can do this. Now let's just create this. Let's look at what does this data frame contain. And here, if you see, it shows me some data which has been now as a part of this data frame structure. It starts with consumption, wind, solar, wind plus solar. And if you see, this one is becoming my index column. So I can always do a head and look at part of the data frame using head or tail. So look at the first records. So let's see this. Now that shows me the head data. I can also do a tail and look at the ending values. So if you closely see here, we have wind, solar, wind, dot solar, and that basically has NA values. So there are missing values, but let's look at the tail, and that tells me that there is some data available for wind and solar and wind solar. Now we can always look in a tabular format using view, and we can look at the data. So this shows me that there are values in these columns. We see NA values, but if I really scroll down, I can see some values which would be available for wind and solar and wind solar. So I can just use view. Now I can look at the dimensions of this particular object, and that tells me there are 4,384 rows and 4 columns. You can always look at the structure, that is check the data type of each column, which can be very useful. So if I see here, I don't see the date column because date column was considered as an index, which can be useful. But I also look at my other columns. So they are of the num types. So that's the data type for each attribute or each column here. Now we would be interested in looking at this date column. So let's look at the data type of this date column. Now if I try to do this, this will show me that this is null because date as a column does not exist because we created it as an index. So if I look at row names and then I search for my data, show me the index column or row.names, it tells me these are the values, that's the date column, which we are seeing here. Now we can access a specific row by just doing a my data and give the index value or row name value. So let's look at that, and that shows me based on this index you're looking at the value. You can obviously search for a different date, something like this. You can also pass in a vector and you can give range of values. So that is 0, 1, 2006 to 4 of January. And we can look at this one. So it shows me these are the values. So here actually I'm not giving a range, but I'm just selecting multiple values from row.names. Now we already know that in R you have a summary function. So you can always do a summary, and that gives you, for each column, it gives you minimum, first quartile, median, mean, third quartile, and maximum values. So we are looking at consumption, we are looking at wind, solar, and wind dot solar. Now, this is good, but then if I would want to really visualize the data, access the data, do some analysis, then it would be good to take all the columns, and then we can later decide to change the data type of, say, date column if we want to use it. So earlier I was using date as row dot names, or the name of the rows, or index, what you call in any other programming language. So here I will just use my data set, and I'll say header as true. I'm calling it my data 2. Let's look at the data, and this one shows me 5 columns, wherein my first column is the date, consumption, wind, solar, and so on. Now looking at the structure, so let's look at the data type. So it tells me that if now I'm interested in looking at the date column from my data to data frame, it tells me it is a factor with 4384 levels, and these are the values. So it is not in a date time format, it's a factor. Now what we can do is we can convert this into a date format. How do we do that? So let's have a variable x, and I'm going to use as.date function, and I'm going to pass in my date column. So that's assigned to x. Now let's look at the head of x, and it shows me the values. We will also see what kind of class it is, and we will look at the structure of x. So class already says it is date type, and look at the structure, so it shows me the format. Now we have converted this column or column related value into x. Now how do I basically extract values out of it or make it a part of data frame? So first I will use, so all once it has been converted in date format, I will go for as.numeric, and here I will create a variable called year, and I will just do a format on x, which is basically of date type, and then I'm saying %y, so that will get me the year component out of this. Let's look at the values. That shows me year component. Now similarly, we can get the month out of this, and then basically look at the month values. We can get the day out of it, and we can get the day component. Now if I look at my data 2, which we had created earlier, this basically had date, consumption, wind, solar, wind, solar. So what I can do is I can add these extracted columns such as year, month, day to my data frame using a cbind, that is column bind, and I will assign it to my data 2 again. So let's do this, and now if you look at head, it shows me date, so that should be date format, consumption. Now this one might not be date format, but we'll see. You have consumption, wind, solar, and we have extracted the year, month, and day, which can help us for group by. We can do some aggregations, we can do a plotting, and we can do various things by these additional columns. Now let's look at first 3 rows here. So I'll say 1:3 for my data 2, and that shows me some data here. You can always do a head and look at the sample of data. So that basically shows me month, day, your columns, and then you have your date. Now what we can do is we would want to visualize this data. We would want to basically understand the consumption. Now as I said, if we want to visualize the data, say for example I want this, which is consumption of data over years, and this one is in terms of gigawatts per hour, as we were mentioning here, gigawatt hours. So if I would want to create this visual to basically understand the pattern of the data, how do we do it? So we can create a line plot of full time series of Germany's electricity consumption using the plot method. Now how do we do that? So here one of the option is I can straight away use the plot method. I can then say what would be in my x-axis, what would be on my y-axis, what would be the type of graph I would want to plot, what is my name on x-axis, y-axis, and this is the simplest way. So I'm saying my data 2, I'm extracting the year column, and here I'm taking the consumption. So let's create a plot. And here, if you see, we are looking at a plot. We do see some tick times, and we see that the data has been divided with every 2 years. So from 2006 onwards to 2016. But then really this data does not give me a very useful way of looking at the data or understanding it. Might be what I can do is I can use the same way, but I can give, apart from x-axis and y-axis, I can say the limits, that is x limit is 2006 to 2018 and y limit is from 800 to 1700. So we can do this, and let's look at this again. This is a plot, but it really does not help me in visualizing and understanding the data. So what are the better options? I can go for multiple plots in a window. As of now, we are just sticking to one plot in window. So if you would want to have multiple plots, you can always change the value here and make it 2 or 3. That will say how many rows and how many columns. So as of now, we will just keep it as it is, par mf row. Now, if I would want to plot, I can straight away give the column name. So I'm interested in getting the consumption. Now I can just do a plot. I'll say my data 2, and I will choose the second column, which is consumption, which we saw here from our data. So consumption was the second column. So I can just do a plot in a straightaway way without mentioning your x-axis, y-axis, limits, and so on. And if you look at this, this one is giving me a pattern. Now here I am looking at x-axis, y-axis, which is not really named. We do not have a name to this graph, and we are looking at the data. It does show me some kind of pattern, but might be we can make it more meaningful. So I can do it this way, where I say my data second column, let's give axis as year, x-axis, y-axis is consumption. Now that has changed, the x-axis and y-axis. Now I can also give some more details. I can say type should be line. I have the line width. I'm saying color is blue. And let's do this. So this looks more meaningful, might be shows a wavering pattern of consumption over years. I can also give a limit of x, that is 0 to 2018, and that basically shows me the range. Now we can change that, and we can be more specific and saying x limit should be 2006 to 2018. And let's look at this. Now this one, once you have given a proper limit, it shows the line graph, and it shows what was the consumption in 2006 and over a period till 2018. I can then use any of these options are fine, but it depends on what and whom you are presenting the data or what kind of analysis you're doing. So I can do a plot. I can choose column second, x lab, which is x-axis, y-axis, type is line, width, giving a x limit, y limit, and then I'm giving a title to this, which is consumption graph. And then basically you're looking at the line graph. Now, those are the options which you can do. Either you could be very specific, or you could just give your column which you want to plot, or obviously make it more meaningful by giving all the details. Now, what we can do is, if we would want to look at this data and understand it better, rather than just looking at a simple line, I can take the log values. So here I'm saying log of my data to second column. So I'm taking log values of consumption, and I'm taking the difference of logs. So I can say difference, and then you can basically increase or decrease this by multiplying it by some number. So rest remains the same. I'm changing the color, and let's look at this plot. And you see, this basically is giving me a better pattern, which makes meaning. Here we see the log values. So this is, you are using a simple plot function. In R, you can also use ggplot. Now for that, we can install the ggplot package. It's already there in my machine, so I'll say no. I will access this by using the library ggplot2. And now I can use ggplot to plot. So the way you specify here, you can say my data 2, that's the data frame. I'm saying type as O, and when I'm saying line, I am basically going to use x-axis, which is year, y is consumption. And let's look at this plot. So again, we are back to the one which we were doing earlier. Really does not make any sense. It gives us some data, but then really does not give me enough information. I can, in my aesthetics, I can say X as year, Y as consumption. I can do a grouping, and then I can give line and plot. So again, we have some information, but really does not help me, right? Now let's look at other example. So I'm just doing the same thing here, and I'm looking at line type being dashed. I'm using the ggplots other methods such as geom_line and geom_point to give me more information. And if I look at the plot, it does give me data. It tells me what are the different values. It gives me some kind of pattern, but I would still prefer the way we were doing with plot. Now we can change the color and obviously add details to it. So what we see is when you use the plot method, which I did earlier, it was choosing pretty good tick locations, that is every 2 years, and labels the years for the x-axis, which was helpful, right? But with these data points, which we were seeing here, or say, for example, this one, or say this one, or say this one, we are looking at some data, but then that really is quite crowded and it is hard to read. You can look at the values, but then it really does not give you enough information. So we can go for plot method, but then we will see how we can consider different data. Now, if I would want to plot the solar and wind time series, so let's see how do we do that. So wind column is what I'm interested in. So first thing is, it was always good to find out the minimum and the maximum values in every column. So I'm saying minimum, I'm saying let's put in here my data 2, and then let's look at the values. So we are looking at the columns. We know consumption is the second column, wind is the third column, and you have solar as the fourth, and this one is the fifth. So let's find out the minimum of each of these columns which we would want to plot. So let's say minimum of data third column. And here I'm also saying remove the NA values because we do not want to consider the NA values. So let's look at the minimum. That shows me 5.7757. What is the maximum value? It is 826. So that also helps me in giving a limit. If I want to plot wind on y-axis, I can give a y limit from 5 to 850. Consumption wise, let's find out the minimum from second column and maximum. And similarly for solar, find the minimum and maximum, and wind plus solar, minimum and maximum. So this will be helpful when you would want to plot multiple graphs or give some limits. So that's fine. Now for multiple plots, as I said, instead of having one plot, let's plot consumption and wind and solar and try to see a pattern. So I can say par function, and I will say 3 rows and 1 column. So now when I start plotting, you will see you will have multiple plots in one single window. So let's see how we do it. So here, let's look at plot 1. So this one is consumption as we did earlier. And let's look at the data. So that gives me some data. You can always do a zoom and you can look at the data. You can basically expand this graph or you can reduce this graph to see what kind of pattern we have in consumption. Similarly, we can basically choose date being x-axis, my consumption being y-axis, right? So this is being more specific because here we have a range, but it really does not give me enough information. So I will basically give x-axis, y-axis. I will give the name, that is daily totals, and then I will basically give consumption, color, and y limit based on my minimum and maximum limits. So let's do this. And now we can look at the data here. So let's see, this data makes a little more meaning because we are looking at the dates. And let me do a zoom. So it shows me all the dates. It shows me the data points. It shows me how the data pattern is changing for consumption. Now this is for consumption. So what we can do is we can also extract specific data. So if you see here, I have done some testing where I'm saying, okay, I would want to get a date specifically. I would want to extract some value. So we are looking at the date column, but if you remember, we did not change the data type. We just changed the data type of date column. We extracted year, month out of it. It would be good if we can convert a column into date time format and put that in our data frame. Now, let's look at the plot 2. This is mainly for your column, which should be consumption and wind and solar. So here I see it is solar data, and I can plot this one to see how it looks like. And that tells me from 2006 onwards, we have some pattern. I can be more specific where I say I would be giving date and then the column for solar, x-axis, y-axis, what is the type, what is the y limit, and what is the color. It is always good to specify your x and y axis, give a name rather than let it automatically pick up. Now this makes more meaning because it shows me some dates. Similarly, we can do for wind. So either you do it just by giving the column or you give your x and y axis. So let's look at this one. And this shows me the data. So we can choose plot 3. This one we can choose plot 2. We can choose plot 1, and we can put all that data in one graph. So that's when you are putting in multi plots in one particular graph. You can always do a zoom. You can always look at the data, right? And this is usually useful to look at the pattern, what kind of pattern we see, what data we have, and so on. Now, moving forward, so we have seen how you are creating these plots all in one window. Let me reset this back to one plot per window. And let's basically plot time series in a single year. So what we have seen is that when you look at the plot method, it was quite crowded. Then we looked at solar and wind. And if you compare that, you will see your consumption pattern, your solar pattern, your wind pattern. And basically we can see from this particular data some kind of pattern. So electricity consumption is highest in the winter, where we will see what is the consumption. Is it highest in winter or is it in summer? We can see that by breaking a year further into months. We can see that, but we see a pattern which goes for every year or every 2 years being highest at a particular point of time, and then it drops down. So electricity consumption is highest in winter, and that might be due to electrical heating and increased lighting usage, and lowest in summer. Now, when you look at electricity consumption, appears to split into two clusters. We can always look at the consumption, one with oscillation centered roundly around 1400 gigawatts. So you can always look at 1400 gigawatts and you see all the values here which are in that particular consumption. Another with fewer and more scattered data points, centrally roughed around 1150. So if you really expand this, you can see you will have a lot of data points at this point. Now, we might guess that these clusters correspond with weekdays and weekends, which we can see if you break that data into yearly, monthly, weekly, and so on. Now, if you look at solar production, that is highest in summer when sunlight is most abundant and lowest in winter. So obviously when you're making or gathering some insights, when you're looking at the data, you are also using your domain knowledge, your business knowledge, your knowledge of business to understand how this goes. If you look at wind power production, that's again highest in winters and drops down in summer. So due to stronger winds and more frequent storms, and lowest in summer. So there is some kind of increasing trend in wind power production over years, which we can see here over the years. And all the time series data what we are looking at is referring or showing us some kind of seasonality. That is, we are looking at seasonality in which a pattern is repeating again and again at regular times. at regular intervals. So if you look at consumption, solar and wind time series, that oscillates between high and low values on a yearly time scale, which we can break down and see. I'll show you that. It corresponds with the seasonal changes in weather over the year. So seasonality does not have to correspond with meteorological reasons. For example, if you look at retail sales data, that will show you yearly seasonality with increased sales in particular months. So seasonality, when we say, can occur on other time scales. So the plots what we are seeing here, they are fine, but if you look at those plots, they might show some kind of weekly seasonality also. So in your consumption corresponding to weekdays and weekends. So let's plot for one single year. Now, how do I do that? So first is I will look at my data 2. That shows me the structure. It shows me date, which is factor, other columns, which are all numerics. Now, like we did earlier, I'll repeat this step where I'm going to convert the date column into date type. Look at head of it, look at class of it, look at the structure of it, right? And then what I want to do is I want to add this to my data frame. So I will create a variable called mod data, and this one will have as data, and I'm formatting the value of X, which is date time, into month, day, and year. So let's do that. And now you look at the mod data, which I created, like modified data. So this is the format I have. It is in date type, if you carefully see here. And then I can look at the head of it. So it says me mod data. Now what we did here is when I said my data 3. So my data 3, we did a cbind and I did a mod data, which is going to add this column to my other columns of my data 2. So my new data frame is my data 3. Let's look at the structure of it. And you see there is this date column. I can delete it, I can remove it, I can let it be, right? So that depends on our choice. Might be we want to, once our analysis is done, we want to remove the mod data, right? So we can keep both of them. Now let's basically extract data for a particular year. Now how do you do that? So this is some wrangling. So I will say my data 4, let's call it my data 4, and I will use subset function. So subset will work on my data 3, that's the data. And what I'll do is I will do a subset. How is the subset found? So I'll say take the mod data column, the value should be greater than or equal to 2017 and should be less than 2017 December 31st. So I'm getting data for 1 year and I'm storing it as my data 4. Let's get the head of it, and you see we are specifically looking at 2017 related data. Now let's do a plotting of this where I will only create a plot for 1 year. So I'm saying my data 4, that's my new data what we got. So here I am going to take the first column, which is mod data. I'm going to take the third column, which is consumption. So I'm looking at the date format for 1 year, consumption values for it, and then rest of the things as we have done earlier. Let's look at the plot, and this makes more meaning, right? So when you look at this plot, it tells me Jan to Jan. It shows me some kind of pattern where I have divided the year into months, right? And it is broken down into say 2 months, so Jan and March and May and July and so on, but we still see a pattern, and that gives me good understanding of pattern where I've broken it down into months. So this is where you have taken time series in a single year to investigate further, and this is what we see, right? Now we can clearly see there are some weekly oscillations. What one more interesting feature is that at this level of granularity, that is when you're looking at yearly data, there is a drastic decrease in electricity consumption in early January and late December during the holidays, or probably we can assume that this is holidays. Now I can zoom in further and look at just Jan and Feb data. Let's see how we do that, and let's see how we work by zooming in the data further. So to zoom in the data further, let's see how we do it. Now here we have this my data 4, which is basically having a subset, right? So let's work on this one. So I will say my data 4, which earlier I was taking data 3, I was doing a subset and I was giving the date, but this time I will make it more narrower. So I'll say my data 4, I will say subset from my data 3, and I will choose mod data column, which we have modified with the date format. I will choose the starting date as 1701, that is Jan, and then let's go till Feb, and let's create this. Now let's look at the head of this. So it shows me we have the data which is Jan, and then you can basically look at more on this. Now again, as I said earlier, let's find out the minimum of this from the first column. So that is basically your mod data. So let's look into this one, and that basically will give me minimum and maximum. Let's look at the values. So this one tells me Jan 17, January 1, and maximum is your Feb 28th, second month 2017. So we are actually looking at 2 months data here. Let's look at the Y minimum. So this is, I will look at column 3. Now what is column 3? Consumption. So let's look at the minimum value for consumption, maximum value of consumption. Let's look at the values which can be given as our limits. Now this is the minimum and maximum. Now let's do a plotting for this data which has been narrowed down for consumption based on my data. So I'm saying my first column, which is mod data, and then third column, which is consumption. I'm giving some naming convention for, namings for your x-axis, y-axis, what is my consumption, or what is my title here, what is the color, and then you see I'm using X limit to give the minimum and maximum limit and Y limit. So let's look at this data. And if you look at this data, it is specifically for 2 months. And again, I can look at the pattern here. What I can also do is I can add some grid here. So I can basically look at this data and make more meaning out of it. So it is bi-weekly data, you can see. Now I can add a line here using ab line, and then I can basically choose what lines I would want to add horizontally. So that basically allows me to dissect the data and look at data in a more meaningful way. I can also add vertical lines. So vertical lines is, I'm saying sequence will be minimum, maximum, and I'm saying an interval of 7. So let's do this, and this basically has added some lines every week, and you can see at the end of week it is dropping, and then it is starting again. It peaks somewhere in the mid of the week, and again it drops down. So this is, you're looking at your consumption data, right? Now what we can also do is we can create some box plots. So when we looked at zooming in data for Jan and Feb, you can add some data points like this. So consumption is highest on the weekdays, as I showed you here, and lowest on the weekends. So this is what we are seeing when we are breaking the data or zooming it further for a couple of months. So we have vertical grid lines, and we have nicely formatted tick labels, that is Jan 1st, Jan 15th, Feb 1st, and so on. So we can easily tell which days are weekdays and weekends with use of these grid lines and basically breaking it down. So there are many other ways to actually visualize your time series data, depending on what patterns you're trying to explore. You can use scatter plots, you can use heat maps, you can use histograms, and so on. Now, moving further, we would want to explore the seasonality, right? So when you further explore the seasonality of our data, we can use box plots basically to group the data by different time periods and display the distribution for each group. Now, how do we do that? Let's come here and let's see how box plot works. So I can just do a simple box plot, and I can choose my consumption column, and that gives me just the consumption data, but this really does not give me any meaning. I can look at solar data, I can look at the wind data, and we can also see some outliers here. So we can create box plots, but if we would want to do a box plot, what is box plot? It is basically a visual display of your 5-number summary. That is, you want to look at your mean, median, you want to look at your 25th percentile, 50 percentile, or 75th percentile. So we can use a quantile function, use the consumption column, and then you basically give a vector which shows you 5-number summary. So that's your quantile. And then let's do a box plot. So if you are looking at quantile, it tells me what is the minimum, what is 25th percentile, 50, 75th, and 100. That's from my consumption column. So let's create a box plot for consumption. Let's give it a name as consumption. Let's give y-axis as consumption and a limit for y-axis. Now that's my consumption graph. So I can look at yearly data. Now that will make more meaning rather than just looking at the complete consumption data. So how do we do it yearly? So we will say consumption, and then I will say the year column. So it is consumption, but grouped based on year. So here I can give x-axis, y-axis, and I can give y limit. So let's create this, and this makes more meaning. We can give some coloring scheme here, but now I'm looking at 2006, 2007, 8, 9, and so on. And we can look at the data, what is the range, right? It gives me 5 percentile, or sorry, 5-number summary of the data per year, and it basically allows me to look at the seasonality of this. Similarly, we can create box plot by just giving consumption, yearly grouped, and here I'm giving the title as consumption, y-axis, x-axis, and y limit, wherein I can also use las. So this is one more feature which you can do, and that basically will give me the tick points. If you compare this one to the previous graph, so when I created this previous graph, I had 2006, 2008, and I had from 600 to 1800. And if I go for the next one, I am basically seeing more useful information. Now let's look at monthly data. So I would want to group it based on months, and let's create that. So this gives me the monthly data where I'm looking at months, and I could select a particular year, or I can just do a grouping based on months. So I can have multiple plots to see a difference here. So let's do this. Now let's create a box plot for consumption, which is monthly data, and let's give it a color. Let's look at the wind data, which is again grouped monthly, and let's look at the solar data, which is grouped monthly. Now if I zoom in, it basically gives me the seasonality of the data for your wind, for your consumption, for your solar. So what we are doing is we are creating these box plots which are giving us values. Now what I can also do is I could look at the day wise also. But before we look into this, how do I infer some information from these box plots which are being created? So this is what we have done, where we are looking at the data for month, and these box plots give me year seasonality, which we were seeing in earlier plots, but give some additional insights. So if I look at the data here, it tells me the electricity consumption is generally higher in winter. Now this is based on months, so we can see consumption is higher in winters and lower in summer. So we can obviously look at our plot, we can see where it is lower, where it is higher, and then we can look at the median and lower two quartiles are lower in December and January compared to November and February. So that is, you look at the quartiles and you will see that the median and lower two quartiles are lower in December and January. Here Jan and December, so you can look at from my plot. Now this is giving you some idea on seasonality. Now that might be due to business being closed over holidays. Now this one we were also seeing when we looked at time series for 2017 only, and box plot basically confirms that there is this consistent pattern throughout the years. Now, when you look at your solar and wind power production, both will give you a year seasonality, what we are seeing here. And if basically I look at the data, so it depends on what parameters you are choosing, but if you look at solar, it will reflect the effect of occasional extreme wind speeds associated with storms and other transient. And since we are grouping it based on months, we can see this pattern is quite evident every year. Now, what we can do is we can group the data day-wise. So here, let me again reset this to one plot per graph. Now I'll say box plot. I'll say consumption, which is grouped based on day. Now we know that there is a day column, and let's give a while limit and let's look at the data. So this is where I'm grouping the data day wise. So you look at 31 days and you look at the box plot. So this is where you are plotting it on a daily basis. So you can look at the data, you can break it down to a particular week. So here I have given day and I have chosen all the 31 days, but I can break it down to a week and I can look at the data. So if we look at the data per week or per day, we can basically infer that electricity consumption, where I'm doing a consumption group by day, is higher on weekdays than on weekends. So time series with strong seasonality can often be represented with models that can decompose signal into seasonality and long trend. Now this is an easy way. Now, how do we look at the frequency of the data? That could be interesting to see. So let me look at, say, the yearly data, which we were seeing here. Now let's go further, and here we have looked at data. So what we will do is we look at the frequency. Now when you look at the frequency, when you talk about frequency in your data, so we have the modified date column, which gives me a frequency. And if we really look into the data, that will tell me that the data is on a daily basis. So for that, let's look at my data 3 again, which gives me data, and you can just see all the data or dates are in sequence. So your 22, 23, 24, 25, 26, and so on. I can access a dplyr package that is basically allowing me to work in a better way. Now I can look at the summary of this, and for all my columns, I'm seeing what is the minimum 5-number summary, date, and consumption. So date does not show me anything because this is not in a date format, it is just a factor, but other things have the 5-number summary. So we are looking at wind plus solar, we are looking at year and month and day and all these columns. Now what we will do is we will want to find out the sum of each column, how many entries does it have, and we will say the value should, NA value should not be considered. So let's look at this one. So it tells me for my particular columns. So let me run this again, and that shows me for each column how many values you have, and these counts do not include the NA values. Now similarly, I can find out specifically for consumption, I can find out is there any NA value. So I'm saying is.NA, and let's find out if there is any NA value or missing value in consumption. It says 0. Okay, that's good. If you look in wind, it tells me there are 1463 entries which are NA. Similarly solar, similarly wind dot solar or wind plus solar. So it gives me a count of NA values, that is missing values, and also values which are not missing. So to understand frequency, what we can do is we can find out the minimum on the date, that is the first column, and I'm saying RM na.rm is true, that is get rid of NA values and find out the minimum. And let's look at the minimum value. This is the minimum from my modified date. Now if I would want to get the frequency, I can basically use sequence function. So I can say from x minimum, that is the minimum value, I want to look at the frequency, that is day wise, and let's just look at 5 entries and see if there is a day by day frequency. So let's look at the value of this, and obviously it tells me there is day wise frequency. So that allows me to look at the frequency, look at the type of it. It is an integer, class is a date. So similarly, we can say from X minimum, we can basically look at the frequency month wise, and I can again look at 5 records. So that shows me monthly data, right? So I can extract the data for frequency, similarly yearly data, and that's also very useful. Now, we can select data which has NA values for wind. So how do I do it? I would want to find out the wind column, and I want to find out where the values are NA. So I will create a variable, and here I will say my data 3, and then I give a conditional where I say is NA in the column. So let's do this. Now once I've done this, I have said that my selected wind data from my data 3 where we said NA values, and I will give the names to this. So names should be in my data 3. I'm interested in mod data, consumption, wind, and solar. So these are the 4 columns I'm interested in. Let's look at first 10 records here, or first 10 rows. So that tells me these are the values where wind has NA or missing values. I can always do a view, and that gives me the complete data. So it basically shows me 1463 entries, and here it shows me all NA values. So you can look at all the way to the end, and it shows me wind has NA. Solar does have some value here in the last row, but then also if you see, the numbers have a difference. So you have 1461 and then you have 2174. So there is a difference. So there is some data in between where wind has some values. So we have found out NA values. Now what we will do is we will select data which does not have NA values. So I will call it cell selected wind 2. I'll again use my data 3. I will say which, but now I'm saying not NA from this column, and I will select the data for the columns. So I'm interested in looking at 10 records, and this shows me not NA values, so no more missing values. So if I really look at this data as I saw earlier, which has NA, and if I look at these values which are not NA for the wind column, so looking at these two results, we will know that in year 2011, wind column has some missing values. So let's focus on year 2011. So how do I do that? Let's call it a different variable. I'll say my data 3. I will say here, when I say which, where we were saying NA, here I will say the year should have a value of 2011, and I want all these columns. Let's look at the data here, and this is showing me 2011, but we are not seeing all the values. So there are some values, but then there are some missing values also for 2011 based on whatever analysis we have done. So let's look at the class of this. It is basically a data frame, do a view, and this one will help me in finding out where are the NA values. So if you just scroll down, looking at all the data, let's search if wind column has a NA or a missing value, and I will see if there is any missing value, in which column or which row it is for the wind column. So we have all the values which are existing. I could select and search for one specific value, and I'll show you how we can do that. So here, let's scroll all the way down. So it's like you're exploring your data and seeing is wind column having NA or missing value for a particular row. And let's scroll here, and here you see there is a missing value for one particular row. So 13th December 2011 has wind value, 15th December has wind value, but your 14th December does not have, right? Similarly, we can search. So there was only one entry which was missing. Now that could be for some reason, might be it was not calculated, might be it was not tabulated. So we have a missing value, and that can affect my plotting, that can affect my analysis. So let's look at the number of rows in this, which will tell me how many rows we have for 2011. So it tells me 365. So that is basically the number of days in a year. Now we will find out if there were NA values. So we earlier checked total number of NA values per column. That is in your row number 265 to 269. We can see here 265 to 269. So this is where we were seeing, are there any NA values, right? So let's go back here, and we want to find out the number of NA values for a particular year. How do I do it? So I can just do a sum. I will say is NA. Now I'm interested in my data 3 wind column, and I'm saying my year has to be 2011, but I'm finding out the NA values. So let's do this, and it tells me 1, and that's right. That's what we saw when we did a view. Let's see how many non-NA values you have, and that is 364. So that basically satisfies my logic. So it's 364 plus 1 missing, so there are 365. Let's look at the structure of this. It tells me you have modified date and date format, you have consumption, wind, and solar. Now let's create a variable, selected wind 4. I will say wind 3, that is which was having all my NA and non-NA values for 2011. I will say let's find out the NA value, because I'm interested in finding out that particular row. So I'm saying find out where the value is NA, and I want all the columns. Let's look at this one, and this is my specific row which has a NA value. Now we know that data follows a day-wise frequency, which we have clearly seen. Now let's select data which has NA and non-NA values. So let's call it test 1. I will use wind 3, which has NA and non-NA values. But now I will say I want the modified date, which should be greater than 12/12/2001. Now remember, we had, when we were doing a view, we saw that one particular day, or what we see here, 14th of December, there is no date. So I will select a subset of data which includes this NA and non-NA. That is, might be I can take 13th of December and 15th of December. So let's start from 12/12. So the date should be greater than 12/12. That means 13th, and it should be less than 16. So that is 15th, and the columns, right? So now we have some data. Let's look at this. So I've selected a subset of data. I could have done this using subset also. So I have NA and non-NA values. Now, why are we doing this? So sometimes you might have some data for a particular column, and you may want to find out if there are any missing values. Might be you want to fill them up or replace them with something. So that is usually useful when you are doing a trend detection. So say, for example, you have data for every month, and might be in one of the months you have missed, or might be you have data for every year collected monthly, and then in one of the years for a couple of months you don't have the data. Like I can say 2016, I have data for all 12 months, 2017, all 12 months, 2018, might be I don't have data for March and June, 2019, I don't have data for same months. So I can forward fill or backward fill them using the previous year's same month data. So we can do that. So here I have test data where I've extracted a subset of data. I can look at the class of this. It is a data frame. Structure of this, it has the columns. Now let's use the library and function and use the tidyr package. And what we will do is we will fill it up. So I will use test 1. I will fill the wind column, which has a missing value. Now once you do this, if you notice, it has done a forward fill. So it has taken the previous value and it has just filled up that. So you can fill up the data using different directions such as up and down, left and right, and so on. So we can take care of missing values in our frequency data, which allows us to basically analyze the data in a better way. Now, here we will want to also look at some more data. So this is to deal with frequencies of fill column, wherein you can take care of missing values forward filled. So filling values can be done in different directions, as I said, and you may want to first convert your time series to specified frequency if your data does not have a frequency, but we had. Now, if you do not have a frequency, might be you can convert it into a frequency such as weekly, daily, monthly, as I showed you, and then basically you can do a forward fill for the values. So for example, if I have my data, I can break it down into weekly and then look at the values, and if there are any values missing for weekly data, I can use a forward fill. So that can take care of my frequency data. Then let's look at the trends of the data, which is the last part of this project. So basically, let's look at the trend. So when you say trend, what does that mean? So in time series data, you always have some kind of trend. So that will exhibit some slow, gradual variability in addition to higher frequency variability, such as seasonality and noise. Now, to visualize these trends, what we do is we use what we call as rolling means. So we know how our data is spread over year or month or day. But how about looking at a rolling average and see what is the difference? So a rolling mean will tend to smooth a time series by averaging out the variations and frequencies. So this can be higher than the window size. So there is something called as windowing, where you can choose a set of time frame. You can also average out any seasonality on a time scale equal to window size. So this will allow you to look at lower frequency variation in the data. So when we are looking at electricity consumption time series, we already saw there is a weekly pattern, there is a yearly seasonality, which we saw using box plots. So we can also look at the rolling means of the time scales. How do we do that? So for this, you can use some package like Zoo, and then you can basically use a rolling mean using the Zoo package, and you can say what is the frequency with which you want to calculate the rolling mean. Now, how do we do this? Let's look at this data. So here I'm going to look at my data 3, which we have been using so far. Now let's call it a 3-day test. You can give it any name. I'm going to use my data 3. I'm using the pipe in function. Now I will use dplyr and I will arrange the data descending in year. Now you can always break it down step by step and you can see the result of this. So I'm going to arrange this data in descending order of year. So obviously my last one, 2017 or 2018, will be on the top. You want to group the data by year. So it depends on how many years we have, we'll see. So you can group the data by year. Now this data is then used to basically mutate. So mutate function is going to allow me to use this rolling mean. So I'll call it as says 03 day. So I'm going to calculate a rolling mean every 3 days for my consumption column. And basically let's ungroup this. So let's see how this works. Sorry. Yeah, let's look at this. And here, when I'm doing a 3-day test, let's look at the result of this and then I'll explain this. So if you see here, we have the test 3-day column. Now this has the rolling average. Now what does that mean? So first value here, what we see is 1367 is the average consumption in 2017 from the first date with a data point on either side of it. That is, you can look at this date, so 1130, then you look at, you are looking at the value 1367 here, so you look at 1130, 1441, 1530. If I take a mean of these, so for example, if I would just do this part, and that is giving me mean, okay, because I have a comment, So let's basically add anything as comment, and then let's do this. So it says me 1367. That's what we are seeing here, right? So you're getting a rolling average every 3 days. Similarly, if you want every 5 days, it takes the 5 values and it gets the mid value, right? So you can always find out the mean, rolling mean for a particular frequency. Now, let's do that for 7 days, that is weekly data, and yearly data, that is 365 days. So how do I do it? Same logic, my data test. Now I'm using my data 3. I'm arranging it in a descending order. I'm grouping by year. So when you do a group by year, so earlier when we did a grouping by, and when we looked at the data, it was telling me how many rows we had, right? So let's do a grouping by year, and let's say test 07. So that's a rolling average every 7 days, and I'm also saying take care of the NA values. Similarly, I'm getting rolling average every 365 days. Might be you can do quarterly, might be you can do half yearly. And let's do this. So let's create this, my data test, and let's look at the result of this. So I will use my data test. I will say arrange based on modified date. Now we know there is a column called modified date. I want to just look at 2017 data. So I'm doing a filter, right? And then I will choose what are the columns I'm interested in. So I will look at the 7 and 365 day, and let's look at say first 7 records. So let's do this, and that basically gives me the consumption value, modified date, year, and my rolling 7-day average or the 7-day mean, which is for first 7 days. And then 365, you will not see the data here, but if I do a view on this, I can basically see the values. So you can always select a particular column to see the values. These are the values for every 7-day rolling average. This is for 365 days, every 365 days. So you see all the values are missing, but every 365 entry, you will have basically some data. Now, let's do a plotting of this and basically visualize this data which we are seeing rolling average. So let me first do a plotting, one plot per graph, and let's do a plotting. I will take consumption data, x-axis, y-axis, color, and give a title to this. So let's create this, and that's my consumption data, which is spread over a period of time, and that's fair enough. But now let's add some more plot to this. So I will add the 7-day rolling average to this. So for second plot to be added in the same one, in R you can use points. So I will say points. I will choose 7 data column. Type is line, width, X limit, Y limit, and color. So let's do this. And that's my pattern 7-day rolling average, which basically gives me some kind of trend. Similarly, I can add one more here, and this time I will choose the 365 day and look at the pattern lines. So now you see some dots here. Well, you could do it in a different way. So I can just add legend to this, and I can say legend will be where in x-axis and y-axis. So I'm saying it will be 2500 and y is 1800. So my legend will come in somewhere here. I'm saying my legend will have consumption, test, and this one I can give some names. I can give what is the color. I can say what kind of legend. It explains what is for each color, and then basically a vector. So let's add a legend to this, and I've added a legend. Now you can do a zoom and look at the data, and here I see that my x-axis is fine, but y-axis is going a little out of my plotting area. So I can actually change that. So here I have 1800. How about making it 1600? And let's look at this one. So we can basically go for this one and start again here, plot and points and line, and then add a legend, right? And you can basically place your legend anywhere in the plot. So this basically is giving me the trend, what I'm looking at, my rolling average. So similarly, you can look at the trend for wind and solar data. So what we are seeing here is when you look at trend, this is one more way of looking at it. You can always create plots in different ways. So 7-day rolling mean has smoothed out all weekly seasonality, which we were seeing here in my graph, where you look at every 7 day, preserving the yearly seasonality. So 7-day will tell that electricity consumption is typically higher in winter and lower in summer. So better is you break it down yearly. So here, if you look at every year, you can see when is winter, when is summer, what is the seasonality, what your trend, what you're seeing here, and if there is a decrease or increase for a few weeks every winter. So similarly, if you look at 365, now as I said, rolling average basically reduces the variation. So if I look at 365 rolling mean, we can see long-term trend in electricity consumption is pretty flat. Now that's what we are seeing. It's kind of pretty flat. There is not much variation over years if you really join these dots. So we can basically see some highs and lows, and that gives me a trend. Now this is how you can do a trend detection, and similarly we can do plotting for wind and solar. So this is a small project which I demonstrated using R. Now all this code which you have here in the form of a project.r file, you can find here in my GitHub page. This is the document which explains some things. Feel free to download this and you can add details to it. This is the sample data set, which you can also find in my repository in the datasets folder. So continue learning and continue practicing R.
Okay, now let's see two more crucial projects related to German credit data and college admission project. So here we are going to use two algorithms. The first would be a logistic regression algorithm on the German credit data, and then we'll explore about k-means clustering algorithm and solve a business case study regarding college admission.
Let's go ahead and take a hands-on demo and just see what does this look like. Now I'm going to go ahead and use the Anaconda Navigator and the which is your Jupyter Notebook, which will then open up in Google Chrome. This is one of the IDEs or ways of editing Python code. I like this one because it, one, protects my computer and creates its own kind of container, and two, it's got a really nice visual demo for doing Python. Certainly you can use a number of other different tools like PyCharm. Is another real popular one. You can actually access PyCharm code through the Anaconda Navigator now, and there's a lot of other tools on there that each have their benefit. And we come into our Jupyter Notebook. I go ahead and create a new Python. I've already done that. And we'll start with a logistics regression model, just so you can see what this looks like in code. We'll actually do two of these as we go through this, and take a look and see what that code looks like in Python. Now, the first thing we want to go ahead and do is load up all our parts modules that we need in our Python code. I'll go ahead and run that, and you'll see here I'm going to ignore warnings because some of the stuff we're doing, we're just looking at it in as you go from one version of Python to one version of whatever the scikit, or in this case the SC package. You'll see some warnings come up. They're not really important right now. And then we're going to go ahead and use the German credit data CSV. And so when I run this, this is all loaded up. Now let's go ahead and just open up this CSV file so you can see what that looks like. And here it is. Here's our German credit data file. We'll go ahead and just open that up with, let's do WordPad is fine because it's a Word document. And when we open that up, you can see right here it's just a bunch of comma separated values. We have across the top, it actually has columns on here, so our first row is a bunch of columns. And then of course we look down here. Oops, I just moved stuff around, but that's okay. I'm not going to save it. And you can see the values, AL1, AL4, whatever that means, or A14 I guess, and then some sorted numbers on here. And we'll take a closer look when we get into the program and looking at the data. For right now we've loaded that under credit DF. And at this point, I want to just kind of take a detour back to the life cycle of data science so we can see how that fits in there. And so we've already done our data discovery. We have a little data prep, but the data is pretty clean. It already comes in preset on there. We might do a little data preparation in here. We're going to start looking at exploring the data analysis and building a data model and then interpreting the results. So really we're focusing on the last 3 steps of this. The data discovery would be start asking questions of what do we want in there? Is this going to be a good loan, a bad loan? What do we want to get out of this data? Where are we going with it? That would be part of the data discovery. And a lot of times that might be a meeting you have with the management in the office or whatever. And then data preparation is, of course, cleaning the data up, making sure you know where the source came from, all those kind of fun things that go into making sure you have good data coming in. Now, you'll notice here, we're using pandas. Whoops, I drew it through the pandas. And we're going to go ahead and read it as a pandas data frame. And of course, pandas sits on Numpy, so a lot of stuff you do with pandas can go right into Numpy very easily. And the reason I bring this up is because pandas has a lot of tools in there for just looking at the data real quick and easy. And so the first one we want to go ahead and do is do credit.df or credit_df, our data we read in, info, and just see what that looks like. And when we go ahead and print this out, you can see here we have 13 columns. Remember we were looking at our data and it had that row you couldn't read across the top. Then it has non-null count. How many values don't have null? What kind of objects are they? They're an object, an integer, different things like that. And we look at object, is it a checking account? This is probably text on here. Duration, how long, credit history, amount, savings account, present employed since. So a lot of different numbers coming in here, and these are just the columns we're looking at. And if you're going to look at the columns, it's kind of nice to actually look at the data. And so we'll use the pandas to go ahead and print it out just like you would on a spreadsheet. Hard to see them all on here, but you can see we have, here's our row across the top because Panda does such a good job sorting out columns and the actual data. Checking account A11, A12, A14. Not sure what that means. Duration, how long they've had it. Credit history. Not sure what the A33 or A34 means. I'm sure it has a special meaning on there. The amount. Here's our savings account and all the information on that. This is actually a much more easy to read view than what we had before, as far as like that text file. When you're just looking at data through the database, sometimes those can be really hard to read. This you can really see, and if I take it down a notch, I can get all the columns in here. We'll go ahead and keep it zoomed in just so we can see what's going on a little easier. And then we can also do creditdf.ilocation. The ilocation feature in the pandas is going to go ahead and do rows 0 through 5, and we're going to look at columns 1 through 7. And let's go ahead and just run that. And you can see right here how we just split it up. So it's real easy to manipulate our data and get a smaller view of different parts of the data as we're going through it. And just like we can look at the first 7 columns, we can also look at the last 7 columns. Same kind of format. We're looking at rows 0 through 5, column 7 to the end, if you leave the number out there. And you can see we can easily now look at this on a smaller screen, much better for displaying. Those are just tricks to help you display your information so that when you present this in front of a group of people, it makes it very easy to read, or you can just copy this out and put it into a document, that kind of thing. And then we also like to go ahead and do like credit status value counts and things like that. Again, we're just looking at the different sets of information on here. And in our pandas data frame, value counts is we're looking at unique values. So there's a lot of unique values in here. That's 700 and 300. That's a significantly diverse set of data. And if we look at the data, one of the things we're looking at is the status 01, 001. And I'm going to guess that that means that it is either default or not default. So that's probably what we're going to want to look for. Hopefully you've had your specialty in domain. Remember we talked about the different parts of data science. Domain is what field it is in. This would be in banks and loans. And so if we want to figure out what the status of a new loan is, we're going to separate the status out. And so if we take our X features equals a list of the columns, that's all this is, credit underscore df dot columns. We remove status, and then we go ahead and this will print our features out, and you can see it's everything but the status on the end. Because that's what we want to predict. We want to predict the new data, whether that status is 0 or 1 or not. And next we want to do a little bit more data preparation. We're going to go ahead and encode. And we're going to take an encode credit df. We're going to create that off of our setup on here. And you're going to ask, well, what are we encoding on here? Well, when we go up to here, let me just go back all the way. When we're looking at all this information up here, you can see there's object, object, object. Well, if I'm doing a prediction and something's just a random object, it doesn't really mean anything. There's no numbers to process. And so when we come down a little further, we can see down here that we are looking at A65. I'm not sure what A65 means. We're looking at A93, personal status. We're looking at A143. These aren't actual numbers. There's some kind of code that the bank put in, probably. And so for our model, they really don't mean anything unless we convert them to numbers. And you convert them to numbers by literally creating a bunch of yes/nos. So instead of thinking it as A173 and A172 as being 0, 1, and if you had A174 maybe 0, 1, 2, you would think of this as a label, A173 is true or false. And then you'd have another label, A172 is true or false. So for every unique job in here, that it becomes another feature added in, and it's on or off, it's true or false. That's what this encoding is doing. And we'll go ahead and list our encoding as it comes out. And if you come up here, you can see it did exactly what I was describing. We've now encoded it. So here's checking account A13, checking account A12, 14, A31. Here's all of our checking account numbers. So there was 3 of them. Here's our credit history, A31, A32, A33, A34. Again, the computer has no idea of knowing what those are. All it knows is those are each unique features. And the same thing with the savings account, A62, and so on, going down. And so once we have our nice list of there, we can go ahead and do... let me pull this in. Here we go. Let's look at our new data set. And if we go ahead and run the new data set, we have our encode credit DF checking, and we're just going to look at these and look at the head. This is just the first few of these, so we can see what it actually looks like in the data. And just like I said, it's now 0, 0, 0, 0, 1, 1, 0, 0. This first column is just the count, 0, 1, 2, 3, 4. That's not part of the data. But you can see here that it just puts a check mark of 1 because it's an AC A12, and we have a checking account AC A14 where it's also a check mark of 1 going across. So we've done a little data preparation. We've come in here and done some exploratory data analysis. And now we want to start building our data model. And we'll kind of go back and forth between exploratory data analysis and data model, and then interpreting the results on this. And so when we go ahead and import our stats models as API as SM, now a lot of times we use the sklearn or the scikit models. In this one we're going to go ahead and use the SM model from stats models, which is pretty common for doing a very basic logistics regression model. And then from the scikit we're going to have our train test split. With any data, you want to go ahead and train your model, and then you need something to test it on, some unknown data, so you can see how well you did. Very common in your setting up your models is to split it up into your training set and your testing set. And what I want you to notice on here is we have xtrain. Well, what is xtrain? That's all the columns except for the last one, which was the status. Was it default or was it in good standing? And then, of course, our x-test is part of the data. We're going to split that up by 0.3, so 30% of the data is going to be, 30% of our rows are going to be put in the x-test, and the y-train and y-test is just the status. And then we create our, once we've created our data and split it up, we go ahead and create our model, and it's a logit. We're just going to call it logit, but a lot of times you end up seeing logit model. With logit, it equals the sm.logit xtrain, y-train xtrain. In sklearn, it's always xtrain y-train, but in the stats model, it's reversed on there. And then they go ahead and run the fit. So we load the data up and then we fit it. And then we can go ahead and summarize that model and see what it looks like. And let's go ahead and run that. It takes it just a moment. And we get a nice summary of our data. Again, we're still looking at the data. And we have, takes just a moment to kind of feed through, and you can certainly see where we have our coefficient, which has to do with the weights in the model. Standard error, that's very important as we look at this coefficient and how it affects the model. P is greater than the absolute value of z, 0.025. These are all your statistical notes on here. So as you look at these, you might look at like how big is a standard error. That's one of the big ones that I usually look at. As we go up and we start looking at the different things, the higher the error, the less, the more we want to be a little careful of it. The lower the error, the better. In more general terms, they also have dealing with the model and its iterations. You can see some general status on here. How many iterations did it have to go through before I was able to come up with the numbers? Because it kind of guesses. It's playing a high-low game, and it takes it 6 iterations till it finds what it considers the best fit. And you can see there's more information up here as far as when it converts, how it converts, and so on. Now, when we have our summary up there, one of the questions starts coming in. Remember I told you we're looking at like our standard error and how these numbers all are telling us how important each one of these features is in running our prediction. And if you have a ton of features and some of them are just kind of all over the place, all they do is create noise. So we really want to get rid of them. They also cause issues in that if you're running a huge amount of data and you have to rerun this model over and over again, this can really tax your time, and so you're losing both time, money, and your results might not be as good because they might be weighted based on some of these very fuzzy numbers. So we're going to look at significant variables and put together a little routine for that. Again, we've come in, if you remember from back here, we're still in kind of an exploratory data analysis and data modeling. They kind of go hand in hand sometimes. We haven't quite got to interpreting the results and running predictions. And so we'll go ahead and build this thing on here. It looks at the LM values, so that's coming up here where this was generated. I'd have to actually look that up for this particular model because I usually use the sklearn version of this. So as we look at this, we're going to look at the p-values of our variables, and basically we're looking to see how good the p-values are. If they're less than or equal to 0.05, we probably those are probably solid values, and if they're greater than that, then probably we're not interested in them. And so let's go ahead and run this, and we see that when we pull out all the values that are less than or equal to 0.05 for the p-values, and if we go up here, here we go, here's our p. I knew it was up here, I just wasn't seeing it correctly. So you can probably see duration, that's going to be good. Amount, 0.01, that looks good. Instant INST rate, which I'm guessing is the percentage rate or the interest. I was trying to say INST and interest at the same time. So we have our interest rate and all this. If we come down here, we see duration, amount, our instant rate, age, checking account A13, checking account A14, credit history A34, savings account A65. These are our primary features. These ones are related when we look at the data. These are the ones that are going to predict whether it's a good or bad loan. And so now that we know which ones work, we want to go ahead and recreate our SM model, or our final logit model. And you'll see here we now have the X-train, the Y-train, and then instead of the X-train, it's X-train significant variables right there. So all we're doing is running this just on the significant variables in the setup. And we'll go ahead and fit it. And you can see here you can actually double bracket and do it all in one line. Up above we had to do it in the 2 lines. There's just how the setup is for this particular module. And then we'll go ahead and do a final legit summary and just see what that looks like. And we can see here's our p-scores. Remember, they're all supposed to be under 0.0, underneath the 0.05. These are all under 0.05. You can see up here are different statuses as far as how it ran. It still took 6 iterations to go through the data, the date, and so forth. And now that we have a solid model, and that's, if you remember correctly, let me flip back on over here. We've done our data modeling. We've created a solid model, and so now we need to actually run a prediction so that we can interpret the results and weigh in on that and see how good they are. And so for that, I'm going to go ahead and, let's see if we can find it over here. Y predict. So we have our model that we created. We want to go ahead and create our Y predict, and it's based on our final eject. And here's the magic word predict, or dot predict. And so this is where we're going to come in and actually get our predictions on here that our model comes up. And remember, we're testing, X test is going in. There's our X test, and it's only the significant variables. So we've created our model. Now we want to push in our test version that's never seen this data before. So this is all new. And then we're just going to take a random sample to see what it looks like. What do those predictions look like? In this random sample, we're just looking at 10 of these. And you can see here is the actual number. It says 0.08, gives us a 1. 0.07. This is our probability number, which is, I would have to actually look to see whether higher or lower is better. I'm guessing the closer to 0, the better it is, but I'm not completely sure on that. I have to actually look up and see with this particular framework. But you can see the actual prediction, 1, 0, 0, 0. So I guess this is a good loan, a bunch of defaults, and some good loans. That's what it predicts it's going to come out as. Now, just looking at the data, it's confusing. You have different models, they have different setup, they have the predicted probability comes out on this, and other models it doesn't. So you really need a tool to dig deeper into the setup to understand what this means. And so what we're going to do is we're going to take our predicted values, which you can see right here has an actual predicted probability, and then we're going to go ahead and insert on there from a sample. Let me just run this because it'll make a lot more sense. We have our actual value and our predicted value. So this is what we predicted, and this is the actual setup. If we just look at this right off the bat, we can see that we predicted 0 and this was a 1. These all came out correct. Number 332 came out correct. 917 was an actual. They were good on their loan and they predicted it's going to be a default. You start to see that there's some variance. So how do we measure that? How do we know whether our model was any good or not? Well, for that we're going to go ahead and load up a nice graph, and we'll use, for our graph, we'll import matplot library pyplot and Seaborn. Seaborn sits on matplot library. And this matplot library inline is just because I'm using Jupyter Notebook. With the new version I'm in, it doesn't even need it, but I tend to leave it in for older versions. And then we import from our sklearn metrics. This is your scikit. Scikit is the main package, and sklearn is how it looks on here. And we'll go ahead and run that so it's nicely loaded. And then we'll go ahead and create a little routine in just a moment here to print this out so we can see what that looks like. And this metrics is kind of a fun metrics because it tells you like how many you have correct on the correct one, how many you had wrong on the wrong one. And this top part is just all a draw routine. So it comes in here and has our actual and our predicted, and as our CM metrics, it breaks it up, puts it into the heat map. The SN heat map gives it some colors, add some labels, and then we go ahead and show it, and we're just going to dump that in there and run that. And you can spend forever building graphics. It's so much fun. We come in here, we have bad credit, good credit. We have bad credit, good credit. We have predicted label. And so when you look at this, you can see here it had, on the good credit, it tells you how well it predicted it and how many false positive it has. And on our bad credit, here we have bad credit, it said 30 of those were bad credit. It predicted them bad credit. While 21 were good credit that it predicted would be bad credit. And then we have 188 that were good credit. But the actual value, and then it had 61 that were bad credit that it said were predicted good credit. So at this point you'd look at this and you'd say, well, if I'm predicting this is our good credit here. Let me flip this on over here. And this is our bad credit. There we go. So we have bad credit, good credit. You start looking at that and you say, okay, can we afford that many defaults after 5 years or whatever it is? And so those are the questions you start asking is, does this model work good enough to predict whether we should give these people loans or not? You're always going to have somebody default on them. And again, that starts going into domain. Banking domain, something I don't know very much about. Clearly I know whether I default on a loan or not, which I don't, and I try very hard not to. And then if we're going to draw the chart, which is really nice to have just a clear visual chart. Metrics also has our classification report, and you can see these are just the numbers we were looking at. They let us know the precision, our F-score and recall and all that stuff on here. You can just print a straight out metrics classification report. Now we looked at a regression model. Let's go ahead and look at a clustering model to see what that looks like. And we'll go ahead and create a new Python on there. And this is going to be our clustering setup. Let me flip this off and switch on over to my clustering menu. In this case, we're going to be looking at k-means clustering. So let's just put that up here. K-means clustering. Now, the last one was a regression model. So it figured out coefficients for lines. You can go back to your old Euclidean geometry or the algebra expression for slope on a line, y equals mx plus b or whatever. And it goes on from there as far as finding distances and figuring out the lines on there. This is a little bit different. When we talk about clustering, it uses similar ideas, but it has to do with edges, 2 points, and how do you figure out a distance between 2 points and what does that mean? Now you'll see here we have our pandas PD, our Numpy is NP, our matplot library. Seaborn sits on matplot library as we talked about. They've added some parameters here as far as colors, and then we did an inline for the matplot library. Again, that's not really necessary. Even in the new version of the Jupyter Notebook, in the old version of Jupyter Notebook, if you didn't do that, it would just kind of hang or disappear. And then we're going to import some data. It's important to have our data set up in here. And instead of looking at this and guessing what the data is, usually you open up the CSV file at this time. Let's just go ahead and print it under the DF head. Because really those text files are so messy, and you look at the DF head and it's easy to look at. Whoops, had a path issue there. So college data, it's a CSV, so it automatically knows there's a .csv on there. And we can see here that they downloaded from a number of colleges, Abilene Christian University, Adelphi University, Adrian College, and then it has whether it's private, I'm guessing yes or no, apps, I'm not sure what that is, acceptance rate, applications embedding, and then the acceptance rate, enrollment, top 10%, top 5%, undergrad, so on. So these are just statistics based on the college, their college getting into a college. And just like we did before, let's explore the data. If you can remember from the chart we were looking at, we're going through our data discovery, data preparation, and exploratory data analysis. So we're really kind of looking at the data and what do we have here, what came in. At this point the data has already been prepared. We're not doing a whole lot as far as getting rid of null values and finding out whether it's bad data or good data and that kind of thing. And data discovery would be figuring out which data to send. So that we've already done. So we're going to go with the exploratory data, jump into data modeling, and then interpret the results just like we did with the other one. And we'll go ahead and use the Panda tool to get the info. DF, you'll see DF very commonly. It just stands for data frame. A lot of people use it as a generic setup when they import from Pandas. And so we have our info, and you can see right here, non-null numbers. Here's our count. So each one of these has 777 non-null values. And again, here's our type of data we're dealing with. And if you remember from last time, here's an object. This was our yes or no. Everything else looks like it's integer. We do have a float value here, integer. Floats and integers, usually when you're running them on a prediction, they're pretty interchangeable in a lot of cases. But whether it's private, true or false, that's pretty important on here. The fact that they could probably be switched to a 0 or 1 is pretty helpful also. And if we're going to look at all that data, we can go ahead and describe it. So there's our data frame, describe. And you have the same thing. Here's our count. All these should be 777. We have the mean value, so you can actually look at what our average is, standard deviation, minimum, different quartiles, 25, 50, the third quartile, that's so on. And of course our max value on there, min and max. And as we explore the data, we can do a lot of fun things on here. We're going to use our Seaborn, and we're going to look at room and board versus graduation date. We're going to add, this is going to be a heat map, so we're going to add whether it's a private college or not, how it fits, the size, the aspect ratio, and all that. That's what this line is here. Seaborn, you can almost do your own class on Matplot Library in Seaborn because there's so many features in there. But when you look at the very basics, you can throw up some data and have a nice colorful map set up. And here we have our graduation rate compared to room and board costs, and in private or public. So you can see that the graduation rate compared to room and board. Interesting thought. How much did I spend on room and board? Am I going to graduate the more I spend on room and board? And you can see numbers go up there on graduation rate. And you can see that the graduation rate tends to go way up for your private schools. And the room and board also continues to grow in private schools kind of thing. It's kind of just a fun heat map. And we can explore other things in our doing our heat maps. We can look at out of state, whether it's out of state, undergrad, private again is one of our setups on here. And you can see here that for undergrad, there certainly is a lot more public schools, and whether it's out of state, interestingly enough, the out of state number goes way up, how many people coming from out of state into the school for the private schools. Just kind of fun things. If you're trying to figure out where you're going to go, maybe you'd want to do this for picking a bachelor's degree or a master's degree or something, or certainly you could also plot this with fun locations and download information on tourism sites if you're traveling, that kind of thing. You do the same kind of thing with. And we'll go ahead and throw out another map on here. Let me go and run this. This is a slightly different setup on here with the out of state. And so we're running, let's see, pull this up. Bins 20. The bins is each, how many bins are you going to split it into? And this is kind of a fun one where you can see private versus public. We have how many out of state, and I'd have to look this up to see what they picked on here. Oh, there we go. Okay, so you can see we have another chart that has to do with the out of state and the number of students coming in, and private and public. So a lot of different setups on here as we dig into the different graphing. So at this point we've just been kind of looking at the graphs on here. Let's go ahead and import our cluster, our k-means cluster. And you can see here we're going to call it KM, I guess for K-means, or maybe it's K-means model. I always label mine with model. Equals K-means in clusters equals 2, random state equals 90. And so when we cluster it, we're only going to cluster into 2 groups. That's what this is meaning here, across the different settings on there. And then we're going to go ahead and fit, and we're going to drop private. So we're not going to be looking at whether it's a private or public school. And we're just going to go ahead and run the cluster on there. And then once we run the cluster on there, we can actually look at cluster centers. Let's go ahead and do that on this. When we talk about K-means, let me run this. Boom, there we go. So we have all these different columns, and each of those columns has a center, and we start looking how the data comes together on those centers. That's what all these numbers. This is the hidden stuff behind the clusters on here. And so we can now do, maybe we'll create a little converter here. If private equals yes, return 1, else return 0. We're going to run our cluster private and apply the converter. And then we'll go ahead and print that out. Let me just show you what that looks like so you can see what we're doing here. And then we go ahead and do df cluster. We'll create a new column on here, private, apply converter. And we can see here it creates private, apps, accept. We've just added on to our data frame on here. And we did that so that we can run the confusion matrix. Make sure we import our confusion matrix. We're going to do a classification report confusion matrix, and we'll go ahead and run this on our clustering. And as you can see here, as we're predictions, here's our confusion matrix up here, just like we had on the other setup where it has how many false, true, false, false, true, false, and false, false. As your accuracy and our setup on there, this is really, if you're looking at where you want to go, maybe you're looking at where you want to go in a, I think more of a tourism thing, but for colleges, this is a great way for looking for a bachelor's or a master's. Coming in here, and you can start finding out which one you want to go to based on this accuracy, whether it's private or public, or how many graduations are on there.
And that brings us to the end of this video tutorial on machine learning projects by Simplilearn. If you have any queries, please feel free to put them in the comment section of the video. Thank you for watching.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.